So let's have a very good start of this week. So basically, I'm working on density functional theory, and I'm looking into the different properties of the materials. So for the current my research, in my current research, I'm working on Hessler alloys. And this Hessler alloys, I'm looking into some promising properties like thermoelectric properties of Hessler alloys based on density functional theory and rigid band approximations. So let me start my presentation. So this is the place basically I am located. So I think most of the participants and the speakers are from Northeast. Probably they know the place, Mizoram, Aizawl. And this is my research group. And out of these five scholars, three of them have already submitted their thesis. They are waiting for their degree. And one has already awarded and two undergoing their research. This is the outline of my work. So I have already the the host has already introduced me that I'm an associate professor in the Department of Physics. And now let's come to my work. So I have 30 minutes, right? So I have to hurry up. So in thermoelectric materials, what kind of materials basically we choose is we choose semiconductor materials. I will come to know that why semiconductor and why not metal and why not insulators and all these things. So you basically, all of you know that the semiconductors are of two types, p-type and the n-type. P-type means in which the holes are the majority carriers, and the n-type are the electrons are the majority carriers. Okay, so thermoelectric means if you create the temperature gradient between the two terminals of the materials, then the potential difference will be created. So the current will flow inside the materials. So here you can see the red part is the hot end and the blue part is the cold end. So you create the temperature difference between the two ends of this rod. So let us consider this is a rod of the p-type materials, and the lower one is, let us consider this is the n-type materials. Now if you hit this part, then there will be the high potential region. Okay, well, the high potential region, and the holes will have higher energy. Once it will have a higher energy, it will try to drift towards the cooler side. So there will be accumulation of the hole at the cooler side. So basically it will give you the positive terminal, and there will be a deficit of the electrons, hole. That means there will be a negative terminals, so that will create the electric field. Similarly, if you go for n-type materials where the electrons are the majority carriers, then the electrons will drift towards the cooler side and accumulate here. That will create the negative terminal. And on the left hand side you will see the positive side. That will be the way it leaves the position. The electrons has leave the position and the hole will be created, then it will be a positive. So negative and positive terminals will be created. So that is the basic idea. So how does it work? So this is the simple device, thermoelectric device. You see that heat has been absorbed by this the two materials, p-type materials and n-type materials. I have already said that when the heat will be absorbed, the hotter end of the p-type will the hole will have the higher potential, then it will go towards the this side, the cooler side. And in the n-type you have the electrons are the majority carriers, then electron will drift towards the cooler side. So at the two ends you will have, at the two cooler ends you have the p-type or the n-type accumulations, or you can say that positive terminals and the negative terminals. Then if you join by a circuit, if you make a circuit, then you will get the external current. Okay, so external current will be there. So this is the basic idea. Now how can we increase the potential of this kind of device or this kind of a module? A simple module can be make in large scale, so that we can increase the efficiency. So you have to make this kind of things, a battery like of things. So many you have that n-type and p-type you have to connect, and that way it's a grid. So this will help in increasing the efficiency of the materials or the thermoelectric efficiency. We know that generally now very like hot topics, because as we all know that energy is the most important part of our life, and life sustainability and leisure life, all these things comes under the surplus use of energy. But energy crisis is another important issues that we have to look into it, and how to solve this this energy crisis is another, the challenging issues now to get the energy. At the same time, we have to look after the our environment also. So basically, this material science looks promising, but the efficiency is still underdeveloped. Okay, so now heat sources are are plenty. We can get heat sources from so many places. The basic things is like we need to get the heat and how to convert heat into electricity or energy. So we can get heat from the automobiles, domestic use, and nuclear plants, and hydro plants, solar also one of them. So many we have sources out there. And thermoelectric applications are not only for generation of the electricity, it has some other effect also. The reverse of the thermoelectric is the Peltier effect. From there we can get the idea how this in thermoelectric applications you can directly implement into the gadgets and all these things. This is a chiropractic disease. That means TGs means thermoelectric gears, and helmet, wearable helmet. All these things are also one of the aspects. So the history of thermoelectricity, how this thermoelectricity trigger the research, how this thermoelectric thermoelectric science came into the picture. So first thing was like Seebeck. Thomas John Seebeck, he found some interesting, he performed some interesting experiment where he has put the copper wire. This is the copper bar. On the top of the copper wire, he put this magnetic needle, and when he hit this copper bar, then he has found that the magnetic needle has been deflected. So this kind of thing is very, very unusual. Why this has happened? And as we all know that when the if you have a straight wire, and if the current is flowing in the straight wire, and if you bring the magnetic needle close to that wire, then the magnetic needle will be deflected. Okay, so he has found out this idea, like this was very intriguing. Despite there is no, the potential difference, he has no external this applied field, still only by hitting, okay, he has found this magnetic needle deflected. It is just like the magnetic needle when you place in the wire carrying the current, it is deflected. So this is one of the intriguing factors where people are drawn interest in this field. Then Peltier effect. Then another guy in 1834, he has discovered another kind of very interesting results, that this is the bismuth and copper, this is the bimetallic strip. So when he applied the field, the electric field or the voltage potential difference, this bimetallic strips having two joints, you will see that the two joints are there where the bismuth and copper are connected here, and bismuth and copper are connected here, okay, at the left side and the right side. So when he applied the potential or the voltage, then he has found some interesting results of temperature difference. The two ends have two different temperature, not the same, even though it is the initial temperature was same. So by applying the voltage, he has found the two difference of temperature. So this is also one of the factor. Then another guy in 1854, he has found out that metal rod, when he hit at the middle, he has found that at one end the heat has been absorbed, another another side the heat has been evolved. So he has named as positive effect, that is positive Thomson effect, and another is negative Thomson effect, where the left side heat has been evolved and the right side the heat has been observed in this metal rod when it is carrying a current. Okay, so these are the two. These are the some of the interesting results they have found out. Now, in 1949, this is a Russian guy, and he has found out how to calculate the efficiency of the thermoelectric materials. Thermoelectric materials efficiency can be found out by ZT. We call it ZT is just a symbol. Okay, it's not a letter actually. It is ZT is a symbol. We can represent this by eta or something else, zeta or something else, but they probably use ZT. So this is called the figure of merit. This figure of merit is written like Seebeck coefficient square multiply electrical conductivity divided by the thermal conductivity and multiply by the temperature. This will give you the efficiency. What is thermal conductivity? Thermal conductivity is a part of two factors. One is because of the electrons interactions or the electron collisions. Another one is the lattice vibration. When you hit the atom, or when you hit some solids, the atomic vibrations will be there, and that atomic vibrations will create the some kind of heat wave. Okay, so most of the thermal electric materials that has been discovered so far are here. So PBTE, Bi2Te, then SiG, screwdrives, clatterites, half Hessler alloys, and other things are also being discovered so far. And the publications in this research field, on this field of thermal electricity, is like it's growing exponentially. So so here some of the materials which is showing very promising results are like PBT, Bi2, T3. All these things are showing promising results. From here also, the left graph also, you can see that the efficiency are very good for those kind of materials like PBTI, then screwdrives, then Bi2, T3. All these things are promising, but the thing is they are not very good for high range of temperature. You see that it goes and terminates somewhere out here. But we are looking for those kind of materials which whose efficiency is low, but which can work, whose working range of temperature is very high. So the Hessler, we have found Hessler alloys as one of them. I will come to know why Hessler alloys. Hessler alloys is one of them because Hessler alloys, you see the graph, it is increasing linearly. So with the temperature, the efficiency is increasing. So that means we can use these materials for a high range of temperature. So metal semiconductors or insulators, what kind of materials generally we use for thermoelectric materials? So based on these papers, we have to decide what kind of materials we are working on. So this is a very good papers from GKH Matson and David J. Singh. This is a lot of complex mathematics are there. So I have to go for these complex explanations because I have no other results or anything to show, because I'm a theoretician, so I have to go for equations and all. I'm sorry for that, but I cannot skip all these things. So as we know that from the free electron theory, electrical conductivity is given by this one, and is the charge density is the charge, then tau is the relaxation time of electrons, then divided by the effective mass. So from the concept of this one, matter waves duality, we can write momentum as P is equal to h by lambda, but h is your Planck's constant, lambda. Then again, more simplified form, this lambda we can write in terms of the vector, momentum vector h. So P will be hk. So now if you take the derivative of momentum, you get the force. So this force is given by h k dot, okay, h bar k dot. So this force is actually the electrical force. This has been generated because of the potential change. Okay, so this is the force minus Q. E minus is because it is the electron charge. So minus QE is equal to HK dot. So now let's come to the picture of how does it looks in when you do the transformations of your space from the real space to the momentum space or the K space. So in the in these pictures we can see that the current density is given by J is equal to minus Q divided by uh, uh, this is omega, then summation over Vk Fk. Okay, so this is the current density. Q is the electron charge, and this omega is the volume of your Fermi sphere. Then summation over Vk is the Fermi velocity, and Fk is Fermi functions. So this is the picture of your J in your K space. So this is your current density. Now working based on this, we will work on here that electron undergoes rigorous. When you have a temperature difference, the potential difference will be created, and the electrons will flip from one place to another. So that will create a chaos inside the materials. Okay, so all these pictures can be visualized as the like shift of the Fermi sphere. So when there will be a collisions of the electrons or like some chaos inside the materials, the electrons will move from here and there. So that will definitely create some changes in your Fermi sphere. The Fermi sphere will be drifted by like this. Okay, so this is the original picture when you are not applying the field or not applying the heat. When you apply the heat, the potential difference will be created, and this Fermi surface will Fermi sphere or Fermi surface will drift towards this side. So actually this is the Fermi surface. Just take this as the Fermi surface has been moved. Okay, the amount of the Fermi surface or the Fermi sphere that has been moved is given by this shaded part. Okay, and this shaded part is nothing but the amount of the current density, because the whole electrons has been moved in this field. Okay, so we can write this. dk can be written as k dot tau t. So from this concept of current density is due to the displacement of the Fermi sphere that I have already explained. Now let's see how does our equation looks like. This whole pictures I transform into equations. So now from this concept, the current density can be written as this one. So minus k dot t is the amount of shift that, as I explained, this delta k is the amount of shift. So I can write like this: J is equal to minus Q. The same equations. Okay, the amount of shift is Fk is minus F delta K. Okay, F delta K, I can write K dot T. Okay, so now this kind of expression I am land up. Now how to solve this problem? So this problem can be solved by applying the Taylor series. So Taylor series, you can use this Taylor series and neglect the higher order terms. So when you apply these things, so we'll land up to this equation 11. So what does this equation 11 talks about is, this is the amount of your shift in the Fermi sphere. Okay, so we are basically interested in this part where you have this equation 11, the second part. Okay, the equation 11 second part, that is the actual the amount of the electron drifted. Okay, so that will give you the actual your current density. So from the Ohm's law, we know that J is equal to sigma E. Okay, then comparing equation 12, equation 12, this is your equation 12. Okay, then equation 12 and this 13, we get the conductivity tensor. We get the conductivity in the form of a tensor. Okay, so now The density of states projected conductivity tensors can be defined by considering minus del F by del K, and this is the delta function. Okay, so del F by del AK is actually a delta function. This will give you the delta function. So now when EI is equal to EK, okay, EI is equal to EK, then you will get one single line. Okay, but when delta EI is not equal to EK, then it will get some kind of broadening. Okay, and when EI and EK is equal to I mean this term is 0, when this term is 0, then you get the single line. That means you got a, that is the that is the picture of your one single states. Okay, but when EI and EK are not equal, the states are broadening. Okay, it's a broad. So that we can use out here. This concept we can use out here in our expression. Then we will get this kind of expression. That means equation 13 now we can write in these forms, like del F by del AK, I can write del EIK and del EI minus del IK format, right? So now the kernel of transport expression is given by this one. This equation 16 is nothing but the manipulation of this one. Okay, so I have taken out all the terms here and now I can replace this one. So sigma, this is the kernel of your transport distribution. Then this is sigma dash is equal to q square summation over k and v alpha and b alpha t, or b alpha and d alpha are the this velocity, the Fermi velocity. So this is the picture I wanted to show, because you have suppose this is the n type, when the electrons will when the left side is heated up of this materials, this is n type materials. This is T1 is the temperature and T2 is the temperature on the right hand side and the left hand side respectively, where T1 is greater than T2. Okay, then you will see that the electrons will drift towards the T2 size. Then electron accumulations will be here and the whole accumulation will be here. Inside there will be a potential difference. So this is the basic idea. Now in terms of like electron density or the electron DFT, how can I show this one? Is like this is the Fermi shift has the chemical potential has been shifted at the higher side, and here the chemical potential has gone down at the lower side because of the the two temperature difference. When you apply the temperatures here on the left hand side, the chemical potential will go high, and here the chemical potential will go low, or it will remain the same. And you see that it has a, because we are talking about the rigid band structures, we will just assume that nothing has been changed to the density of state. So this is the concept, or this is the very crude assumptions, but somehow it will give the good result. So this is in practical, the density of states or the band structures changes when you apply the temperature. But here in theory, we cannot do all these things. We cannot implement all these activities. So we will assume that only we will map those density of states and the band structures. Okay, but it will not change with the effect of temperature change, right? So now all of you know about the characteristic of the Fermi functions. How does it looks like? And if you take the derivative of the Fermi functions, it will be like this. This is Lagrangian type of broadening. So you will see this one. We are interested only in these things. So why we are interested in these things, I will come later. So now the current due to the potential difference and the temperature is given by this part. The expression is we have taken from Landau-Boltzmann expressions. The current is like this form, and 1 by q. This I have already explained this integration from minus infinity to plus infinity, and this is sigma dash is the conductivity tensors. Then we have a two different chemical potential that results in two different Fermi functions. Again, we will use solve this problem by using the Taylor series. Then once we apply the Taylor series, we will get these two parts. One is this, another one is this. First part is the pink part, another one is the yellow part. The first pink part is the coefficients of delta V, and second part is the coefficient of delta T. Okay, so now I cannot say all these symbols again and again, so I will just that's why I put them into shaded, like pink shade and the yellow shaded. Okay, so now current is now inside the current inside the materials, or the thermoelectric materials, is two types. One is because of the potential, right? Another one is because of the temperature, because you have the temperature difference as well as the potential difference. Okay, so the the current inside the materials due to the potential difference is the charge current, and the current inside the materials due to the temperature difference is the heat current. Okay, so these are the two currents. So now basically I am interested into charge current, so I will take only the first part. Okay, the first part, which is because of the delta V change in the potential. So I will name it as sigma E, because let's refer sigma E as charge current. Okay, so charge current, charge, E is the charge, so sigma E is the electrical conductivity because of the charge flow of the charge. So I can write like this. This is equation 25, and equation 26, let us not touch this one, let it be like this only. Equation 26, it is because of the temperature difference, so let it be like this for the time being. Okay, so I am concerned only about the sigma E, that is the electrical conductivity because of the potential difference, right? So now, how does I can apply this out here is like, I will take the density of states or the band structures, then I will fit this sigma E equations into this one. Okay, into these expressions. Now you see this one, del F by del E is the derivative of the Fermi function. So this derivative of the Fermi function looks like this. This is represented by dotted line, and you see this one, this dotted line, and this is changed with the temperature. Okay, these things will change with the temperature, not the band energy. Okay, the band structures will nothing to do with it. It is rigid. We have assumed that the band structures density of state is the rigid one. Only what we can change is the sigma E. Okay, so sigma E I can change. How we can change? We can change by taking this Lagrangian. So the broadening of the Lagrangians will take more states. If it takes more states, that means the electrical conductivity will be high. If it takes less states, then the electrical conductivity will be low. So as we already know that we cannot change the band structures. Suppose this is a semiconductor. Okay, so semiconductor, then from here what can we expect? We can expect in what conditions this Lagrangian will takes more, or the map more states. Okay, so that is the main concern. So here, if you go for metal, right, if you go for metal, it will take more states because metal doesn't have a band gap, right? So it will take more states, and the electrical conductivity will be extremely high. Now if you take for a semiconductor, it will take more states and your electrical conductivity will be mediocre, okay, or in the average range. But if you go for a insulator, that means these two legs, or the two, the two legs will not stretch enough to take the more states, right? So it will not penetrate inside the density of the states, so it will not capture more states. So that means your electrical conductivity will be low in that case, in case of the insulator, right? So that means which is better? Up to here, metal is better because it is taking more, this Lagrangian is taking more states in the metal. In semiconductor, it is mediocre, average, okay? But in the insulator, it is very difficult to go, penetrate these two legs inside the states, so it takes less. So far we have understood that metal looks better, okay? So this is the real, this is the picture how it we can show it. I is sigma E delta V plus sigma S delta T. What is I here? I is the total current. Okay, I is the total current, that is the external current. So I is the external current. Internal current is because of this one, change in the potential and change in the your temperature is inside the current. But if you add both, then you will get the external current. Okay, if you join this one, this is the external current. So the light will go like this. It looks like a battery. So battery cell. This is the current. Now what we will do is we will short circuit this one. If we short circuit, what happens is the external current will be 0. So I will get this I will be 0. Okay, this I thing will be 0. Then I will be land up with this kind of things. There will be dB by dt. So if you take this one, if you take dV on the right hand side, if you take dV if you take dV on the left hand side and all of the terms on the right hand side, I will get equation 29. Okay, so this is very simple. And now what I will do is I will just short circuit. Short circuit means the total current, the external current is 0. If the external current is 0, the first term will become 0. First term 0 means that means minus sigma S divided by sigma E delta T. Okay, so I will get del V by del T is equal to minus sigma S by sigma E. So what is dV by dt? dV by dt is nothing. We are very familiar with this term from our BSc standard also, I think from our class 12 standard also. Okay, dV by dt is the derivative of potential with respect to temperature is nothing but the Seebeck coefficient. Okay, so now we land up to the Seebeck coefficient S. So Seebeck coefficient S is given by minus sigma S divided by sigma E. This sigma S is the one which I left earlier. Okay, I said like, okay, I will be utilizing this one in the later case, so I can use here now. So now my Seebeck coefficient looks like this, right? So I put all these complex term here, then I will get this kind of things. Then I will solve this one to a simple form, that is E minus mu divided by QT, right? So now here, how does it looks like? E minus mu divided by QT, right? So now here, from here, how do we come to the conclusions here? What is E minus mu? E minus mu is the difference of the energy with respect to the Fermi functions or the Fermi energy or the chemical potential, right? So E minus mu will basically, it gives you the band gap, okay, almost like a band gap. If it is an N type, then the conduction band, the lowest part of the conduction band up to Fermi energy, that will be your E minus mu. And if it is a P type, then Fermi energy minus the highest of the valence band. Okay, so that will give you the this value. So that means it is like a band gap. So S value, the S will changes when you change the band gap. So bigger the band gap, the S value will be high. S value will be high when you have the bigger band gap. But in the earlier case, sigma value will go high when the band gap is low. So this is a little bit tricky and controversial. How can we solve this one? This is not controversial, but it is a little bit tricky to solve, because to get the high value of efficiency, we need S, that is Seebeck coefficient, also high. We need sigma also, we need to high. But you know, like if you try to increase S, then sigma will go down. If you increase sigma, then S will go down. Okay, so but in our expression, the efficiency is S square sigma divided by K. So both should be high, but here the two things cannot be controlled simultaneously, right? So this is tricky things, but how we will optimize this one? But we cannot control them. I mean, we cannot control them, or we cannot decouple them, and we can control individually. Okay, if you change one, another will definitely go high. So it's a tricky thing. So, but we can optimize it. Okay, how can we take the optimize? Means how can we take the best value? So what we will do is we will plot the sigma and S with respect to chemical potential or respect to the carrier density. Okay, doesn't matter. You take S as a function of the carrier density, or you take the sigma as a function of the chemical potential, doesn't matter. So then we will take S square sigma. Then from S square sigma also plot with the same with respect to the same function. Then we will see that one some point we will get the high value. So this is the optimized point. So with respect to this optimized point, we'll drop a line. Then this line will drop at some point, right? At sigma, it drops, caught the sigma at this point, and S, it caught the S value, this perpendicular line at this point. So we take these two values. So these are, we consider them as the optimized value. So when we consider this as the optimized value, then we will calculate the S square sigma divided by KE, or the K, and multiply by T. That is your efficiency, right? So now that's all about the charge and all. Now let's come to the how the heat current is developed, how heat current has been this one. So now we will come to the same expressions like before. Now we will consider this as a heat current. So this is the expression for heat current. It is taken from Landau expression. Then same technique has been applied here also. Then we will go like this, and dV by dt. Then the coefficient of dV and dt can be written as like this. 38 and 39 is 38. Equation 38 is the coefficient of your potential, and this one is the sigma k is the coefficient of T. Okay, so here we have land up into these expressions. Now the electrical electron thermal conductivity, the thermal conductivity can be written as Ke by this term. Okay, and this is, what is this term actually? This is because of the potential difference or the temperature difference. This is because of the temperature difference. Okay, so because of the temperature difference, when you have the temperature difference, the electrons heat will flow, that will give you the heat current. Then from the expression of the heat current, we will finally calculate the Ke value, that is the electron thermal conductivity. That is the thermal conductivity because of the electrons. Okay, the electrons have a high kinetic energy and all. When you move the electrons at a higher rate or the higher kinetic energy, they transform the kinetic energy to each other's, and that will definitely spread out as a heat current. Okay, so this is how we calculate. Now, why we choose the Hessler alloys? How much time do I have? Hello?
Sir, it's already over, but you can continue.
Okay. Can I finish in 5 minutes?
Okay, no problem.
Okay. Yeah. So this is the Hessler alloys. I will just go basic characteristic of the Hessler alloys, why this is important and why this is interesting. So Hessler alloys has been, studied for various reasons, and it is showing various interesting properties. And most of the Hessler alloys are ferromagnets. Okay, and they are basically expected to have its potential applications in the spintonics. They are highly stable materials, and it can be easily prepared in the lab. And they have a very good band gap, 0.5 to 1.8. That is best for thermoelectric applications, maybe not for solar cells and all. And low damping factors. The damping factor is very, very low, and low magnetic moments. Because of by virtue of having a low magnetic moments, it is having a low damping factors, and high perpendicular anisotropy and high Curie temperature. So these are the interesting fact about the Hessler alloy. And Hessler alloys can be easily identified. For what property you are going to utilize these materials, because we have already, well-developed equations or well-developed formula for, analyzing or pre-assume the properties of the Hessler alloys. Like suppose Mt is equal to Zt minus 18. This is for ABC type of Hessler alloys. Okay, or Mt is equal to Zt minus 24. That is ABCD type of Hessler alloys. This is for the ternary, and this is for the quaternary. Now, what is Mt? Mt is the total magnetic moment. Okay, and what is Zt? Zt is the total number of valence electrons in that particular Hessler alloy, right? So now let me go for this one. MT is equal to ZT minus 18. Now here X COSB, X is any transition metal. Let me take this TI. TI is having 4 valence electron, and CO is having 9 valence electrons, and SB is having 5 valence electrons. So when you add 4 plus 9 plus 5, it will be exactly 18. So if you put this 18 here, that is the total number of valence electron in TiCOSB. So I can get 18 minus 18 is 0. So its magnetic moment is 0. So this is a non-magnetic materials, and it should have a band gap. It is a semiconductor. So we can identify it that way. So now if you come to then another one, I will replace this X by V, vanadium. Vanadium has 5 electrons, CO as usual having 9, okay, then SB is 5. So in this case, so 5 plus 9 plus 5 will be 19. So if you put this one, this is XCOSB, that is first type, okay, that is ABC type. So now 19 minus 18 will be 1. So its magnetic moment will be 1. So this is a magnetic material. This is a ferromagnet or antiferromagnets or ferrimagnets. Okay. So basically, so this will give you 1. So 1 means it is having a finite magnetic moment. So this is the magnetic materials. Okay. So that way we can easily analyze the properties of the Heisler alloys in advance before going. Okay. Before just going for trial and error, we can go for this kind of assumption, and we can start working out, like calculations. So these are the half Heisler alloys and the full Heisler alloys. Half Heisler alloys is this type. We call this as ABC type. Also, we call it half Heisler alloys, and ABCD type we also call full Heisler alloys. And full Heisler alloys are this one. This is 1, 2, 3, 4 atom, one atom of Cr and one atom of Al. So this is full Heisler type. So this will follow the rules of MT is equal to ZT minus 24, and this is COVSB. I just give you the example. This will give you the this will follow the rule of MT is equal to ZT minus 24. So this is the interesting assumption. So many things about Heisler alloys. I will not explain these things. I will direct. I have used, first what I did was I used the density functional theory. Then I get the density of states and the band structures. Then I map this density of states and the energy bands to get the thermoelectric properties using the Boltzmann transport equation. So I use Y to K. Now I'm working also in quantum espresso. This is our latest paper that we have published, and this is the full Heisler alloys NaHF Xe Ge. X is the transition metal like CORHIR. We replace this one. Then we have we have checked with different compositions. Then we calculate their lowest energy. So among this one, the T3 phase is the most stable one. We have also checked their dynamical stability by calculating the phonon, and all these 3 phases are stable. And we have calculated the band energy, that is the must, that is the key. So band energy is the key in when you're calculating the thermoelectric properties theoretically. And then we have used both GGA plus SOC and GGA plus U. Okay. This is our results, thermoelectric results. So we have calculated the Seebeck coefficients for NaHF with respect to chemical potential, and this is for NaRHFGE. This is the power factor, that is S square sigma. This value we calculated to know the optimized result. And KL value that I have not explained all these things because in Boltzmann equations this KL is not explained. KL is the lattice part of thermal conductivity, because in ZT we know that S square sigma divided by KE plus KL. I have explained only up to KE. KL is a different part because KL comes out of the lattice vibrations. So our value is a very good one, that is 1.22 for NaHF COGE, because it is having a very good band gap, that is from 0.5 to 1.8. It is in the range of that one. So all our results depends upon the electronic structures. So if the electronic structures having a band gap in the results, so this is what we have found out. We have used different computational tools and we compare the results. So thank you. Sorry, I took, I think, a little more time. Yeah, any questions we can discuss?
Yes, thank you so much, sir, for your nice and informative talk. So it is open for interaction. The participants may ask questions or queries.
So I have removed the, so you can just unmute and ask, okay? I have removed the restriction now.
We can discuss outside the Zoom also, no problem. You can or you can mail me also anytime, no problem.
Yeah, that will be a good thing actually. Thank you, Dibya sir. So so if anyone has any queries, he or she can directly contact Dr. Rai over email, and he is very responsive to in Facebook also in Facebook also.
Yeah, in
very
all
responsive.
yeah.
So
I can reply if I know the answer. I can reply in, you know, like
So okay, so so thank you so much, Dr. Rai, for your informative talk on behalf of the organizing community. So I'd like to request you to chair one session actually for the next a couple of talks, I think around 4 or 5. So I have already provided you with the list, sir. So
yes,
you
yes,
make
the links are with me. Not a
yeah.
problem.
So for in that case there is a minor change. Sagar Bhattacharjee, he will be his particular presentation is rescheduled to I think after afternoon. So other than that the schedule is fine. It's the same.
Sagar Bhattarai,
He will be presenting at 2:30 today.
okay, afternoon.
2:30
So
p.m.
you will not
afternoon.
hear,
Yeah,
right?
yeah.
Okay.
So he had some trouble with his health or something actually. That's why. Okay. So if there are no more questions, then let's proceed to the sessions. Then presentation sessions. Okay. So over to you, Dr. Rai. You can. Yeah. So I think the first talk is by Mr. Amit Kumar Moria from IIT Guwahati. Okay.
Yes, Amit Kumar, then
Yeah, Amit Kumar, are you there in the?
Monica Roy.
Yes, sir, I am.
Okay.
Yeah.
So you can please share your screen, then we'll start.
Okay, sir. So should I start now?
Yeah, you can share your screen first. Then we can start. I think
it's 10 minutes, right?
yeah, 8 plus
so-
2. Yeah, 8 minutes plus 2 minutes Q&A. Dibya,
so
I think your
yeah,
screen is
it's
shared
shared.
actually. Let me stop. Okay. So now can you share, Amit?
Yeah. Okay, sir.
Yeah.
Yes.
Okay. Okay.
So,
you can see your screen.
my screen is
Yes.
visible to you? Yeah.
Yes. It is visible. Yes.
Okay, sir. Should I start now?
Yes.
Yes,
Dibya. Okay. Sure. Please.
Okay. So, good morning to everyone. I am Amit Maurya, a research scholar in Department of Physics, IIT Guwahati. So, my topic of just okay. So, my topic of presentation is structural properties and memory effects in the cluster glass phase of the pseudo one-dimensional spin chain compound CH3CO2O6. So these are the outline of my presentation. Here, first I will give a brief introduction about the spin chain compound. Then I will come to the experimental detail. Then I will discuss my result. Okay, so this is the introduction part. Here, the general formula of CH3CO2O6 is A3Bb prime O6. Here, A is some alkaline earth metal, which is basically some non-magnetic ion, and Bb prime is some magnetic ion, which is belongs to transition metal element. And this is like we have as a one-dimensional system. It is not exactly a one-dimensional. That's why it is called as quasi one-dimensional. This is part of my slide. I will like discuss why I am saying it as a quasi one-dimensional. So, and also it shows the geometrical frustration behavior. And here there are two cobalt present. So both of cobalt are in the +3 oxidation state, but their spin is like distinct. One is in the lower spin state, which is 0, and the other cobalt is in the higher spin state, which is like 2. And this is the one compound CH3CO2O6 in this series, which actually shows the quantum tunneling of magnetization. So basically, what is the quantum tunneling of magnetization? We can understand from this MH curve. Here we can see that as we increase the H value, like magnetic field, our movement gets aligned. But after applying each 1.2 Tesla, around 1.32 Tesla, we get a sudden jump in the movement. And this becomes after each interval of 1.2 Tesla. And the height of this jumping basically depends on the temperature. This is taken at 2 Kelvin. As we change the temperature, this height will accordingly change. And now coming to the structural introduction. So here, this is the structure of the pseudo one-dimensional spin chain compound. Here we can see that the structure is actually made up of a one-dimensional chain, interacting chain. These are forming the chain. And the chain are actually formed due to the edge sharing of octahedral and trigonal space. And these chain are separated with each other by some non-magnetic ion. So why I am saying it as a quasi one-dimensional? Because the distance between two magnetic ions along the chain is almost half of the distance between the chain. So the interaction between the magnetic ion along the chain is almost like 2 times or higher than the interaction between the chain. That's why it behave like a more like one-dimensional. Even if crystal structure is 3-dimensional, but it behave like a one-dimensional. That is why it is called quasi or pseudo one-dimensional. When we look at the top of this crystal structure, then here each point actually represents a chain, single chain. So when we look at the top of this crystal structure, we can see that each chain are arranged in a like lattice of the AC1. So after reaching at 12 Kelvin, we just stop the cooling process and we turn off the magnetic field and we leave the sample for getting it relaxed for 2-3 hours. We did it at like 12 Kelvin, 8 Kelvin and 4 Kelvin. And again, after getting it relaxed for 2 hours, here follow the part taken during the interrupted field cooling method. It means it does not forget its previous history even after removing the magnetic field and leaving it for getting relaxed, which gives actually a clear signature of the presence of magnetic memory. So it shows the memory effect also. Now this is the conclusion. So basically we synthesized our sample by using solid state reaction. Then we perform the X-ray diffraction to check the like stage and the stage purity. And we find out there are two magnetic transitions. One is from like paramagnetic to partial disorder ferromagnetic state, and the second is like spin glass behavior below 10.79 Kelvin. And we find out by interrupted field cooling magnetization that it shows the memory effect. So this is the reference. Thank you.
Thank you, Amit, for your very compact talk. So now the session is open for question, 1 or 2 questions, quick questions. Yeah. Okay, if there are no questions, let me ask you one thing. Like, I see that you have said that the two chains are having a very large distance, right? Yeah. You use something. The distance between the two chains, right?
Yeah, the distance between the two chains here. This
So,
is
what kind of interactions you report in this?
yeah, that is magnetic interaction total. In like here, these two are magnetic ions, that green one and that blue one. So the distance they will that
No,
they
that
will
I can understand. But you
yeah
have said that one chain as a
actually
you have
that's why
considered that.
I am
So
saying
in a way, it looks like a cluster of
used to say are pseudo one dimensional, like
room temperature, because they have a big gap, right, between the two chains. You have
so it is stable and like room temperature.
okay.
But we get the interaction like this interaction below the ordering temperature. Like in the room temperature, it is paramagnetic. But it shows the ferromagnetic and string glass behavior below the like 30 Kelvin.
So the I mean the bond between the two.
So magnet of like wonder was
But you have different this
yeah
chain. You have a cluster
different
chain.
chain.
How this
So
chain talk to each other?
a chain, yes sir. Like they have along the chain ferromagnetically,
Yeah,
but
that
they
I can
can
understand.
interact.
But between the
Yeah.
chain,
But between the chain, it can be ferromagnetic, it can be anti-ferromagnetic.
okay.
So we have to first find out the ground state, like using DFT calculations, like which state is stable for my system. So accordingly, we will proceed.
Okay, thank you.
Yes, sir.
Konika Roy, Tezpur University. In hexagonal WO3 using various electrolytes. Konika, are you here?
Yes, sir.
Okay, you can share your screen.
Sir, this is visible.
So one thing before this start actually. So we have also
Visible, but you have to make it large.
I will see.
Yeah, please go ahead.
Kindly make it full screen, Konika.
Yes.
Yeah, it's fine.
University working under the supervision of Dr. Chairperson. Today, the topic of my presentation is electrochemical study of total storage in hexagonal W3 using various electrolytes. So, as we know that the consumption of energy is increasing day by day, and the emission of carbon dioxide from different sectors, as we can see from here, like from different sectors, it is increasing day by day, and by 2050, it is estimated that it will be reaching 94%. So people nowadays are moving towards renewable sources of energy.
So excuse me, Konika, can you take your headphone close to your mouth? Yeah.
So now it is open. So like by 2020, like it was seen that the amount of renewable sources of energy is increased to a greater extent. So the different sectors that are contributing to the renewable sources of energy are like biofuels, biomass, hydrofuel projects, and all those things. But for the adequate energy supply, we need to store it. So here comes our research topic, that is batteries. Okay, batteries. So batteries are electrochemical devices that come with that convert the chemical energy into electrical energy. So in the market, lithium-ion battery is overpowering because of its very high energy density and for various applications. So there are the two modes that it is the charging mode and the discharging mode. But there are some disadvantages of lithium-ion battery for its high cost because it is not available. Availability of lithium-ion is very less, so the cost is high. Another risk is the bursting of lithium ions, and another problem is the lifetime of lithium ion is very less. So people nowadays are moving from non-lithium batteries. Here I am working on proton charge storage. So among the different charge carrier like lithium, sodium, potassium, aluminium, hydrogen is one of the abundant element on the earth crust. So the molecular mass of hydrogen is very less. For lightweight batteries, it is one of the finest and excellent charge carrier. Apart from that, the hydration radius of hydrogen is very less. And it works on a unique mechanism of Gaussian mechanism for its storage. So coming to aqueous electrolytes are lowest cost. It is environmental friendly. It doesn't catch fire easily. It is very easy to form electrolyte using that. So here for the electrode material, as we know, there are the three components of a battery: the electrode material, the cathode and anode, and the electrolyte. So for the electrode material, we have chosen W3. Because transition metal oxide has various oxidation state, and coming to W3, it has very high theoretical capacity. It is very easy to prepare, low in cost, and it can easily accommodate ion movement of ion through the electric material is very easy. So we have prepared using a simple hydrothermal method, and it was in the hexagonal phase, it was characterized by the XRD Raman, and it shows a nanorod-like structure which was evident from the efficient image. So for the electrode preparation, we took PVDF and NMP with the active material in 8:10:10 ratio, and it was dried overnight at 60-degree temperature. So this is the efficient image, and it was coated on a conductive material, that is the graphite. So here we have chosen three electrolytes, the H2SO4, HCl, and H3PO4, taking the same proton concentration in all the three electrolytes. 0.5 molar of H2SO4, 1 molar of HCl, and 3.75 molar of H3PO4 was taken, and it shows similar results in the three electrolytes. This is the CV curve, that is the cyclic voltammetry, which shows the electroactive activity of our electrode material. So this is the discharge graph. The peak position and the peak shows the reduction of the electrode material when hydrogen ion moves towards the electrode material. Then reduction occurs, and in the subsequent cycle we can see the charging, that is the oxidation of the electrode material is occurring. At that time the hydrogen atom come out of the electrode material. So this shows the electroactive nature of the H plus in W3. So this is the GCD profile, that is the galvanostatic charge discharge profile. Here we can see that the capacity is more in the case of HCl, HCl, but there exists a problem issue here. Here we can see continuous discharge that is happening. Continuous discharge is happening. It may be because of the electrolyte that we are using. It is aqueous based electrolyte, and over we are taking acidic electrolyte. So side reaction like hydrogen evolution reaction may occur, and for this reason continuous discharges is occurring. So this is the issue. And moving forward, we have taken H2 as H3PO4 as the electrolyte. As here we can see that at higher current density also H3PO4 shows better result. That is why we have taken H3PO4 as the electrolyte. So for the issue that we were facing, that the side reaction, we choose a particular kind of electrolyte, that is a gel electrolyte based on PVA, as polyvinyl alcohol has very high conductivity among the different polymers. So we have prepared a gel electrolyte in different ratio, like 1:5, 1:10. And here we can see it can go up to a subsequent number of cycles, which was not possible in the aqueous electrolyte. It can, for aqueous electrolyte, was like close to 30 or 40, but it could go up to 100 cycles. So here we got 1:8, it is showing a better result and not improve in the capacity, but improve in the performance of the cycle life of the electrode material. So here, for like two kinds of reactions that are happening for the charge storage. So mainly it is surface storage or diffusion control. So here, from using the power law equation, we have calculated the B value, and when it is close to 1, then it is due to the surface control, that is ions are storing at the surface. And if it is close to 0.5, then it is diffusion control. But here we are getting intermediate value 0.6, 0.8. So we can say pseudo-capacitive kind of behavior it is there. Like the charge storage are controlled mostly by surface, but their redox reactions are also occurring from this big is like calculated. We have calculated the B value. So now electrode material should be like stable after multiple charge discharge. So for that, we did the XR2 investigation, and here we can see that from the XRD, there is a little shift after first discharge, which is showing some kind of contraction that are happening. It may be due to the hydrogen ion, which is moving due to the first discharge, and some kind of bonding that are happening between the oxygen from the W3 and with the hydrogen. So some kind of contractions are happening, which is shown from the first discharge, and from the first discharge there is a little bit shift towards the left hand side, which is showing that the peak position are coming to its original value. It is also supported by the Raman profile, and it is showing similar kind of behavior. Now from the efficient images, we can see that there is no much changes in the electrode material after the first discharge and after multiple cycle also, which show stability of the electrode material after the cycle. Now, another strategy we have chosen, and that is we have made a composite out of graphene and W3, taking very less amount of graphene, that is 10 mg of graphene, and this is the XRD pattern of graphene W3 composite. This plate like structure, it shows the graphene flex with W3 along with the W3. So the electrochemical behavior of graphene composite is almost similar, but there is a little bit increase in the area of the curve, and here we can see that it can go up to 200 cycles, which was not possible with W3 in the same electrolyte. So in conclusion, we have synthesized W3 by using hydrogen method. Here, the H3PO4 is a better electrolyte for protostorage W3 for higher current density. There was a problem of long cycling stability, which was solved using a particular kind of electrolyte, that is the PDA-based gel electrolyte. Along with that, we have also seen that graphene-based W3 can also increase the cycle life, because graphene composite W3 enables the electrode of rapid movement of the H plus ion in the electrode material. Thank you. I would like to acknowledge my guide, Dr. Shamil, for this guidance, my laborate and physics founder for giving me the platform to share.
Thank you, Konika, for timely finishing your presentation. So let's have some short questions. Anyone, please unmute your mic and you can directly ask the question. Okay, if there are no questions, then we will move to another presentation. Rituparna Vaishya.
Yeah, Doctor, actually Rituparna Vaishya had to cancel it at the last moment. Actually, I just got the information. So we'll be moving to Dibya Saikya. So Dibya, are you there? Yeah.
Yes, I'm here.
Okay. So
Okay,
please.
Dibya Saikya from IIT Jodhpur. His title of the talk is Pressure-Induced Structural and Electronic Properties of CS PBI3 perovskite. Please share your screen and
Your screen is visible, Dibya. You can full screen it. Yes.
Yes, yeah. Please go ahead.
Yeah. Good morning, everyone. I am Dibya, currently a PhD student under the supervision of Dr. Chairperson Sahu at the Department of Physics, IIT Jodhpur. So my title of the topic is pressure-induced structural and electronic properties of cesium layer perovskites. So what is the importance of cesium layer in optoelectronics? So if we see the electronic structure of CSPB-I3, then it has a band gap in the range of 1.6 to 1.8 electron volt, which is suitable for single junction as well as bottom cell of the tandem cell solar cells. Furthermore, in terms of cesium lead iodide based perovskite solar cells, they have already recorded efficiency of more than 21%. And recently, this material have tremendous research interest in the field of solar cells, then light emitting diodes, photodetectors, as well as lasers. So these high performances are mainly attributed to large carrier diffusion length, then ultra soft charge dynamics. Then this material possesses high absorption coefficient of the order of 10 to the power 5. Then also it possesses very large carrier lifetime over 10 microseconds. However, there is a disadvantage of this material. At room temperature, it shows a phase transformation from its photoactive to photoinactive phase. So application of pressure seems to be a clean approach for the modification of the crystal structure of cesium lead iodide, which results in the generating of novel physical properties like band gap modification, as well as improvement in the stability. So we have chosen cesium lead iodide for this work, and we have applied hydrostatic pressure to see the electronic structures as well as structural properties of cesium lead iodide. So there are basically 4 known polymers of cesium lead iodide. So first one is alpha phase. Then this is a tetragonal phase, which is known also as beta phase. And these gamma and delta both are orthorhombic phase. So gamma phase is a 3-dimensional phase, whereas delta phase is 1-dimensional in structure. So this cubic phase is stable at very high temperature, more than 583 Kelvin. Then when we lowers the temperature, then this tetragonal and gamma phase stables at around 510 K and 325 Kelvin. And this orthorhombic delta phase is a room temperature phase. However, it is photoinactive. Photoinactive in the sense that if we shine light, then there is no light activated phenomena for this phase. So in a computational part, we have used our density functional theory within the projected augmented wave method as implemented in Bha's package. We have used PV functional for the exchange correlation energy with a kinetic energy cutoff of 500 electron volt. And Brillouin sampling was performed with K-point mass of 10, 10, 10 for cubic phase, 8, 8, 10 for tetragonal phase, 8, 8, 6 for gamma phase, and 6, 6, 6, 10, 4 for delta phase. And relaxation was done until this force is less than 0.005 electron volt per angstrom in each atomic site. And for phonon calculation, we have employed the phono-P package with energy cutoff of 800 electron volt, along with a convergence of energy up to 10 to the minus 8 electron volt. So first, see the structural properties of cesium lead iodide under the effect of pressure. So when we applied the pressure, then this lattice parameter of a cubic phase then beta phase and delta phase decreases with the increase of pressure. While for this orthorhombic gamma phase, the A side lattice parameter is decreases more as compared to B and C direction. Furthermore, in the B direction, lattice parameter first decreases and then it shows a slight increase with the increase of pressure. So this is because of the tilting of this PB, this octahedra, PBI6 octahedra in the gamma phase. Then we have computed the total energy with respect to pressure, and we can see that with the increase of pressure, as obvious, the total energy increases. Furthermore, we have calculated the energy difference between orthorhombic delta and gamma phase, because our gamma phase is a metastable phase. So from this figure, we can see that as pressure decreases, this energy difference is first decreases, and then about from 1.2 gigapascal of pressure, it increases with the application of pressure. So this indicates that we can preserve the gamma phase by the application of pressure. Then we have investigate the thermodynamical stability of this material with the application of pressure. So we have computed the formation enthalpy by using this formula. So here, this is for the formation enthalpy of cesium lead iodide, and this is for cesium iodide, and this is for lead iodide. So if formation enthalpy is negative, then it is thermodynamically stable, and for a positive SF value, this indicates a thermodynamically unstable phase. So from this figure, we can see that this delta phase is the most thermodynamically stable phase of cesium lead iodide, and at 0 gigapascal of pressure, all the 4 phases shows thermodynamically stable, while this alpha phase shows thermodynamically unstable phases with as pressure increases, and this orthorhombic gamma phase shows thermodynamically stability up to pressure of 1.6 gigapascal, while tetragonal phase shows thermodynamically stable up to 0.8 gigapascal. So then we have moved to the dynamically stability by computing the phonon band structures as well as its density of states. So at 0 gigapascal of pressure, both alpha phase and beta phase shows some negative phonon modes in the Brillouin zone. So this indicates that these two phases are dynamically unstable at 0 gigapascal of pressure. However, this orthorhombic gamma phase shows positive phonon modes. This indicates that orthorhombic gamma phase is dynamically stable phase. Then we have computed the phonon band structures as well as those at 2 gigapascal of pressure. So here also alpha and beta phases shows negative phonon modes, indicating they are dynamically unstability property. While for gamma phase, there still exist positive phonon modes. This indicates that this gamma phase are dynamically stable even at 2 gigapascal of pressure. So we are excluded the orthorhombic delta phase because this phase is photoinactive. So we are excluded delta phase in the calculation. Then we have studied the electronic properties. So here these are the projected band structures of the 3 phases. So for the 3 phases, the conduction band edges is mainly contributed by the lead element, while iodine atom is contributed to the valence band edges for all the 3 phases. This cesium element contributed far from the valence band edges, and this has a very deep band in these three phases. Then we have investigated the spin orbit coupling effect in the cesium layer iodide. By considering the SOC consideration, here we can see that this conduction band edge is shifted downward, more downward as compared to valence band maxima. So this indicates that spin orbit coupling is mainly contributed by the lead atom of the cesium lead iodide. So as we consider the SOC, then band gap decreases because of the downshifting of the conduction band minimum. Then we have computed the projected density of states. So here these results also supported the results of projected band structures. This conduction band minima is mainly contributed by the lead 6p orbitals, and this iodine 5p orbitals is mainly contributed by the valence band maximum, and all the three phases shows a similar kind of nature. So this is the variation of band gap with the application of pressure. So for alpha and beta phase, band gap decreases with the increase of pressure. However, for gamma phase, the variation of band gap with respect to pressure is similar to the variation of lattice parameter in the b-axis. Here, as pressure
Dibya, can you come to your conclusion?
Yes, sir. Within 1 minute, I will come to. So here, as pressure first increases, the band gap increases, and then it slightly increases with the increase of pressure. And for SOC, the band gap decreases with the increase of pressure for alpha and beta phases, and for gamma phase, it increases with the increase of pressure. So in conclusion, we have studied the effect of pressure of cesium lead iodide perovskites by applying hydrostatic pressure in the range of 0 to 2 gigapascal. So within the applied pressure range, both cubic and tetragonal phase showed dynamical instability, while autonomic gamma phase demonstrated dynamical stability. The conduction band edges is mainly contributed by the lead element, while valence band edges are predominantly contributed by the iodine atom. Thank you.
Okay, thank you very much. Any question?
Yes, I have a question.
Yeah.
So when you are using this PB SOC, like technically speaking, when you are using PB, it's a pseudo potential, right? So you are writing as PB plus SOC. So it's a different kind of pseudo potential, or you are integrating it into the calculation itself, like the SOC part.
Yeah, I have just integrated in the calculation.
Okay, thank you. I thought it might be a different pseudo potential, so it's okay.
Yeah, you can use the different kind of pseudo potential for the SOC part because it depends on the calculation tool. For quantum spacer, you can use different kind of pseudo potential.
Okay, thank you.
Okay.
Okay, thank you very much, Dibya. Next speaker is Anupam Setia from IIT Jodhpur. His talk will be synthesis and characterization of halide double peroxide. Anupam, are you here?
Yes, sir, I'm here.
Okay.
Is it visible?
No. Yeah, it's visible. Go for slideshow mode. Okay.
Good morning, everyone. I am Anupam Setia, working under the supervision of Dr. Satyajit Sahu in the of Department of Physics, IIT Jodhpur. In today's conference, I am presenting my topic of synthesis and characterization of halide double perovskite. So these are the contents of my talk, where I have include the introduction, synthesis method, characterization of the material, and their applications. So since we know that halide perovskite material are promising material in the field of optoelectronics devices, so in recent time researchers have done different work on the halide perovskite material, where halide perovskite have the structure with ABX3, where A is the organic inorganic cation, B is a metal cation, and X is halide ion. But there are different problem occurs in case of halide perovskites. Mainly it has a toxicity effect due to the presence of lead element in the halide perovskite, and also their stability in ambient environment. There are degradation of this material, so we have to study about some alternative of this material where we can reduce the toxicity and increase the stability of the material. To overcome this effect, we have used researchers have used different techniques. So we have studied use of halide double perovskite material, where we have replaced the bivalent cation of halide perovskite with a monovalent and trivalent cation, which have the structure A2B-X6, which is called the halide double perovskite structure. The importance of this material is it has a stability more than the halide perovskite material, and also it has some tunable properties where we can adjust the band gap of this material, which increases the optoelectronics properties of this material. And also due to absence of lead element in this material, we can say that it has toxicity level is less as compared to halide perovskite. So there are different studies using double perovskite material. There are different theoretical studies have been done till so far. Based on this, different works have been done using the different method, synthesis method, for the synthesis of double perovskite material. So there are different methods which can be used to synthesize the halide double perovskite material. There are solvothermal method, spin coating method, solution process method, and mechanochemical method, and other hot injection method. In our lab, we have synthesized a double halide perovskite material using a solution process method, when we have mixed the precursor and at particular temperature for some hours in a ambient environment. After some times, after stirring at a particular time, we have get the material double halide perovskite, which we have in synthesized CS2CuBr6. So we can further, for the device application, we can use a spin coated film, and also we can make the powder of this material by adding anti-solvent in the solution. Then after that, after drying of this precipitate, we have get the double perovskite powder material. So after that, we have studied the characterize the material for confirmation of the synthesis of this material. So where we have studied UV visible PL spectra and SAM, EDX, XRD, Raman, and XPS of this material, which confirms the synthesis of this material. For the from the UV visible spectroscopy, we have found a peak at 367 degree and nanometer, 367 nanometer, from where we have found the band gap of this material using tau plot as 2.9 electron volt. Again, from the PL spectroscopy, we have also calculated the band gap, and we have also get almost 2.7 electron volt. band gap of this material. Also, we have studied the FSM of this material. We have this is the FSM images of this material, thin film of this material. We have get some cubic structure of this material, and also we have find the EDX of this material using SEM. Then we have found the atomic percentage of this material almost similar to the original material. Again, also we have studied the characterization using XRD technique, where we have found the peak at this position, where we have confirmed the synthesis of cubic phase of this material. Also from Raman spectroscopy, we have found the vibrational modes of this material at T2 different places, which also confirms the synthesis of this material. Again, from the XPS spectra, we have with different binding energy, we have find the elemental composition of this material. It also confirms the synthesis of this material. So double perovskite material can be used in different applications, solar cell, laser application, photodetector, LED, and also we can use this material in case of memory device application. So we have not gone to the application part. So in future we have studied the application of this material in different field. So in conclusion, we can say that we can use a simple solution process method for the synthesis of double perovskite, and also structural analysis and optical characterization of this material have been done, and this lead-free non-toxic double halide perovskite can be used for different application. Thank you.
Okay, thank you, Anupam. Let us have one quick question.
Okay, sir.
Yeah, anyone? Let's take only one question, no time. Okay, then there are no questions. Then let's move to another talk. This one is from Mousami Narzari, Central Institute of Technology, Kokrajhar, Assam. Our talk will be synthesis of BiVO4 GC3N4 heterojunction for photodegradation of organic pollutants. So Mousami, are you here?
Yes, sir.
Okay, please start.
Is it visible, sir?
Yes, yes.
Yes. Good morning, everyone. My name is Mousami Narzari. Currently, I am pursuing a PhD from CIT Kokrajhar under the supervision of Dr. Manasibuza Borua ma'am. So today I am going to present on the topic synthesis of bismuth benadate and graphite carbon nitride heterojunction for photodegradation of organic pollutants. So this is the outline of my presentation. As we already know, water contamination has become a major problem over the past few years due to the population growth and rapid industrialization. One of the main cause of water contamination is the untreated discharge of wastewater from nearby industries like textile industries, pharma industries, and agricultural sectors. Many industries use high volume of water not only for cleaning but also for numerous other processes involved in the production or manufacturing of the products. In that process, water becomes exposed to chemicals, waste, and other harmful substances. So when this wastewater is released into the nearby water bodies, it restricts the photosynthesis in water and decreases the oxygen dissolution, which is harmful for the aquatic ecosystem as well as for the other living beings. So effective wastewater treatment is required. Photocatalysis is considered as a simple, cost-effective, and environmental-friendly technique for wastewater treatment. It has many other applications such as water splitting, bacterial disinfection, and many more. So the major breakthrough in photocatalysis was in 1972 when Honda and Fukushima reported hydrogen evolution from water using titanium dioxide electrode under UV light irradiation, and their work was published in Nature. After the pioneering work done by Honda and Fukushima, the research in photocatalysis got tremendous attention. Since then, many photocatalysts has been developed. So the basic principle of photocatalysis is when a photocatalyst is irradiated by a light, the electrons in the valence band will get excited to the conduction band. As a result, holes will be created in the valence band. So at this step, there are two possibilities. Either the electron and hole will recombine, or the electrons in the conduction band will take part in a reduction reaction, or the holes in the valence band will take part in the oxidation reaction. So in a photocatalyst, the oxidation and reduction reaction should occur simultaneously. So the problem with a single photocatalyst is that the electrons and holes quickly recombine. So in order to reduce the recombination of electrons and holes, there are various strategies like doping, heterojunction, facet engineering, morphology control. So among them, construction of heterojunction is considered to be an effective strategy for the effective charge carrier separation. So heterojunction is generally defined as the interface between two semiconductors. So for the formation of heterojunction, we have selected two materials, that is bismuth benadate and graphite carbonitride. Both of them are non-toxic visible light active materials. However, the photocatalytic efficiency of both the pure bismuth benadate and graphite carbonitride is low due to the fast recombination of electron hole pairs. So to enhance the efficiency, we have combined these two materials to form a heterojunction. So our objective was to develop bismuth benadate and graphite carbonitride heterojunction, and then study of their structural and optical properties, and then investigation of photocatalytic activity of prepared heterojunction. So methodology, first we have prepared bismuth benadate by hydrothermal method, and then graphite carbonitride was synthesized by urea pyrolysis, and then the bismuth benadate and graphite carbonitride are added in ethanol and then sonicated for 10 minutes, and then magnetically stirred for about 8 hours, and then dried overnight. The results and discussion. So we have done the XRD analysis to know the phase composition of the material. Here we have seen the presence of both the phase of bismuth benadate and graphite carbonitride, which confirms our heterojunction formation. Further, we have done the FSM analysis to know the morphology of the samples. Here, the pure bismuth benadate exhibits ellipsoid-like structure, and pure graphite carbonitride exhibits a sheet-like structure. And for the heterojunction, we have seen the close contact formation between the two materials. Further, we have done the EDX analysis to know the elements present in the samples, and it confirms the heterojunction formation. FTI analysis was also conducted to know the functional groups present in the samples. And then to know the optical properties, we have done the UV visible analysis. Here, for double absorption edge was observed in heterojunction, suggesting the heterojunction formation. Then we have done the PL analysis to know the reduced recombination of electron hole pairs. Here, the emission intensity of heterojunction is lower than graphite carbonitride, which suggests that the minimized recombination of electron hole pairs. Then we have checked the photocatalytic activity of all the samples by degradation of methylene blue dye under visible light, and also for the photocatalytic degradation of Congo red dye was also performed, and the efficiency and the rate constant was calculated by this formula. And here we have observed 89.02% MB degradation and 88% Congo red dye degradation, which is better than both pure and pure bismuth and pure graphite carbonitrate. So this is the comparative table of our work. We reported photocatalysts. Here we have observed slightly better results than other reported literatures. Conclusions: a novel visible light responsive bismuth and graphite carbonitrate was successfully prepared. Then we have confirmed the heterojunction formation by various characterization techniques like XRD, FSM-EDX, FTIR, and UV visible analysis. Then we have also done the PL analysis. And then photocatalytic activity of all sample was examined by degradation of methylene blue and Congo red dye under visible light, which showed the enhanced degradation of both the dyes. Therefore, we can conclude that bismuth and graphite carbonitrate could be a potential photocatalyst for photocatalytic degradation of organic pollutants. So I would like to thank my supervisor and the CIF of IIST Guwahati for various characterization, and I would also like to thank my lab mates for their support, and I am also thankful to Department of Physics, Bhawanipur Anchalik College, Assam, for giving me the opportunity to present my work. These are my references. Thank you.
Okay, thank you, Mosmi.
Thank you.
Any question? Any question from the audience side? Okay, if no questions, then we will move to another talk. It is from Subhankar Saha, Bodoland University, Assam. And his talk will be synthesis and characterization of silver zinc oxide or copper oxide nanocomposite using bark extract of Terminalia arjuna. So Subhankar, are you ready? Subhankar Saha?
He's in the room, but I do not know his name. Subhankar Saha, are you there?
Yeah, I can see his name in the list.
Yeah, exactly. Maybe because of some connectivity issue might be. There might be issue with your microphone, I guess, Subhankar. Yes. Subhankar, can you type in the chat box? Okay, you're here. Okay, I guess you have a problem with your microphone.
Yeah, his microphone is not working.
We have a static in the background. Okay, yeah, that's what. So can you rejoin quickly, Subhankar? There might be issue with some sort of driver issue. Just rejoin once again. Or you can join from your mobile also, then I can share my screen from here. Then let's do one thing, Dr. Rai. Since there's some sort of issue with Shubhankar's end, so let's end this session and we'll shift his presentation to the next one. Because of time constraints.
That's fine. Yeah, that's fine.
Yeah,
So we
okay,
can
let
save
me.
the time.
Okay, 1 minute. I guess Shubhankar is again joining. Let's just check. Shubhankar, are you there? Again, there's a static on your background. We can do one thing, Shubhankar. We'll reschedule your talk to I guess the end of session 2. Okay. We cannot hear you actually. You have some static on your end. Okay. Then okay, just before lunch break, we'll okay. So till then, you can figure out what's the issue with your microphone, or you can opt to some alternative. Okay, then thank you, Dr. Rai,
Thank you very
for
much.
your valuable time, for the magnificent talk. And we hope to invite you sometime to Bhawanipur Anchalik College.
Sure.
Okay.
That will be my pleasure. Yeah.
Thank you so much.
Yeah,
thank you so much,
for your invitations, and all the best for your conference.
Thank you so much, sir. Thank you so much.
Okay, thank you. Have a good day.
Okay, yes, sir. Thank you. You too. Okay, so we have with us Professor Pabitra Nath, sir, from Tezpur University for the session 2 actually. So he will be first talking about he will be first having a plenary session, plenary talk, and then the second session will start. So I'll request a convener, sir, to kindly introduce Professor Nath to the audience. Over to you, sir.
Yeah, sure. So I'd like to have the honor to introduce you with Professor Pabitra Nath from Tezpur University. So Professor Pabitra Nath has obtained the PhD degree from Guwahati University in Physics. He has carried out his postdoctoral study from University of Illinois, USA, from Voices Fellowship Program funded by Ministry of Science and Technology, New Delhi. So far, Professor Nath has more than 50 publications in peer-reviewed journals and 20 publications in conference proceedings. Apart from this, he has patented 5 research works. Moreover, JSPS Invitational Fellowship Program 2022, INSA Bilateral Exchange Program Award, Gandhian Young Technology Innovation Award, Same Tata Endowment Loan, Scholarship, etc. Some of the scholarships and awards that he has achieved. Currently, Professor Nath is serving as a professor and also the head of the Department of Physics at Tezpur University, Assam. So we welcome you, sir.
Thank you. Am I audible to you all? First of all,
yeah, you are audible.
I have shared my screen. Is it visible to all?
It's visible, sir.
Okay. Thank you so much.
1 minute, sir. So I think there's an issue with your webcam.
Is it?
Yeah, now,
okay now?
Yes. It is okay.
Great.
Then put a bit,
Okay, great.
yeah, sure.
Yeah. Okay. Let me go to this presentation slides. All right, and then
maybe you can align your camera a bit. Towards,
is it?
Yeah, it's fine. Yeah, no. Thank you so much, sir. Thank you so
All
much.
right. Okay, thank you so much. First of all, I would like to thank the organizer, especially Mr. Thapa, Vikas Thapa, who invited me to deliver a talk on this occasion. And Bhawanipur Anchalik College actually is very close to my heart because it is a parental loss of my in-laws. So that is how actually I often visit Bhawanipur. I mean, because sometimes I have to travel to that there also. So that way, Bhawanipur Anchalik College, it is just near the highway, right? It is just close by the highway. So it is very close to my heart again. So without further delay, let me start my talk actually. That is about my all smartphone based analytical tool for sensing and imaging applications. So before I start my talk, let me give you a quick glimpse about my, the existing of my parent universities like Tezpur University. This is the bird's eye view of the university. where you can see, the university is spanning over an area of around 255 acres of land. It's a beautiful lush green campus. Equipped with, currently it has 5,000 students currently studying here, and more than 305 faculty members are currently engaged as a full-time faculty here. So we are so these are some of the glimpses of our university campus. That is the main entrance gate, and then you have a very beautiful auditorium, and this is a sports ground of the university, and we have a beautiful guest house, and we have a community hall here. Actually, cultural activities and other activities are often conducted in this community hall. So as far as my research is concerned, over the last 12 years or more than 12 years, we have been working on different areas of photonics, primarily on the smartphone platform sensing and imaging system. And then we also work on the 3D optomechanical system design, because we are using 3D printer for development of different optomechanical setup. And then we are also working towards the development of biomedical instrumentations as a low-cost platform, because we are actually trying to develop alternative instrumentations that can replace the conventional biomedical instrumentations. And also we do some kind of simulation study to in order to calculate the surface plasmon resonance kind of based of work, because we have some collaborated works in recent years where we perform this simulation study on a simulation tool like COMSOL multiphysics software, and there we study those the wave optics. We actually study the enhancement of the electromagnetic field due to coupling of the laser beam on a metal nanoparticles. And the other area is, of course, is very important, is a very emerging area, is a surface enhanced Raman scattering based sensors. But primarily we develop some low cost platform substrate for studying the Raman scattering signal from the samples, which is possible, which can be obtained using the readily available nanostructures. Nanostructured patterns such as Blu-ray, DVD, or paper, and or leaf. Sometimes we are also using naturally available leaf, and from there we also detect the Raman signal from there by depositing nanoparticles on it, of course. So as far as my smartphone-based sensing is concerned, as I mentioned, we work on three different aspects of on phone-based smartphone-based sensing system. One is on a water quality monitoring. So using that, we actually detect different water quality parameters such as fluoride, which I am going to discuss or include in this presentation. Also the turbidity or the pathogens, the bacteria, different bacteria that are present in water samples. And then imaging system, we also develop some macroscopic system using our smartphone device. And the other one is the agricultural soil quality parameter sensors. That means we also perform the soil quality monitoring on a smartphone-based sensing system. Based on our work done, we are already recently have incorporated one company or startup, you can say, popularly we call it startup, and where I engage my wife as one of the CEO, and I also become the director of the company. So this is recently we have incubated at Tezpur University. Its name is labdig.in. You can also visit the site for that. So coming to the societal problem that we are having, right? There are a lot of in many places in Assam and northeastern region as a whole, you will find that our groundwater is often contaminated with different toxic elements such as fluoride, and the people actually living in those areas, they actually consume the water without bothering about the quality. So as a result of this, they often suffer from different diseases such as dental fluorosis, and you can see how the teeth of the person is deformed, and then also there is called another disease that may occur is skeletal fluorosis. So he has a bone deformation or something like that. It is because of the consumption of heavy fluoride content water, and it is prevalent in many parts of Assam and northeastern region. Similarly, during rainy season, we have our groundwaters, our water resources are often contaminated with a lot of pathogens and microbial particles. As a result of which, people during rainy seasons are often affected by gastroenteritis or other cholera, diarrhea and cholera kind of diseases. It is because of the presence of the pathogens, different bacterial species that are present, and people consume those that water sample or the water resources without bothering about the presence of the pathogens. So in order to detect those quality of this water, what you require is a sophisticated instrument, such as one I have shown here. It is called a nephelometer. It is used just to detect the microparticle that is present in water. Okay, how much microparticle is present. So this is the microparticles which I have shown in this glass beaker. Sorry, I should go back. So in this glass beakers, they are containing different microparticles, and depending on the concentrations, the color is gradually changed. So here in the nephelometer, what you require, it actually detect the light scattering from these water samples, and depending on the amount of light scattered from the sample, it will give you a proportionate kind of signal which can be correlated with the concentration of the microbial particle. Similarly, the bacterial sample, which is present, or pathogens that are present in water samples, what you require is a OD600. It is a very sophisticated instrument, also available in the biological laboratory or material science laboratory, to detect the amount of pathogens present. Actually, the pathogens are grown in a cultivating medium, and once it is growing gradually, their intensity, or you can call that the density per volume, will be increasing, and which can be correlated with the light scattering, which will be detected by this OD600 instrument, and that way you can correlate that my actually sample is contaminated, or it has some pathological sample, because the bacterial samples grow with time, and which can be correlated with the light scattering, light signal, which will be recorded by this OD600. So this is how we conventionally use this instrument. These are actually expensive. For example, this nephelometer is more than 1 to 2.5 lakhs or something like that, and this OD600 is, again, I have checked with the laboratory, it is again more than 2 lakhs or something like that. With sophisticated instrument, the person has to be very skilled. A layman cannot handle this instrument, because he has to have some training, some kind of training, then only he can operate this instrument. Sorry. So the another problem that we are having in our northeastern problem is that during rainy season, people are often infected with the malaria, right? So and then you can see this picture, in Indian map, you can see that the Assam is highly prevalent of malarial diseases. So during rainy season, we have this density of malaria per million is be like 74,000 to 249,000, something like that, it is one of the most prevalent disease in India. I know Assam is among one of the most prevalent disease of malaria in entire nations. So what you require essentially to detect the malaria is a microscope. Again, since the microscope is relatively expensive, and it also needs some technical person to operate it, so therefore, even though the person is infected with the malaria, due to lack of availability of microscope in remote areas, they cannot perform the diagnosis. So it is that these are some of the hindrances in our region, due to its location, you can say, or the other thing. So people are often they are not being able to be diagnosed in proper time, although it is needed essentially. So what we are doing, we are looking for an alternative platform to develop such sensing and imaging, development of a smart for development of a different analytical tool or imaging system. So let me give you a brief idea about the smartphone. It was first demonstrated in 1973 by Martin Cooper from Motorola Company. It was the first mobile handset demonstrated by Martin Cooper in 19. As you can see, the size of the phone is something like the size of a brick, and it is like several pounds. Now today the dimension of the phone has reduced, and you can it is weighing between like 105 to 150 gram or something like that. And see the growth of the technology. This one of the most penetrating technology in the mankind is the mobile phone technology, as far as the recent technological penetration is concerned. So the world, if it is growing, if you can see in this map, in the world, it is growing at the pace of 30 between 15 to 30. You can approximately like 22.5 But in the less developed countries, the growth is tremendous. You can see it is approximately 55 or something like that. It means that in the least development countries, you can count like Bangladesh, Sri Lanka, or the African countries, the growth of this technology is immense compared to the developed nations, because it is as I mentioned, that it is considered to be one of the most penetrating technology in the world so far. So as far as the smartphone is concerned, so we all know that the smartphone is actually equipped with so many gadgets, sensors. It has an accelerometer, it has a gyroscope, a magnetometer, front and rear camera sensors, near field communication sensors, then barometers, and I mean what not. Actually, it has a lot of sensing element embedded on it. So an user, apart from communicating to another one, but he can use those sensors for development of different sensing and imaging system. So in addition, one can also use these readily available optical components and convert the smartphone into a very useful analytical system. It can be your spectrometer, it can be your colorimetric sensor, it can be your microscope and whatnot. And on top of it, there are a lot of user-friendly applications, or you can say the operating systems, such as from Android and Mac or iOS, or we also have a Microsoft. They are also providing that operating system, and makes the smartphone a really user-friendly system. So along with this, one can also use some of the available platform where he or she can develop applications, which is a custom design application. Of course, these applications is something like it's like a block codes. You can combine your assembling the block codes, and you can develop your own custom design applications, such as one which I am displaying here. One such applications we have developed during one of my research students, and using these applications, he could detect the water qualities. I will come to it once again. So these are the custom design applications that one can develop using this platform, such as I mentioned here. It is an MIT App Inventor, and this is free. You don't require any money to pay to learn these applications. Just go to MIT App Inventor. You can choose your block codes and learn the basics of it, and assemble the block in a certain sequential way, and then you're done with your applications. So this is how we have done. These are some of the block codes we have during the development of the applications. So once you are assembling it in a certain fashion, then you are done with your applications, and this application is ready, and you can perform your enabling your sensor of the phone to do certain specific kind of sensing studies. So this is how we can use custom design applications for to make our sensor a really user-friendly device. So what you have essentially in your hand, both the power of a hardware. That means the power of the hardware means the different sensing element of the smartphone, which may be your camera, which may be your the front ALS sensor, or maybe your rear camera or the front camera. Also, you can use your audio jack. This could be your the hardware component, and also at the same time you have a software on the phone itself. And therefore, you can use both the hardware and software part of the phone and convert it into a really a user-friendly device or user-friendly sensing element. So this is one of the pictorial representations using which actually we have detected fluoride, iron, and phosphate in our lab. And these are some of the technique we have used. Some of the techniques we have used, standard technique, which is actually readily available. These are established technique. You don't have to worry. What I am doing basically, we are developing our own sensing setup, and we can perform the sensor, and we compare the result with the standard analytical tool which is available in the laboratory. So this is one of such work that we have conducted a few years back in my lab. So here we estimated the fluoride level in drinking water. So here again the standard protocols are available in the literature. So what we simply followed that protocol, which is a very established protocol, and this protocol name is called APHA, APHA method 4500. So actually this if your water sample is containing fluoride, So the color of the reagent is gradually bleaches. That means it is gradually become faint, and that can be detected on a smartphone platform. So this is the just a simple protocol we are using for detection of fluoride, with our smartphone device. So this is the color of the sample at different concentration of the fluoride, from 0 to all the way from 0.1 milligram per liter. And you can see, if I perform the spectrometric analysis, you can see this absorption had changed a little bit, which is a distinguishable data I can extract from the spectrometric analysis. Using these samples, now I design using this particular information in hand. That means this distinguishing result, or you can say that it yields the discriminating results at 570 nanometers. So what I do, actually, we are using a filter at the in front of the sensor at 680 nanometers. So we are using this schematic. I mean, this is the prototype actually, and this is the schematic representation of the setup that we have developed in the lab. So we are using the flash lamp of the smartphone, which is a white LED, of course, and in front of the flash LED, we are using 680 nanometer, 568 nanometer optical filter, so that only 568 nanometer signal is passing through this optical fiber, and then it is we are collimating the signal using a planar-convex lens, and then we allow it to pass through the cuvette. Simple absorption based sensor we are developing on a smartphone. See how simple it is to look at it. So and this is our sample holder, and you have a lens so that the transmitted modulated signal is coupled to the ALS of the phone, and you can detect the change in the modulated signals using this from this by intensity of the signal recorded by the ALS. ALS is nothing but the ambient light sensor, which is sensitive to the intensity of the light. So these are our preliminary data with different concentration of fluoride level present in the sample. So we started from 0 to 2 mg per liter, and we have observed that we have found that it is almost linearly varying with a regression analysis showing that it is 0.98321, which is quite linear, indicating that this is a quite linear linear response to the change in concentration of the fluoride in the sample. And then we have chosen two different smartphones. One is your Asus to validate that my setup or the protocol that or the sensing setup that I'm using is working fine with a specific phone. So we have used two different phones. I think we conducted this experiment few years back. So at that time we had a Moto Z in our lab, and that Asus Gen phone. I think this phone is no more in the market nowadays. But anyways, we used two different phones and observed the change in the response of the sensor. We found that in both situations they show the same some kind of linearity response. But the degree, or you can say their inclination or the sensitivity is different for different phones. It is obvious because the camera which is equipped in the different phone, or which is embedded in the different smartphone, they are having different features, and therefore their sensitivity will act differently with the sensing response. So after that, we perform we compare the data with our spectrophotometer, our laboratory gas spectrophotometer, and our smartphone fluoride-based sensor, which we have developed in the lab. And we found that in all the situations, we collected water sample from different parts, such as 6 Mile Guwahati, then Kasarigao, then Birkuchi, Dengao, and different places of Assam. And we compared the data. And in each cases, we found that the results are really, it is very comparable. So in both the situations, they yield a similar kind of sensing data. So it suggests that the sensor which we have developed on a smartphone platform is very reliable, and it can be useful for similar purpose, for detection of similar. And the applications, as I mentioned at the beginning, that the applications which I have developed on MIT Inventor is called the F-Sense, which is showing here. So this F-Sense has a feature that if suppose a layman is handling my setup, so if suppose he finds that his sample is containing more than the permissible limit of fluoride, so immediately it will show you the red cross, crossing, it is a danger. So it will indicate that you should not take this water. And the same the information can be stored using the same applications, or it can be shared to the central laboratory water quality monitoring setup. These features can be integrated. There is no problem with that. And similarly, you can also map the data of a specific locations. So these are some of the features which you can incorporate in your applications. These are very flexible, and one can develop applications according to his requirement of the of his sensor. So in the next part, what we have done, we measure the turbidity. And as I mentioned that during rainy seasons, our water bodies are often contaminated with different microbial samples, such as different slate particles may be incorporated, maybe there, or pathogens are there. So because of that, your water bodies or water resources becomes turbid. Turbid means it contains a lot of microbial particles. So more is the number of particles, this which can be actually this turbid medium can be detected. One of the best way to detect this turbid medium is by light scattering principle, right? So there are two ways to detect or correlate the light turbid medium with the concentration of the turbid medium. Is that you can perform that forward scattering, which is transmitted signal is recorded by detector, or you can detect in the at right angles to the incoming light directions. So it's called a side scattering. So if you consider the scattered light signal intensity at a right angle to the incoming light signal, in this case, intensity of the scattered signal will purely depend on the concentration of the turbid medium. That means our goal is to detect how many particles are present per unit volume in the liquid medium, and that can be obtained, or that can be assessed by recording the scattered signal at right angles to the incoming light signal. So this is my light source. So I'm going to detect the light signal intensity in this direction, so at a 90 degree. So based on this principle, we developed another smartphone-based light scattering device. So this is our this is the layout of the schematic layout of the device. So here we are illuminating the infrared light source, and it is allowed to pass for the sample, and the scattered signal is recorded by the ALS ambient light sensor. And this is actually when the phone is in the horizontal directions. Now this is the prototype which we have developed in the lab, and you can see the person can handle the whole setup on his palm. So it is very, very lightweight, you can say, and it can be handy or portable. So this is the setup which we have developed in our lab, and this is the top this is the top panel of the whole setup. So this is my sample. The light signal is here, LED. So light signal is here, and scattered signal is recorded by the phone itself. So this is how we have developed a very compact setup to record the turbidity in the medium. To analyze this setup, what we have done first is that we synthesize different standard turbid medium, and these are nothing but a formaging sample. Actually, usually it is a standard turbid medium which can be synthesized in the laboratory, and these are different as indicated here in the 40 NTU, 80 NTU. These are the standard way or unit of turbidity, level of turbidity 40 NTU. That means we have doubling you can say that we have increased the turbidity level by 40 maybe. So this is how we have seen, we can see the turbidity level how it's increased. So also we have taken another level of concentrations, and like from 0 to 0.1, something like this, 0 to 1, and from 1 to 10. That means we have considered different range of turbidity medium, and we have seen the response with our smartphone device, with our smartphone sensor, or with our design smartphone sensor. And all the range of concentrations from 0 to 1, and then from 1 to 10, and from 40 to 400, in all the situation we found almost similar linearity of range of response. So this suggests that our sensor is very, very useful to assess the turbidity level in a medium from a very low turbidity level, or you can say from low concentrations to all the way up to 400. Of course, the range or the response range you should consider a kind of a reasonable response range. Suppose if I consider from 0 to 1, if I consider all the way from 0 to 40, you may not be able to see a very linear, because in this case, you are considering a very wide range of turbidity medium, and therefore you will have some kind of saturation or kind of plateau you can encounter at a very high concentration range. So in order to have a linearity response, you have to consider different range of turbidity level, like 0 to 1, as I have mentioned, and from 1 to 10 at a increment of 1 or something like that. So different scale you can consider for that. And this is the sensitivity and the resolutions which we have evaluated for our design sensors. And then we compare the data of the different field collected water samples from different areas, and then we compare with the nephelometer, the standard nephelometer, which I have shown at the beginning of my presentations. And we found that the data are almost comparable, suggesting that my device is equally good, or if not perfect, or if not accurate, but it is comparable, or it is like a comparable data compared to your laboratory nephelometer or turbidity meter. And therefore we can conclude that this sensor or the analytical system can be used in a laboratory for measurement or for assessment of turbidity in the lab, in the water. Again, the same setup can be used also for growth of bacteria in the laboratory environment. As you know that in different bacterial samples, if you culture them in a laboratory environment, it will grow at a certain pace, right? And after that, it will take a plateau. I mean, this is those who are working in the biology or biological laboratory, they can understand it better. That for that, what you require is a OD600 instrument. I mean, you have to monitor the growth of the bacteria at a certain interval of time. So we have also utilized the same principle. I mean, we also record this setup we have utilized for recording of the growth of the bacteria. So this is what we have used for recording the growth of the bacteria in the laboratory environment. Here, this bacterial sample is cultured bacterial samples are placed in the setup, and you are using this incident laser source, light source, and the scattered signals are being recorded by ALS of the phone. So this is the prototype which we have developed in the laboratory, and we record the data. So this is how we have estimated the growth of bacteria at a certain regular period of time. It is in hours. And you can see that we compare the data with our the regular OD600 meter instrument. So one can see the different phases of bacterial growth, which is actually conventionally we can record these different phases of bacterial growth, such as lag phase, log phase, and stationary phase with our OD600. And also it can be recorded by our standard smartphone-based sensor or smartphone-based bacterial growth instrument. So this data shows that it is actually varying in a similar fashion as your OD600. This again suggests that our device can be useful for recording or for monitoring of growth of bacteria in a laboratory environment. So this is different these we are recording, and this E. coli. These are two different bacterial sample, and in each cases we found that it is varying almost similar in a similar fashion as that of the as that of your standard OD600. Again, in order to further confirm that whether how good or how reliable is my instrument is, so what we did actually, we diluted the sample by 50% every time. So from suppose I have taken a concentration of 1 mg per liter, then I have diluted it by up to 0.5 mg, and then I diluted further by 50%, and show and observe how much intensity is decreased in each cases. For different, we've observed that for all the bacterial sample, which we have considered in a laboratory, if we diluted by 50%, the signal intensity equally dropped by almost 50%. It can be seen in this graph. This is showing, this is a signal data which we have recorded with our smartphone and sensor or with our smartphone device. So it again confirmed that this sensor can be useful for monitoring the growth of bacteria or monitoring the growth kinetics of bacteria reliably, and it is performing as good as your OD600 meters. So in the last part of my discussion, in the last parts of my presentations, I would like to discuss about the smartphone which we have developed as a part of our research activities. So this is another 3D printed setup which we have developed. here what we have done, we incorporated some small commercially available lenses. This is a ball lens and a planar convex lens, and this is a 3D printed device, and 3D printed device, and we have a sample stage here. You can introduce the sample stage. So this is the stage for that, and you can convert your phone into a very useful very useful compound microscope, which has optical magnification of approximately 520 optical zoom, which is sufficient enough to see the blood sample. So this is the blood sample which we have collected with this setup. So this is the prototype which we have done. It looks to be a little complicated, but in the recent work we have simplified the system and we have improved it significantly. Anyways, this is one of our work which we have done a couple of years back. So this is what we have collected. This is the blood samples which are required. Again, as I said, that a smartphone has a feature that you can incorporate your applications. Applications mean we have developed some image processing applications which can be stored in the cloud, right? These applications can be stored in the cloud, and so that you can once you capture the images, you can send it to the cloud. In the cloud, the image will be processed. So this is the first with our applications, it is first cropped the image. See, this section has been cropped, and in the cloud they will compute the image, and you can see a better image which we have computed in the cloud. So this is what we have very recently, I think a few years back, we have proposed, and see the performance of the blood samples and see the imaging performance, which we have compared with our standard JACE microscope, which is like it will cost you like 3 lakhs, and our system is costing like 25,000 or so, including the smartphone also. So behaving their performance wise, they are at par. But here we are using the features, or here we are using the features of both the hardware and the software and the cloud facilities of the computer, of the smartphone. So utilizing those features, we can improve, or we can enhance. One can enhance the imaging quality of the microscope, and your performance are similar as your standard microscopic setup, a standard microscope. So this is the performance which we have compared with our blood sample recorded in the laboratory. So this is one microscope which we have designed. It's a simple bright field microscope, and its optical zoom is around 520. It seems to be a little complicated, but nevertheless, we are getting a very crisp and enhanced imaging using this setup. Then the next part, what we have done, we develop a multimodal microscopic system. Here, this setup is very compact. Here we are using an optoelectronic devices, which is nothing but an OLED panel. And this OLED panel, the feature of the OLED panel is that one can generate different imaging, different patterns, such as this white circle, then black circle, something like this, and the blue ring covered by black background, so and so forth. This different pattern of the OLED is very important to use it both as a spatial, as an optical source, and at the same time as a spatial modulator. And this spatial modulator, actually spatial light source, is required to generate different imaging modalities. So this OLED panel, the display panel of the OLED can be controlled again from the smartphone using certain programming ports. So which we can do with a Arduino microcontroller we are using to control the display panel of OLED, and therefore we can generate different imaging patterns. So this is the schematic representation of the whole setup, and one can see this is the bright field imaging of, suppose, potato starch cells. This is the dark field imaging. This is just a pictorial presentation, so I will come to it one by one. So this is what we have developed, and of course we got a patent on it. This is the patent number. I think already the patent has been granted last month in the month of March this year, and the work has been published I think 2 years back in 2022. Anyway, this is our setup which we have developed in the laboratory, and if one can see the fluorescence imaging also can be obtained on the same setup. So these are the different the display pattern one can generate on an OLED or OLED panels. So as I mentioned, that The purpose of generating different display pattern is to obtain different modes of imaging, such as bright field, dark field, fluorescence, and so on. So this is the imaging the standard micropixels of 5 microns, which is commercially available, and this can be imaged with our smartphone microscopic setup, something like this. And this is under bright dark field mode, and this is under fluorescence mode, imaging, and which has been captured by our smartphone. So these are again different biological samples, which this is called human epithelial chick cells. These bright field imaging are actually, because their optical properties, these cells are optically translucent, therefore it cannot be captured in a bright field mode. But if you capture them in the dark field mode, you can see the morphology of the cell. But it can be seen even better. The morphology of the cell can be seen in better for when you perform the differential phase contrast, which also can be performed on our setup. And this is, of course, the fluorescence-based imaging, which can also be performed on the same setup. Therefore, we can say that this is our design system is perfectly standalone. One has to just switch from one mode. I mean, the pattern of the source. If a user switch it from one pattern of display to the other pattern, he can immediately get the bright to the dark. He can switch from the bright to the dark, or dark to the DPC, or DPC to the fluorescence, and something like that. So this is again the polarizing microscopic images. Again, can be done on the same setup. Of course, here what you need is a polarizer, and it can be introduced in the setup itself. So this is the oblique illuminations and Reinberg illuminations. I mean, this is a color stain kind of imaging pattern, sometimes required in the biological and food engineering. For analysis of different bacterial samples in the food engineering. So this is again the Reinberg modes of imaging, and these are the oblique illuminations, something mode of imaging of the same cell. So this is all about our work. You can also visit my our website, or our laboratory site for to know more about our detailed activities, our research activities. Finally, I would like to thank you all for your patience hearing, and I would like to take questions if you have any. Thank you so much.
Yes, thank you so much, sir, for your nice and very informative presentation. I'm sure the participants are benefited or inspired from your innovative and developed ideas.
Thank you so much.
So, yeah, so it is open for discussion or any kind of interaction from the participant side.
Good morning, sir. I have a question.
Yes, please.
Sir, when you are saying that you will be transferring the images to the cloud for computation,
yes.
What kind of computation would that be? Like, have you developed some specific codes for the computation, or are you using some neural networks or?
No, not we are not using any neural networks. So we actually in the cloud, if you perform the MATLAB code, because these are the image processing code, right? I'm basically enhancing the quality of the image, right? All you need, suppose you first capture the raw image of the from with your setup, and then you can perform this computation in the cloud by cropping the image, and then you send it to the cloud for computations. Because if you perform it in the phone itself, it is also possible to do the computation in the phone. But our ordinary people, they don't use a high-end smartphone, right? They don't they don't use very high-end smartphone. Therefore, the processor speed is very moderate. And if you keep on computing your image, so eventually your phone will be very slow, right? And maybe you will not get, it will take a much longer time to get a better image. So better to transfer it to the cloud and then do the computation and get back the crisp images for your work. That's the idea.
Okay, sir. And regarding the sensors that you have developed, are you planning to make it commercially available?
Of course. As I said at the beginning, that we already have incorporated one company, right? So this is about a lab dig. So we already raised money for that. We already got two grant from BIRAC and another from Numoligo Refinery Limited, NRL, and where they have funded us to take it to the commercial level. it is underway actually. We have already, I think we got a grant from 3 different funding agencies, also from startup or any DP or something like that. Anyways, but we are trying to take it to the product level. It will come maybe by mid of next year or something like that. Yes.
Okay, sir. And I have one last question, not regarding directly to your work, but you have mentioned about using COMSOL multiphysics at the starting of your talk today.
Yes.
So actually, I am also planning to use COMSOL multiphysics in some of my work. So if in future I have any doubt, then is it possible to contact you later on? Or
Of course, anytime. I mean, I'm open to collaborate with anybody anytime. You know, this is the era of collaborations, right? You cannot make your research compartmental, or you cannot be isolated. You have to collaborate. Anytime you're welcome to my lab anytime. No
okay,
issues
sir.
there.
Thank you, sir.
Welcome.
Excuse me, sir.
Yes.
Hello, sir. Am I audible?
Yes, yeah, perfectly. Yeah, you're audible.
Sir, can we set the polarization like circular polarization, elliptical polarization, or something like that on our biological samples for using the smartphone-based microscope?
Actually, I am not much worried about the circular or you said the circular polarization, right? I'm sorry.
Yes, sir.
Can
Yes,
you
sir.
repeat that? So you are using, you mean to say that you are using some circular polarizations, or what polarization you mentioned about that?
Sir, some kind of biological samples that the cell of the biological sample, or it's like the surface of the biological sample, shows some kind of circular polarization and some kind of elliptical polarization, and sometimes maybe the linear polarization. Can we distinguish using that microscope?
That's actually our purpose is to introduce 2 polarizer. Okay, I mean the idea is that suppose your potato cells, or they're basically, because of their crystallinity in nature, they exhibit some color variations, right? Crystallinity,
Yes,
you know,
sir.
and similarly some crystals also, they, you know, under polarizing microscope you can see the you know, the crystalline material, they exhibit different color pattern, right? So
Yes, sir.
what actually in a polarizing microscope it does, you know, it has 2 polarizer in it. Okay, so
Yes, sir.
one polarizer will actually, you know, there will be one polarizer just after the sample, or maybe before the sample, and then another will be there just before the IPS, something like that. And you keep on
Yes, sir.
rotating you keep on rotating the polarizer near to your eyepiece.
Yes,
So
sir.
that way, once you see that change in color, so basically what we do, we are using 2 polarizer, while
Yes, sir.
one has been used as has been used for polarizing the light signal, and another has been used for checking, I mean, the crystallinity or the structure of the material. So this is how we do. Actually, we are mimicking how a polarizing microscope work. So we are not bothering about the circular polarization of the, you know, your sample. We are not bothering about the other electrical polarization of the sample.
Okay, sir.
That is our goal is to whether our microscope, the design microscope is performing similar to your the conventional polarizing microscope or not. We just
Okay,
compare the data, and that is how we are doing in our, you know, work. Yes.
okay, sir. That means my question is that if the like your smartphone-based microscope work like the real microscope, can we analyze some kind of sample using that microscope? That was my
Yes, you
my
can.
yes, sir.
Of course, you can. Yes, I think I have seen you. I have shown you some data, right? I mean, I think this here in the slide, perhaps you have seen the potato starch cell sample. I
Yes,
think,
sir.
yeah. So those are the samples which you have captured on our smartphone, and the similar sample, perhaps. I think I should have incorporated the comparable data on the standard polarizing microscope, but
Yes, sir.
this polarizing microscope is not in our laboratory. That's why I skipped that part. But anyway, you can compare, you know, you can consider any potato cell, check it in your observe it in your polarizing microscope, under my polarizing microscope, and see, you will see almost a similar kind of pattern that what I have shown in my presentations.
Okay, sir. Thank you, sir.
Okay, welcome.
So, any other questions? So, I have a question from my side.
Okay, no, yes, please.
when you talk about the optical filter of your sensor,
Okay.
you mentioned that you have used the 568 nanometer optical
Nanometer.
filter.
Okay.
Why
Yes,
this
yes.
particular number?
Oh, yes, very good. I appreciate your questions. See the spectrometric data. I mean, I think I have shown you, that in the sample that which we have synthesized in the laboratory, which is the standard protocol, of course, that alpha method. So you have seen that those particular samples shows the highest absorption at 570 nanometer, right? 570. I think I have shown you the spectrometric data. I think if you
Yes,
so I think we didn't get the 570 exact filter, but 568 nanometer filter was available commercially at that time only. So we procured the 568. So doesn't matter, even if it is 568 or 570. So it is very close to that point. So that matching value. So we are using that 568 nanometer, where the absorption of the sample is showing a distinctive kind of values, right? So perhaps the spectrometric data shows the highest absorption at 560 or 568 or 570 nanometers. And therefore, if I use a light source that emits 568 nanometers, then my absorption will be very high. And that can be useful in the present work or for development of the sensor work. That is the idea, actually. You can use other wavelength, but you may not obtain the you may not be able to get the discriminated, or you can call distinguishing data.
Okay, thank you, sir. Thank you so much.
No.
So thank you so much for your presentation, and so I'd also like to request you to chair the session number 2. And
Okay, thank you.
I believe the schedule is also with you right now.
Yes, I do have.
Yeah.
Can I switch off the video and the mic as well? Or
Okay. Yes,
yeah.
yes, sir. So it's over to you, sir.
Okay, thank you.
Excuse me, sir. So I have a small announcement. So, the second speaker, like Atanu Betal, so his talk is rescheduled to, I think, around 3:10 p.m. So I think in his place, Subhankar Shaha will speak. Okay. So the first will be by Abhinav Goswami from NIT Manipur, followed by Subhankar Shaha from Borden University. That is the minor change in the schedule.
Okay.
Over to you, sir.
So now Subhankar will be presenting.
Now Abhinav will be speaking. Then after that, Subhankar. Yeah.
Okay. So Abhinav Goswami, right?
Yes.
Okay. So duration is for 10 minutes, I believe, right?
Yes. It is 8 plus 2 minutes. Yes.
Okay.
Yes, sir.
Thank you so much.
Thank you, sir.
Hello, Abhinav, are you there? Yes.
Yes, sir. I have already shared my screen. I hope I am audible and visible.
Yes, you are. Please.
Okay. My name is Abhinav Goswami, and I am a research scholar at Department of Physics, NIT Manipur, under the supervision of Dr. Ibetombi Soibam. My today's presentation topic is the study on the dependence of magnetization with applied field for microwave sintered cobalt ferrite nanomaterials using the law of approach to saturation. Okay, so this is the outline of my presentation today. So we'll begin with the quick introduction to my sample. I am using cobalt ferrite nanomaterials here, and it is basically a mixed phenyl structure. Here you can see the parenthesis here indicates the A side of the sample, and the square bracket here indicates the B side, that is the octahedral and tetrahedral and octahedral sides respectively. And the X here, it depends on the thermal history as well as the preparation condition. So given the preparation technique and the heat treatment given to the sample, this X value may change. So there is not a fixed cationic distribution for this particular kind of materials, that is the mixed phenyl materials, and that depends on how the system or the samples are being synthesized. And that is also an advantage for the system because as it has many promising applications, so if we can tune those particular properties in one particular area, then it can be useful for many different kind of promising applications. Say, for example, if we somehow tune it in a way that the coercivity of the samples tend to be lower, plus it is a magnetic sample, so it can be used for applications like hyperthermia, and other biomedical applications. So let's go to the sample preparation technique. So I have used a wet precursor, citric precursor method, also known as the autocombustion method, where in this case the precursors, the iron nitrate, cobalt nitrate, and citric acid were added into a distilled water to make a solution. The solution was then stirred at 40 degrees Celsius continuously, and ammonia was added to the solution to bring the solution to a certain pH level. After this process, it turns out to be a black solution, which was given a heat treatment at 100 degrees Celsius, which turns it to a black gel. Subsequently, it turns into ash, which was then again calcined at 600 degrees Celsius for 30 minutes, giving us the calcined powders. And the calcined powders were then sintered at 700 degrees Celsius for 3 different sintering time, that is 2 hours, 4 hours, and 6 hours. In this presentation, we will be representing them as I1, I2, and I3 respectively. So let's look into the XRD spectra. So this is the XRD spectra, and we have calculated the average crystallite size and the lattice constant of the sample here. And it also shows the pure phase formation of the sample. In looking into the crystallite size here, we have seen that it reduces from I1 to I2, and then again it increases for I3. So this particular structural parameter would be useful while explaining certain other things later on. So let's come to the last one, the topic of discussion today, that is the law of approach to saturation for the magnetization. So let's go into some introduction of this. This is basically a fitting the certain equations into the magnetic data that we have received from VSM analysis, that is the MH loop. We take the Virgin curve of the loop and try to see which equation fits into the saturation level of the data that we have received experimentally. In this particular equation, equation number 1, let's look into it as an example and see that here the independent variables are the H, that is the fill, and the dependent variables are M, and there are certain parameters here like the parameter A, B, and C. So A by H term, it generally attributes to the structural defect, even though it may be attributed to certain other things. It's a little bit vague in explaining this part of the parameter, but the B term here is really important. In most of the studied cases, the B term is represented with the magnetocrystalline anisotropy, and this relation here, it represents how it is related directly to the effective anisotropy, which in turn is in terms of the magnetocrystalline anisotropy. And the CH term, it's also referred as the paramagnetic term or paramagnetism term, but it gives us the intrinsic magnetic properties of any particular samples. It can be related to the intrinsic magnetic properties of the sample. So that was equation 1. Let's look into these other 3 equations here, equation 2, 3, and 4. So in this particular study, I tried to fit all these 4 equations and try to find out which equation was best fitted for my particular case of sample. There has been more than 15 equations for this law of approach to saturation that are reported in various papers. So in this particular case, I am using only 4 of them. And in order to find the best fitting equation, at first we have to find the best fitting range. So the VSM analysis was done from minus 15,000 ostrate to plus 15,000 ostrate. And since we are taking only the Virgin curve here, we have to take up a section of the data which is closer to the saturation level. So in order to find that section of data, we first started with the fill range between 2,000 to 15,000, then 3,000 to 15,000, then 4,000 to 15,000. As you can see, the level of fitting done by all these 4 equations are a little bit different, and the closest one comes to this one, but still we cannot decide directly by looking at the graph. So these are the goodness parameters that we have analyzed from the fitting there. So these are for all the 3 fill ranges, and here, among the apart from the chi-square and r-square, this M by ms value, it dictates the ratio between the highest level of saturation to the lowest level of saturation that is given in any of these plots here. So the closer it gets to 1, the better is the result. So in this case, the fill range between 4,000 to the 15,000 ostrate, it gives us a very good goodness parameter as well as the M by ms results. So in this particular table, we are using the equation number 1 to show the parameters. Now, since we have selected the fill range here, let's try selecting the equation. So the same thing was done for the equation also. All the equations as well as for the fields, everything has been included within these three plots, figure 2, 3, and 4. So the goodness parameters here are as follows, and from looking at the goodness parameters, we can see that the equation number 1, that is this one, this shows pretty good chi-square as well as the r-square value, and the range that we have selected here is all 4,000 plus up to 15,000. So these are the plots for the base fitting equation as well as the base fitting field range for each of the samples. This is for I1, this is for I2, and this is for I3. So it fits pretty much properly here, and after the fitting, these are the parameters. This is the table that lists all the parameters. So we'll start with the things that we get from the VSM, the saturation magnetization, the coercivity. This is the M by MS value. This is the saturation magnetization that we get after the fitting. And these three are the parameters from the equation itself, the parameter A, B, and C. And from the earlier equation, the earlier relation, I showed that the effective anisotropy can be related to the parameter B. So I have calculated the effective anisotropy from the parameter B. Even though the correlation can be done directly from the parameter B, it would be helpful if we calculate this parameter here. So here we can see that, let's talk about just the B and the C parameter. The C parameter here, it's interesting because the way it is changing is in accordance with the way how the average crystallite size of the sample were changing. So first it is decreasing, and then it increases even higher than the first one. And for the B here, it goes in trend with the saturation magnetization that we have observed. And the saturation magnetization that is being observed from the fitting itself is pretty much close to the one that we have observed from the VSM results. And let's look into the explanation now. Pretty much discussion, because the parameter C that we have attributed to following the trend of that of the crystallite size, it is technically mostly reported that this parameter C, it is influenced by the intrinsic magnetic properties of any sample, and given the size or the shape of the sample itself, the domains might be affected by the way it changes or the way it interact with the magnetic field itself. So that might be a reason why this C is directly related to the structural parameter or the crystallite size that we have seen. And coming to the K effective, that is the B parameter there, this is a relation that can define the effective K, and it is also related to this EMC, that is the magnetocrystalline anisotropy. Given the sample, if the shape is pretty much constant, then we can ignore these things as reported from this article there. And the surface, it depends on how the structure, it depends on the structure analysis or the FSM or SEM images, which we have not done here. So, but we can at least say that the magnetocrystalline anisotropy is a major factor contributing to this K effective. And the way this K effective,
your time is up. I mean, you should cover.
Yes, this is the last page anyway.
Okay.
Okay. So we can say that the increase in the MS, it outweighs the increase of the K effective in contributing to the HC here. So as we can see, the HC is decreasing, whereas the saturation and this one is increasing. So in conclusion, we can say that the crystallite size that we have observed from the XRD, it correlates to a parameter C, and the another parameter B that we find from the base fitting graph, and this is the base fitting equation here, can be also correlated to the saturation magnetization, as well as somehow we can correlate it to the coercivity of the sample. And that is the conclusion for this work. And these are some of the references that I have used for this work here. And thank you very much.
Thank you, Abhinav, for your presentations. Now, session is open for 1 or 2 short questions, quick questions. Anybody? So if not, let us thank the speaker, or let us thank Abhinav.
Yes, sir. Thank you, sir.
Yeah, let us now. Next is I think Subhankar is there, right? I think he's in the line.
Sir, am I audible?
Yes, you're
Subhankar,
audible,
yes.
Subhankar, yes.
Subhankar, you're-
Okay, thank you.
please start your presentation.
Is my screen visible, sir?
Yes, yes. Go to presentation mode and start. Yeah.
Good afternoon, one and all. Myself, Shubhankar Saha, Research Scholar, Department of Physics. This is the title of today's talk: Synthesis and Characterization of Silver, Zinc Oxide, Copper Oxide Nanocomposite using Bark Extract of Terminal Ozone. Basically, green synthesis is a synthesis process where we use plant extract and microorganism such as bacteria and fungus. It is a bottom-up approach. In all part of the plant, some phytochemicals are present, which is act as a reducing and stabilizing.
Shubhankar,
Yeah, I think
your screen is froze actually. I'm sorry to interrupt.
Yes,
Actually, you need to, I think, share the entire screen, not just the presentation part, the entire screen. Then the slideshow will be appearing actually. Okay, just share your entire screen, not just the presentation. Okay, now just go to the presentation one and then.
It's not properly working, sir.
Yes, just go to the presentation part, the lower. Yes, just go to presentation. No, not
Now
yeah.
it's visible, sir.
Yes, so now make it full screen. I think now it will be visible. Yes,
Okay.
now it is
Is it
visible.
visible?
Yeah,
Okay.
yeah.
Okay.
Yeah, please go.
Thank
Please.
you.
Yes.
So this is the schematic diagram how green synthesis process carried out. So first plant extract is added to the material solution and the reduction reaction start. And the plant extract, the phytochemical present in the plant extract itself act as a stabilizing and capping agent, and we get the synthesized nanoparticle. We can vary the shape or size of the particle by varying the pH, temperature, or the concentration of the plant extract. These are some advantages and disadvantages of green synthesis of nanoparticles. Basically, the advantages are it is a very simple and one-pot reaction. It is cost effective, and the hazardous chemicals involved it is eliminated. But it has some disadvantage that we cannot control the shape or size of the prepared nanoparticle, and heating condition is required for the formation of the nanoparticles. In my present work, I synthesize silver, zinc oxide, copper oxide nanocomposite using terminal bark extract at the different concentration of the silver. For this, I used zinc nitrate, copper nitrate, and silver nitrate, the precursor solution, and the concentration of the silvers are correspondingly 5%, 10%, and 15%. And for the presentation, from now onwards, the 5% silver concentration will be termed as A5 and 10% as A10, and 15% of the silver will be termed as A15. This is the experimental technique where terminal of the bulk extract is there. So firstly, the silver nitrate solution is added to the zinc nitrate solution and sonicated for 15 minutes to get the uniform distribution. And then this is again added to the this combined solution is again added to the copper nitrate solution, again sonicated to get uniform distribution. Then this solution are placed in magnetic stirrer, and slowly the bark extract is added to it with constant stirring, and some precipitator observed, and this precipitator settle down at the bottom. After 24 hours, I collect this precipitated, air dry, and calcine at 500 degrees Celsius for 1 hour to get the final nanocomposite. These are the X-ray analysis of the prepared nanocomposite. The first one is for A5, that means the 5% of the silver second one is for that A10, and the third one is this one is for that A15. So from all the external data, it is shown that we got sharp intense peak. So from there we can say that the TPR nano composite are crystalline in nature, and we show some peak for all the that means all the that means for silver as well as for zinc oxide and copper oxide, as the dot represent the peak for the zinc oxide, and the triangular one is for the copper oxide, and the star one is for that silver that means nanoparticles. And we calculate the average crystallite size from the Debye-Syrah formula, and the particle size are, as for A5 it is 33.85, for A10 it is 41.75 nanometer, and for A15 it is 42.82 nanometers. So it is observed that as we increase the concentration of the silver, the particles average crystallite size is also increases. Next, the optical properties of the synthesized nanocomposite are studied by UV spectroscopy, and I use the Kovalka-Munk function to determine the absorption coefficient, and the modified type plot using KN function is used to determine their corresponding energy band gap. So this one is the absorption spectra and the corresponding type plot for A5 sample. This one is for the A10, and this one is for the A15 nanocomposite, and their corresponding absorption peak and band gap are tabulated here. So for A5, it is found that absorption peak at 305 nanometer, and for A10 it is 311 nanometer, and this is for A15. For A15 it is 350 nanometer. So we observe that as we increase the concentration of the silver, the peak shifted to the higher wavelength side, and their corresponding band gaps are this is 3.20 electron volt, 3.17 electron volt, and 3.03 electron volt. So we see that as the concentration of silver increases, peak shifted to the higher wavelength side, and their corresponding band gap decreases. So which means that the particle size, as we increase the concentration of silver, particle that means band gap decreases, which corresponds to there is an increase in crystallite size, and this is also that means we already shown from XRD data. So my UVTRS results are in agreement with the XRD data. So this is the VSM analysis for that nanocomposite, or all the nanocomposite. So from this MH curve, we say that we got a hysteresis loop, and we can conclude that the from that MH curve that the ferromagnetic behavior of the synthesized nanocomposite at room temperature. These are the magnetic parameter value for all the three samples, and we can conclude that the ferromagnetic behavior may be interaction between the oxygen vacancy and the silver ion doped in the zinc oxide copper oxide nanocomposite. Now come for the conclusion part. XRD pattern shows that the samples are crystalline in nature. The crystallinity increase with increase in the concentration of the silver doping. The UV spectrum shows that with increase in silver concentration, there is an increase in absorption peak, and the band gap energy decreases with increase in silver concentration. And the MH curve shows that the ferromagnetic behavior of the prepared nanocomposite. So I would like to thank the organizer, the Department of Physics, Bhawanipur Anchalik College, for giving me this platform, and I extend my gratitude to my supervisor, Dr. P.K. Musari sir. And last but not the least, I would like to express my gratitude to all the faculty members and fellow scholars of the Department of Physics, Bowdoin University, Prakash. Thank you.
Thank you, Subhankar, for your nice presentations. Now it is open for some questions from the audience. We have 2 minutes in hand for question and answer sessions. Yes. Subhankar?
Yes, sir.
Yeah, can you, I have one question actually. Can you go to the
Yes,
slide, I mean, where you have shown the band gap versus the size? Yeah.
This one, sir.
Okay. you can see that A5 and A10, the
Yes, sir.
band gap is like 3.2 and 3.17, right?
Yes, sir. Yes, sir.
See the crystalline size, it has changed significantly, right?
Yes, sir.
So what is the and see from 4.12, it has the crystalline size has it has changed significantly from 33 to 8.5 to 41. But again from from the A10 to A15, the size has
Yes, sir.
increased by a small amount, but whereas the band gap is changed significantly. You see.
Significantly. Yes,
So
yes, sir.
how will you justify that thing? What is the reason for that? I just want to know that.
Sir, this might be, sir, because the silver ion, as we increase the concentration, sir, it might possible that, sir, silver ion may that means deposit in the lattice side of this composite zinc oxide copper oxide nanocomposite. So as the silver ion this may be the size of the silver ion, I suppose, sir.
Is it? So, do you have the spectrometric data of all these samples? I mean, UV visible data. I mean, since you have considered the absorption peak,
Yes, sir. These are the
Okay.
This one is for that A5, sir.
Okay. So, I think it would have been better if you have merged it, all the three samples, A5, A10, and A15. So in that case, it would have been better to have a kind of comparative kind of idea. Anyways, thank you so much for your presentations. Any other questions? Any other question from the audience? If not, so let us thank Subhankar for his presentations.
Thank you, sir.
Next is Atanu Bital.
No, actually, sir, Atanu's talk is rescheduled to so his talk is rescheduled to I think later afternoon. Yeah. So I think now it will be Sarfaraz. I think he's not joined yet. Neither Apurva. So we can move on to Vikas Kumar Das. So is Vikas Kumar Das from Tezpur University? Are you here?
Vikas, are you online?
Yes, sir.
Yes, please start your presentation.
Okay, sir. Is it visible, sir? Hello.
Yes, it is visible.
Okay, sir. So, good afternoon, everyone. My name is Vikas Kumar Das. I am from Tezpur University, and under the guidance of Professor Damodar Mohanta. Thanks to the conference committee for accepting my abstract. And top of my title is Roughness Mediated Surface Wettability Characteristics in Flower Petal. So, before going to much detail about my talk, so let us introduce what is wettability. Wettability is just the propensity of surface to become wet. You have seen many of the objects just wet because of the rain, some kind of water is spread over here or there. So there is a mathematical law which is given by Thomas Young for a smooth surface that this contact angle, this particular this particular equation which relates the surface energy, interfacial energy of solid vacuum, solid liquid, and solid liquid vapor. So, with the help of this interfacial energy, the contact angle made by the water droplet with the surface is decided. So, depending upon this contact angle theta, we can just distinguish object on the superhydrophilic when the contact angle is less than 10 degree, in between 0 and 10 degree. If the contact angle is greater than 10 to 90, then the surface is termed as hydrophilic. If the contact angle is greater than 90 and less than 150, that the contact is said to be a hydrophobic surface. If the contact angle is greater than 150 or something in liters and 140, then the surface is termed as superhydrophobic surface. So, The wettability of a particular surface depends on the two things. One is the surface morphology, that means how the surface is, the surface structure, and another is the chemical composition. What is the chemical material in the surface? Okay, so in this study, we will just focus on the roughness, that is the surface morphology, how it dictates the wettability behavior. So in this figure, you can see that roughness is in the nano dimension, that in micro dimension as well as macro, or in the combination decided the wettability of particular water drop on the surface. So roughness may manifested via structure in varied length scale, leading to wetting dewetting features in system. So in this example, there is a flower called pickle, where this is the same image and this is the magnified same image, and the contact angle is 143.9 degree. It is found as hydrophobic, and you can see in the same images it's micro bubble and the nanoparticles structures are there. And along with that, this is orchid flower, white orchid flower, and the contact angle, water contact angle is 134.3 degree, and it is also hydrophobic. And in the same images, it is seen images, it observed that the microbumps and nanowaves are present in the epidermal cell of this flower, which is actually dictated the wettability features. You can, in these two examples, which is given by Feng in his later in his study, apart from that, the combination of micro, here you can see the microbubble or nanoparticle or microbumps in nanowaves, the combination of micro and nano roughnesses also lead to the superhydrophobicity. That means the contact angle is beyond 150 degree. So one of the common example in the is the rose petal. In the rose petal, the water contact angle is 151.6 degree, which is hydrophobic, and it shows some kind of petal effect. That means whenever the water droplet is placed on a rose petal and we make it upside down, then also the water droplet will not come out from this surface, and this effect is called a petal effect. And in the same images, it is seen that the periodic array of micropapillae and the nanofolds are present on its papilla top. Because of this structure, the superhydrophobicity is seen in the rose petal. Like that, there's another famous example is the lotus leaf. In lotus leaf, the water contact angle is 164 degree. That is, it is also superhydrophobic material. But here's the difference is that if we tilted the surface of a lotus leaf by slight 1 or 2 degree, the water droplet roll off. That means there are two kinds of natural surfaces where the structure is almost same, that is the micro and the nano roughness. But one shows the petal effect, when upside down the surface, the water droplet will not come from it. Another is that kind of lotus leaf, where if we slight alter the surface, then it will shows the lotus effect. That means the water droplet roll off from it. So in order to explain mathematically those wettability features, we can have two models. For the micro roughness, the model is Winzel model and another is Dibya model. Okay, so where the roughness and the water contact angle is related to the atomic contact angle. In the Winzel state, what has happened? The water droplet actually emerged on the micro roughnesses, here you can see, but in Dibya state, the water droplet is suspended over the micro roughness. Combining these two effects in nano and micro roughnesses, here we have 4 cases. The Dibya state, where the water droplet is suspended over the micro as well as the nano roughnesses. Winzel state, where the water droplet is suspended over the micro roughness, but it weighs the nano roughness. Again, in Winzel state, the water droplet weighs the micro roughness, but suspended over the nano roughness. But in Winzel state, both the roughnesses is weighted, and for both of these 4 cases, the 4 modified equations are there. Now, our motivation is to proper understanding and evaluation of surface wettability of our natural textile surfaces, which leads to fruitful day-to-day application. Like in glasses of your window or glasses like speakers. All these are some beautiful example, and apart from that, the solar cell also could be a good example where surface wettability behavior is applied. Okay, so for that purpose, in order to understand wettability in more detail, we have taken two samples which is easily available in Assam perspective. So one is the pepper flower, and another is Krishnasura flower. So in pepper flower, I have taken three kinds of its color: pink, white, and yellow. But in Krishnasura, we have taken only the one kind, that is the red one. So these are the scientific names or family belonging to this particular specimen. So we have utilized a contact angle meter to measurement the static water contact angle. In pink bougainvillea, we have seen its contact angle is 121.1. So white bougainvillea, it is about 116.9, and for yellow bougainvillea, the contact angle is 121.3. For the Krishnasura flower, that is Delamis regia, it is 126.6. That means all these four samples are hydrophobic in nature, but none of them are super hydrophobic. So we have also performed to know, is there any petal effect or lotus effect? There is the term, there is the experiment called dynamic water contact angle. That means we have to rotate this stage and we measure the contact angle at each degree of tilting. So when we tilted the surface, in the x-axis it is the tilting angle of the surface, and in the y-axis it is the water contact angle of the top of the surface. So in the 0 degree, the water droplet behave like that, and when it is tilting angle is 90 degree, the water droplet will not come from the petal surface. And this is also shows that the pink bougainvillea flower also shows the petal effect. Similarly, white bougainvillea flower is also showed a petal effect, and yellow bougainvillea flower is also showed a petal effect. But there are microscopic information, that means they are different in the sense of receding contact angle and advancing contact angle. Advancing contact angle is this angle where we, if we turn around, this is the advancing contact angle, and the receding contact angle will measure by this end. And when there is a difference between advancing and receding water contact angle is called the contact angle hysteresis, which gives the information about the surface adhesiveness of a particular people or a particular texture surface. So you can see for pink bougainvillea, the contact angle hysteresis is 51.4. For white bougainvillea, it is 36.6. For yellow bougainvillea, it is 47.7. So the interesting thing is that among the same species, the water contact angle can vary from one to another range. That means a drastic change can be there in the water contact angle hysteresis. That means is the surface adhesiveness. So all of the colors of bougainvillea exhibit petal effect. That is the water drops of pink in those surfaces. So we want to know what is the surface morphology of this particular flower. For the pink one, you can see this is the epidermal cell. Through those epidermal cell, there is a beautiful excellent star-like structure. And when we zoom one particular structure, it is the nanostructure that is present over this particular cell. Again, for this white one, this is the lower resolution image, and when magnification is bigger, that means from this area, if we zoom it, it appears like that. When we zoom this particular area, it turns out like that. That means in nano dimension, there are some kind of flags present over the microstructure epidermal cell, which is
because your time is up. This comes to the conclusion.
Yes, sir. This is not present in the pink bougainvillea flower. So yellow one also shows the same kind of epidermal cell. So the observation is the epidermal cell have the extended star-like shape covering few hundred square meters. They exhibit fractal-like structure and nanoflakes are observed. Apart from that, the roughness mediated by micron-sized epidermal cell and nanoflakes present on them could be resulting hydrophobicity and water droplet filling effect. From another sample, that is from Krishnasura, it is also shows this kind of behavior. That means the petal effect, and the contact angle hysteresis is 35.4 degree. It is also shows the petal effect. So in the microscopic images, this is the microscopic images for Krishnasura flower, and you can see in those epidermal cell there are nanowaves are present. So the epidermal cell are polygonal shape. Each epidermal cell possesses nanowaves on its surface. For this simple, thinning effect and hydrophobicity also could be because of the two triad of micro and nano roughness. So the conclusion is the roughness could be a factor for hydrophobicity and thinning effect, which can be calculated with the help of geometrical analysis using Windsor model for this case. And it could be extended for the fractal structure in case of bougainvillea. Although the specimens are from the different classes of species, the observed phenomena are the same for the experimental surfaces, which can be attributed to the two tiers of roughness, again the nano and the micro roughness. So the roughness can be calculated for each specimen. In the future, we can calculate the roughness for each specimen using the geometry provided by the surface to relate the weightability features. Again, the nano and micro roughness result in both Lotus effect and Pittel effect. To distinguish these phenomena, the thinning force can be calculated to gain more insight. The role of surface chemistry can also be studied in reference to the aforesaid effect with the help of XPS analysis. So these are the acknowledgement and bibliography of my talk, and thank you for your attention.
Thank you, Vikas, for your presentation. So it is open for quick question. If anybody is having questions, you can take quickly. Yes, anybody? If not, let us thank Vikas. So we now move to another next speaker. Next presentation is from Achyut Sharma Hazarika from Kaziranga University.
Yes, sir.
Are you there, Achyut?
Yes, sir.
Yes, please start your presentation.
Am I audible?
Yeah, you're audible. Please share your screen.
Is it shared?
Yeah, I think it is going to be shared. Okay, yes.
There is, I am good evening to everybody. I am Achyut from R&D Cell in Computer Department of R&D College. The Scholar Department of Ecology and Science from and today I want to give an analysis about the synthesis and development of synthetic graphite and phenolic resin composite and characterization of electrical conductivity and mechanical strength. There is on application of the application in now the outline of
please go to the presentation mode, Achyut. Sorry to interrupt you.
Okay, am I visible? My presentation.
You are. Please go to the presentation mode. I think it is still in the.
Okay, this is my outline. There is introduction by 12 cells.
Actually, Mr. Hazarika.
Yes, sir. Yes, sir.
So you need to basically just.
Okay, sir.
You need to basically make it in full screen mode. Where, okay, just go to the slideshow, that option in top of your presentation. Yes. Yeah, or you can go there.
Okay. Now,
but again, I think you have just shared, because you have only selected them. So can you please select your, share your entire screen and then go to this. Kindly share your entire screen. You can just close this share. You can just switch off the share screen now. Again, you can reshare it. Okay. You have to select the share the whole screen basically.
Okay.
So there will be an option that will mention as entire screen. So you need to select that.
Entire screen.
Yeah. When you press the when you select the share button,
yes,
you will have. Okay, I think now. Okay, yeah. Now it works. Okay. Sure. Please go ahead.
Okay. why fuel cell? Fuel cell can operate at actually a higher efficiency than combustion engine and can convert chemical energy into the fuel directly to the chemical energy with efficiency capable of exceeding 50%. And it can help in the, and actually there is a conservation of the fuel, fossil fuel, alternate clean energy system, environment protection, and sustained development. Now, there is there is so many applications of the fuel cell. There is a portable applications, and there is transport applications, and other is the stationary applications. This is the figure which we show there. There is the direct methanol fuel cell. There is GMFC. There is in the up to 100 watt, and EEMFC. That is the proton exchange membrane fuel cell. That is up to 100 kilowatt, and the SOFC, that is the solid oxide fuel cell. AFC, that is the alkaline fuel cell. MCFC, that is the molten carbonate fuel cell. And now I want to give my emphasis on the bipolar plate. That is the that is a bipolar plate. That is also known as flow filled plate. It is a key component of connecting each shell electrically and supplying reaction gas, removing reaction byproduct of the cell. And the bipolar plate can be made from various materials. Just I will discuss my next slide. That EMFC system is designed to generate power up to 0.60 kilowatt by consuming hydrogen fuel with a constant current density 0.02 ampere per centimeter square. In practice, what we have, the many fuel cells are usually assembled into stacks. Now, what is the functions of the bipolar plate? There is the functions of the bipolar plate is to distribute the fuel and oxygen within the cell and to facilitate water management within the cell, separate individual cells into stacks to carry current away from the cell and to facilitate heat management. Okay. Then what the materials used in the bipolar plate? That is, a bipolar plate actually we just use there are so many types of the bipolar plate. There is a non-porous graphite plate, pocket metallic plate, and a composite plate. And a composite plate, that is our aim. That is the carbon base, and the other is the mixed base. We select the composite carbon base. That is where we use the polymer matrix as thermoset resin, and the other is the carbon filler. That is a natural graphite house. Okay, this is our keyword. Then what we use in our study, that is one is the synthetic graphite and the other is the phenolic resin. These are the materials, two materials. That is one here. One picture is the FESM for synthetic graphite, and the other is the graph for the XRD of synthetic graphite, and other is the graph for TGS. That is the gravity analysis for phenolic resin. These are the two important graphs. So we select these two for the to make the what is called the bipolar plate. Okay, then how we prepare the composite? That is the preparation of the composite is phenolic resin. So that is a compression molding technique. That is the what we use here. The synthetic graphite and the phenolic resin are combined. They are mixed in the powder form by the mixer grinder, and this is composition filled in the die and allowed to increase the temperature up to 150 degrees Celsius and slowly applied around the sample by hydraulic press between 120 degrees Celsius to 150 degrees Celsius, and by keeping the sample at 150 degrees Celsius for 2 hours, and after 2 hours, freeze off and allow the sample under pressure for 12 hours. Then what we find that there is one of the most important characterization. There is creation of the composite, that is a measurement of the mechanical property, that mechanical properties of the composite, what we have in our laboratory, the mechanical properties of the composite were measured by using strong universal testing machine, model this one, that is 59597, and sample for testing were prepared according to ASPMD 790 standard. ASPMD stands for the standard test method for flexural properties of the that is the material. Then we found that if the sample composition contains 100% resin, then the flexural modular, that is in MPA, that is 3570.8, etc. And this shows the whole the data. Table shows the data what we had, what we calculated after. Then we actually measured the electrical conductivity. The electrical conductivity was measured by the conventional what we have in our laboratory, the whole probe method at a constant current supply. The electrical resistivity of the composite bipolar plate sample was measured using the four-probe technique, and we found that 80 to 20%, that is the conductivity, is 40.28. And when the synthetic graphite percentage is 70% and resin percentage is 30%, their conductivity becomes very, very less, that is 2.2. 60 to 40% is also less, 0.77, and 50 to 50% is very much less, that is 0.09 per centimeter. And what conclusion I can draw there? From our observation, what conclusion we can draw that the synthetic graphite phenolic resin composite prepared by compression molding techniques shows in electrical and mechanical properties. In plant conductivity of the composite depends on the graphite content, and the 80% of synthetic graphite content is what we observed that 80% of synthetic graphite content is very high electrical value. That is approximately 40 points, that is 40.38 per centimeter. The conductivity is very high, so with constant current supply of 0.121 ampere. The mechanical characterization of the composite shows that synthetic graphite content makes the material more resistant to bending, and the flexural modular value goes up to 9700 ampere for maximum. There is a synthetic graphite content that is 85. The material can sustain 50 ampere for just 50% loading of synthetic graphite with a load amount of 251.5. What we found that the other factor is that these composite materials can become efficient. This composite material can become efficient candidate for the bipolar plate fuel cell application as per USDA target 2025. After found other secondary separation in yes, sure. This is my reference. Thank you.
Thank you, Mr. Hazarika, for your presentation. We have a few seconds, roughly. I mean, we can take a couple of quick questions from the audience. Yeah, Mr. Hazarika, you have shown one on. Can you go to the previous slide? I mean, the mechanical properties. Yes, I have one question. Yes.
Yes, sir.
No, not really. I think you have listed some thing, right? I think 256 or some 224. Just after that, go next.
Next slide.
Yes. After yeah, next one, please. You have mentioned one particular. Yes, here. Just be there in the previous slide. Yeah. No. Here. Yeah. So you have said a high electrical value of 40.38 S per centimeter. What do you mean by S per centimeter?
Oh, that is the what I mean to say. That is the conductivity. There is Siemens per centimeter of 3.68.
Okay. And then you have written in the conclusion part, in the third point, the material sustains 46 MPa, megapascal, I believe, for just 50% loading with SGA load of around 251 kg or something like that. Load.
It is load is easy.
It's kg, right?
251 yes.
Okay. Thank you. I think this clarity I want to do from you. Okay. Any further questions from the audience? If not, let us thank Mr. Uchur Hazarika for your presentations. Thank you, Uchur. So we now have the next speaker. Wait a moment, I missed the schedule. Who is in the next?
Oh, actually, hi. So next, there were a few, but because some network issues at their end, they were not able to join. So now, I think in the list, Jyotsna Saikia is there, I guess, in the participant list. So, Jyotsna.
Jyotsna.
Yes,
Jyotsna
sir.
Saikia. Okay. Hi.
Okay.
Haha. Then, is it okay? So, please share your screen.
Yes,
Sure.
Yes.
Okay, sir. Thank you, sir. Sir, isn't my screen visible?
Yes, your screen is visible, but you need to share your entire screen. Then only the whole the presentation mode will have the entire picture. So you need to share your entire screen, not just the presentation.
Yes.
Yes,
Better.
this will. Yeah.
Okay, sir. Good afternoon to all. I'm Jyotsna Saikia from the Department of Physics, R&D College. And the topic of my presentation is spectroscopic studies on the interaction of aspirin with polariprotic solvent. And here we use DMF as a polariprotic solvent, and we study the interaction between aspirin and DMF. These are the main outlines of my studies. Aspirin is a non-steroidal anti-inflammatory drug that exhibits a broad spectrum of pharmaceutical activities that includes analgesic, antipyretic, antioxidant, and anti-inflammatory properties. This drug also shows its preventive effect against several human cancers, including breast cancer, gastric cancer, colon cancer, etc. And multiple lines of evidence shows that reactive oxygen species is one of the major contributors towards the growth, progression, and regeneration of cancer cells. A high level of reactive oxygen species level promotes metastatic tumor progression. Since cancer is one of the leading cause of death worldwide, so researchers are trying to find the best possible medication to cure this deadly disease. DMF is a simple polariprotic solvent that significantly inhibited tumor metastasis by reducing this reactive oxygen species production. So in this context, we aim to study the interaction between aspirin with DMF using spectroscopic tools, and we mainly use Raman, SARS, and FTIR spectroscopy to study the interaction between them. We'll also correlate the experimental findings with the DFT-based spectra of the molecules, and we'll also study the role of intermolecular hydrogen bonds in the structural properties of the molecules and its impact on the molecular spectroscopic signature. The experimental methods includes this Raman, SARS, and FTIR techniques. This one is the experimental setup for Raman spectroscopy, and this one is the experimental setup for FTIR spectroscopy. We prepare silver nanoparticle to perform the SARS, to record the SARS spectra of the molecules. And the computational methods includes the geometrical optimization and frequency calculations of the
aspirin and aspirin DMF combination. We used GaussView 5.0 and Gaussian 09W software for this geometrical optimization and frequency calculation process. We used the BTLYP 6011 plus GDP basis set under the context of DFT, and Origin Pro 2021 software is used for spectral analysis. We have used a scaling factor of 0.9668 to compensate the systematic errors. It will also enhance the correlation between the theoretical and experimental results. Figure 2A shows the optimized structure of aspirin, and figure 2B shows the optimized structure of aspirin DMF combination. Here we observe that in figure 2B, two intermolecular hydrogen bonds are formed between aspirin and DMF. This is the O3 molecule, and this is H33 hydrogen molecule. One intermolecular hydrogen bonds in formed between oxygen and hydrogen molecule, this one, and it has bond distance 2.31 angstrom, and another one intermolecular hydrogen bonds is formed between O22 and H21, and it has bond distance of 1.64 angstrom. And due to the formation of these two intermolecular hydrogen bonds, the bond parameter of the complex has changed as compared to the individual ones, and these parameters are, some of the parameters are listed here. In table 1, we observe that the O2H21, this bond is calculated as 1 angstrom, whereas it is calculated as 0.97 angstrom in the individual state, that means in case of aspirin. Here we observe that this O2H21 bond is elongated by 0.03 angstrom in the complex as compared to the individual state. Similarly, this C11O3, this bond is also calculated as 1.22 angstrom in the complex, whereas it is calculated as 1.21 angstrom in the individual state. This bond is also elongated by 0.01 angstrom in the complex. And this elongation or contraction of bond lengths is due to the formation of intermolecular hydrogen bonds, which is also because of the charge transfer between the two molecular units. And due to the variation of bond parameters of the complex, the spectral properties of the complex is also changed. And these are the Raman and charge spectra of the complex in the spectral region 0 to 2000, and this one is for 2000 to 4000 per centimeter. And figure 3C shows the theoretical and experimental Raman spectra of the individual component, that means for aspirin in the spectral range 0 to 2000, and this one is for 2000 to 4000 per centimeter. And figure 4A shows the FTR spectra of aspirin DMF combination in the spectral range 0 to 2000, and this one is for again 2000 to 4000 per centimeter. And these two are the FTR spectra for the individual molecule aspirin in the spectral range 0 to 2000 and 2000 to 4000 per centimeter. And these are the vibrational assignments of aspirin, which has been calculated using theoretical calculations. These are the theoretical data, DFT based wave number, and this is for experimental Raman, and this is for experimental FTIR spectra. Here we observe that the stretching mode associated with O2H21 group is calculated as 3648.09 per centimeter, and we observe that this mode is lower to the 3014.42 per centimeter in the interacting state. Similarly, if we see here, the stretching mode associated with C11O3 group is calculated as 1724.49 per centimeter in case of aspirin, whereas it is calculated as 1691.07 per centimeter in case of aspirin DMF combination. Here we have observed that the wave number decreased in the combination as compared to the individual state. And this is due to the formation of intermolecular hydrogen bond. Here we focus on the OH and C double bond O, these two groups, because these two groups participated in the intermolecular hydrogen bond formation between aspirin and DMF molecules. And this is the conclusion part. Here we study the interaction between aspirin and DMF using Raman search and FTIR spectroscopy techniques. Here, from this analysis, we have observed that the OH and C double bond O groups of aspirin and DMF are involved in the intermolecular interaction between the two. And due to the intermolecular hydrogen bond formation, we found the redshift in case of C double bond O and CO stretching vibrations. These are some of the references, and I would like to gratefully acknowledge NERIST and Tezpur University for providing instrumentation facilities. I am also thankful to the organizer for giving me this opportunity to present my work. Thank you. Thank you so much, sir.
Thank you, Jyotsna, for your nice presentation.
Thank you, sir.
So we have a couple of minutes for to take few questions from the audience.
Hello.
Yes,
Hello,
Satya Sadhan.
yes, sir. I have a question. Yes,
Okay. Please.
Yeah. As per reports or as per research, we have come to know that DMF is toxic in nature. So, have you ever tried to see the toxic effects or cytotoxicity of your study?
We have not taken into account now during my research, but in future I will study that part also, sir. In this work, I will also study the toxicity part using. There are various computational tools to study the toxicity. One is LD50 values, which is also used for toxicity measurement. I'll taking care of that part, sir.
Yeah. Okay, look into it, because as per the application point of view, I think this care should be taken, because ultimately the research is going to impact the society, right?
Yes, sir. Yes, sir.
Next presentation, please.
Okay, sir. Thank you, sir.
Okay.
Any further question from the audience? Okay, I have one question for Jyotsna.
Yes, sir.
Can you go to the slide where you have considered the Raman and the search spectra? Can you go to the slide, please? Is your slide still there?
Jyotsna, please share your screen.
Okay,
Yeah. We have only 1 or 2 minutes. That's why I'm taking this time. Okay.
Yes,
Yes, it is visible. Let it be in this position now. Yeah, just go to the Raman spectra and the SARS as well.
Okay,
Okay.
sir. This one.
Okay.
Yes,
So
sir.
which one is your Raman, and which
Sir,
one you
this
have?
middle one is the Raman, and the upper one is for SARS, sir.
Okay. Do you observe any significant change in the SARS signal? I mean, when you consider the SARS,
Yes,
basically
sir.
the idea, what is SARS first of all? What is SARS?
Yes, sir. Actually, is surface enhanced Raman spectroscopy, SARS.
Okay, fine. Okay, thank you.
Yes, sir.
So what is the purpose of using SARS here? I mean, you are to amplify the Raman signal, right?
Yes, sir.
But yes, go ahead.
Yeah, okay, sir. So if we see in figure 3.8, around 1600, we have observed that this peak is enhanced significantly as compared to the normal Raman spectra. Basically,
Understood. Okay.
spectra, we have concern about the intensity enhancement, because the normal Raman techniques gives the intensity of normal Raman spectra is quite low, so we go for the highly sensitive techniques, which is SARS, which is basically used nowadays. So here we have observed that around 1600, this peak is significantly increased in SARS spectra. And
okay, that is fine. But my concern is, what about the other peaks? These are also signature Raman peaks.
Yes,
and
sir.
you can see that near 500, or that 500 shift. the
Yes,
two neighboring peaks, actually, which is, with a normal Raman peak, they
Yes,
are showing almost equal intensity. But when you
Yes, sir.
consider their source, one
Yes,
is
sir.
amplified, whether the other is suppressed, right? Another
sir.
is, So, what is your comment on that?
Sir, it may be due to the interaction between the silver nanoparticle and the substrate. It may be due to that reason, sir.
I think you have to check on it. I mean,
sir.
yes, there some peaks have been enhanced. I mean, it
Yes,
has been
sir.
amplified.
Yes, sir.
But the correlation, or if you want to correlate between the peak enhancement
sir.
by incorporating starch substrate,
Yes, sir.
I don't. Somewhere it is found to be, it's not missing. Somewhere it is found to be missing. You have to correlate it properly. Okay.
Okay, sir. Thank you, sir, for
So,
your
yeah. Another thing, what substrate you are using as a starch substrate? Which substrate you are using? You have to
Sir.
use some substrate, right?
Yes, sir.
What is
Sir,
that?
Sir, actually, we make the silver nanoparticle, and we use that for substrate, and we take our sample and we give the sample there, and we then check the record the spectra, sir.
I mean, you just drop casted the silver nanoparticle on a glass substrate or some other thing?
Sir, on glass substrate, we drop the
Okay. Silver nanoparticles. And then what are silver nanoparticles? You are putting your sample, right?
Yes, sir. Yes, sir.
Okay, but since you are doing some kind of analysis, I think you should also understand the mechanism of source enhancement, and also you have to take the images of the silver nanoparticles, how it is distributed. Okay,
Yes,
in
sir.
order to get a confirmation. Okay, actually it is showing the source enhancement actually.
Yes, sir.
There could be other attributes also in your signal enhancement process. But
Yes,
I would suggest you to check the formation of the source.
Yes, sir.
Under scanning electron microscope or FESM or something like that,
Okay,
to
sir.
ensure that the silver nanoparticles are actually there and forming some hotspot on it.
Okay,
Okay.
sir. Okay, sir.
Okay.
Thank you,
Okay.
sir.
Thank you, Josna.
That's understand, sir. Okay.
Okay. Yeah. Thank you so much. So can we go to the next speaker now?
Yes. So the next speaker is Pankaj Bora from Kaziranga University.
Okay,
Dr. Bora, he's here, I guess. Dr. Bora. Okay.
Okay. Hello. Am I audible?
Yes. So okay, let me make the announcement. So after Pankaj Bora, Apurva Rai from Guru Hasidas Vishwavidyalaya, Chhattisgarh. So are you there, Apurva Rai? Yeah, you are here in that. Yes, he's here. Okay. Okay, fine.
Okay.
So after Pankaj Bora, Apurva Rai will be speaking. Sure. Okay.
Apurva, please start. I think Pankaj.
Pankaj, yes.
Yeah, please, Dr. Pankaj, please start.
Is my slide visible, sir?
Yeah, yes, now it is visible. Please go to the slide presentation mode.
Actually, again, I think you need to share your full screen. I think you need to share your full screen, not just the presentation. Just you can stop your sharing and then start again starting with like the full screen. Entire screen, basically. I'm stopping your screen sharing now. Okay. You can just reshare it by the option of like share entire screen. Yeah, it's fine now.
It's fine now?
Yes.
Okay.
Please go ahead.
Good afternoon, everyone. So myself, Dr. Pankaj Bora, Assistant Professor from the Department of Physics, School of Basic Sciences, Darpan, Kaziranga University. So my topic of discussion for today is the enhancing EMI cell link and still capabilities in the X-band using planar material structure. metamaterial structure. So in this work, we have to investigate the planar metamaterial structure to improve electromagnetic interference shielding and steal capability in the X-band frequency region, which is from 8 to 12 gigahertz, using FR4, that is frame retarded material 4 as substrate, and the copper conductor as a back substrate, as a back flip. So we will design and analyze the various metamaterial configurations to achieve superior absorption characteristics, and our goal is to create the design that offer high absorption at normal incidence, and so polarization dependence and wide angle performance, while also being lightweight and flexible. So this research underscores the effectiveness of metamaterial structures, particularly the proposed metamaterial microwave absorber design, in enhancing the EMI shielding and steal capability in the X-band. So I express my gratitude towards my supervisor, Dr. Jyoti Prasad Gogoi, and also the facilities of the Kaziranga University and chemistry laboratory as well. So this is the outlines of my presentation: the introduction, theory, methodology, and simulation result, fabrication method, application, future scope, conclusion, and reference. So introduction: the term metamaterial, which is actually derived from the Greek word meta, meaning beyond, and material indicating that these materials go beyond the properties of conventional materials. That means this kind of materials is not existed in the nature, so it is a completely engineered material, you can say. Okay, so Sir J.C. Bose conducted the microwave experiments on twisted structure in 1989 to demonstrate the viability of artificial materials. He also studied how these waves bands spread out the changes and direction. The Russian scientist Dr. G. Veselagov he is the first person to most actually demonstrate the possibility of the existence of such kind of materials theoretically. But the J.B. Plenary in 1999, he actually practically made these materials. So basically, what is metamaterial? Metamaterials are desert a macroscopic composite having a man-made three-dimensional periodic cellular architecture designed to produce an optimized combination of the not available naturally to a specific excitation of two or more responses. By arranging these structures, the wavelength of the electromagnetic wave, metamaterials can manipulate electromagnetic waves in unusual ways. So what is metamaterial absorber then? The metamaterial absorber is a type of metamaterial designed to absorb electromagnetic radiations, typically in a specific range of frequencies. The metamaterial absorbers achieve high absorption levels, though they are unique structure rather than their composition. The structures are engineered to interact with the electromagnetic waves in such a way that the incoming radiations is efficiently absorbed. So this is how my work is totally on this simulation work actually. So this is how the methodology for the process. The first we start, then the reference unit cell is being designed, then the substrate material is selected, then adjust unit cell parameters to have the desired results. If the simulation results fulfills the expectation, and then we can fulfill the again. If it is not fulfilled, then again we have to repeat the same process. If it is fulfilled, the required in the simulation, if the data of the unit cell fulfills our requirement, then we need to made it practically. But if it doesn't fulfill the characteristics, then we can again restart the process. So this is the proposed design, metamaterial absorber unit cell. So these are the different parameters which are giving. This is the unit cell of the metamaterial structure. So this metamaterial structure consists of basically these three parts. This one, So it consists this is the ground plan, and then we have a substrate material. This ground plan is made up of completely copper, completely perfectly conducting material. Then this one is the substrate. We are using basically FR4 as the substrate material, and then in the top, this one is the design, material design. So this is, we have this design we are selected for this purpose. So this is all about the design which we have that means constructed by using CST Micro Studio. It is a software, okay, with the help of which we can design this metamaterial absorbers. Now, once we simulate the process, then we have get this S11 parameter. This S11 parameter, actually, it is the reflection loss coefficient. That means it is the there should be two ports. One port is giving us the signal, and the other port is what, taking back the signal. So S11 means what? It is the reflection at port 1, and then reflection at port 1 divided by incident at port 1. So if it is goes beyond, if the value is very small, that means a very small amount of waves get reflected from the surface. So maximum waves get absorbed by the surface. So its S11 value comes out to be around minus 35 dB. This is in dB scale, and this is the frequency region, which is from about 8 to 16 gigahertz range. So it shows a potential peak over here. So it is and also the minus 10 dB bandwidth here is for little bit enhanced. So it is value is around, in minimum value is around minus 35 point. Sorry. So its value is around minus 35.493 dB, while at 11.36736 gigahertz frequency. This is the frequency where we are getting this S11 parameter. It has a minimum of again minus 34.014 dB. This one, the optimized metamaterial exhibits a minus 10 dB bandwidth of approximately 403 megahertz. Okay, centered around the resonant frequency. So minus 10 dB bandwidth is over here. That means so we are getting a very good bandwidth of around the 403 megahertz, which is centered around the resonant frequency. So this is the absorbance. If we put the absorbance against the frequency, then we are getting that what most of the almost 98% absorbance is occurs here. So now what we have done, we have changing the polarizing angle while keeping this theta is the incident angle, and phi is the polarizing angle. So if we studied this process by keeping the incident angle fixed, that is normal incidence, and but while this polarization angle, we are changing the polarizing angle in like this. So we are getting a graph like this. So from this graph you can see that if we change the polarizing angle, that does not change too much about this S11 parameter. So it is we can say it is polarization independent. Now here what we have done, we have changing the incident angle while keeping the polarization angle same now. Now if we change the incident angle by keeping the polarization angle same, then we can see this kind of variations, which suggests that what it is doesn't depend much on this polarization. Now what we have done in the third case, we both the polarization angle and the incident angle vary. So here varying, but keeping both the polarization angle and the incident angle same. That means equal. So we are getting a graph like this. From here again we see that the whenever the polarization angle and the incident angles are keeping at around 0 degree, that this graph will give us the maximum values. Now this is the substrate thickness variation. This graph shows that the what S11 parameter whenever we change the substrate thickness. So this result shows that when the substrate thickness is 0.6 millimeter, then it gives the maximum absorbance, maximum S11 parameter, that is it is beyond minus 40 dB. So it suggests that 0.6 millimeter, if we take 0.6 millimeter substrate thickness, so that will give us a good result. Now, if we change the dielectric constant of the substrate, then we get the S11 parameter varies like this. So epsilon.
Dr. Pankaj, your time is almost over. Please.
Okay, just few one or more slides, sir.
Okay.
So this is if we change the epsilon parameter, then we get the graph like this, which again shows that the what if we keep the epsilon value is 4.6, then we get the very good absorption over here. So this is the mu epsilon and mu, real part of epsilon and mu. So this suggests that the what for this portion it is shows the negative values. That means it is a negative refractive index we are getting. So that actually what the metamaterials reflects. With the help of metamaterials we are able to get a negative refractive index. So these are some of the applications of this metamaterial structures. So the future scopes. So this is my, and then these are some references. Thank you. Yes, sir.
Thank you, Dr. Pankaj, for your nice presentation.
Okay, thank you.
Since we are running out of time, I mean, we can take quickly, very quickly, 1 or 2 questions from the audience.
Okay.
Yes. Any questions from the audience side, please? So if not, let us thank Dr. Pankaj.
Okay, thanks.
Yeah. Can we now move to the next speaker?
Yes. So now is Apurva Rai. Apurva Rai, you're there in the list, right? Can you please unmute and share your screen? Apurva Rai, are you there? Yes, are you there, Apurva Rai? You are on mute, but we cannot hear you. Can you make sure you have a good microphone connection? I don't know. We cannot hear you, Apurva. Can you hear us?
Apurva, you are not audible to us. Kindly unmute your mic, please.
Apurva is unmuted, but I can. There's a problem with the microphone again. Okay, Apurva, right? Then please make sure your connection is good. So then we'll reschedule you to the next one. Okay, so now Dhaneshwar Kalik. Okay, now I guess Apurva, right?
Yes, sir. Yes, sir. Am I audible now?
Yeah. You're audible now. Okay. So you can share your screen, share your entire screen.
Is it visible?
Yes, it is visible. You can do it in full screen mode, and
yes.
Professor Nath, if it's fine, we can proceed, right?
Yes, it is possible.
Yes. Okay.
Yeah, please.
Okay. Good afternoon to all. My name is Apurva Rai from Guru Ghasidas Central University, Bilaspur, Chhattisgarh, and I'm working under the supervision of Professor H.S. Tiwari, sir. And topic of my presentation is autocombustion synthesis of cerium-doped zinc ferrite nanoparticles for supercapacitor applications. So here are my contents. So as we all know that energy is being a very important issue for years. So we have so many sources for energy, like we have fuses or capacitors or batteries. But the main problem is storage of energy, which is the main issue for the consumption of utilization of the energy. So it is necessary to develop energy storage devices to store the charge and to release when it's needed. So for that we have capacitors and batteries, but these both are different in two ways, like in amount of charge storage and how quickly the charge is delivered. So to the supercapacitor can build a bridge between these two by delivering the charge very quickly and can store large amount of charge. So we have worked on electrode materials for supercapacitors. So here we have taken spinel transition metal oxides in our paper. So we have this AB204 kind of material, which we can see on screen. This is the structure where A2 plus cations had occupied 1/8 of the tetrahedral site and B3 plus cations occupied 1/2 of the octahedral site. So AB204 kind of material we have taken, which is zinc ferrite ZnFe204. So we have synthesized it with autocombustion synthesis. In this synthesis, we have just taken the precursor in a stoichiometric ratio, and generally heated it at hot plate at 80 to 100 degrees centigrade. And then we got a product which we have to ground, and after ground we have calcined it at 800 for 5 hours. After calcination, we have just checked it, yet we have checked structural and electrochemical properties. So here XRD of our sample. So here XRD indicates the pure phase of the sample. No impurity peak has been observed, and by doping we can see the peak has been shifted towards the higher angle, and there is no any extra phase has been observed of any oxide or something else. So pure zinc ferrite, and we have refined this XRD pattern. So after ritual refinement of just pure zinc ferrite, we have got these parameters like crystal structure, lattice angles. It's cubic, and space group is FD3M, and chi-square value is 1.19. We have calculated lattice parameters, crystallite size, X-ray density, and unit cell volume by the formula, and here are the values. So we can see after Rittveld analysis that lattice constant increases when decreased with the increasing amount of cerium. And we have plotted here, we have plotted WH plot. Here we can see the crystallite size decreasing with the doping. This is WH plot, and strain. We have calculated this strain by the formula. Here is the formula: beta cos theta is equals to 4 epsilon sin theta plus 0.9 lambda by d. So we have calculated strain and by WH plot method. We have analyzed just to check if our sample is prepared or not. We have hello. So we have just to check if our sample is prepared or not. We have did a Raman spectroscopy of our sample, and here we can see that in the range of 600 to 800, it should be A1G mode, which is present in our sample. F2G3 mode is also present, and F2G2 modes are also present, but EG and F2G1 are not here because of lower frequency, I guess, or something, but we haven't calculated something else just to check. We have analysis. Basically, for electrochemical measurement, we have here a cyclovoltammetry study. By that, we can check if our electrode material is appropriate for supercapacitor or not. So, after analyzing, when we are just increasing our doping concentration, the capacitance is increasing, which is 106.87 farad per gram at the scan rate of 2 millivolt per second. So we can say that it's good. It's showing a good capacitive property, and this is the conclusion. So we have did XRD and Raman to check if our sample is prepared or not, and we have performed only CV yet for our sample, which we can say that after doping, the capacitive property is increasing. So it's a promising material for super electrode material for supercapacitor. There are references. Thank you. Thank you, sir.
Thank you, Apurva, for your presentation.
Yes, sir.
Yeah, we have a couple of minutes in hand, so we can take a few questions from the audience.
Yes, sir.
Yes, any questions from the
Yes,
audience side? Apurva, I would like to ask you one question. If
Yes, yes, sir.
Yeah. So can you go to the Raman slide? I mean, you have taken some Raman analysis, right?
Yes.
Yes. Can you switch it on? Yes. So this spectra, Raman spectra, doesn't give you any significant peak. Although you can
Yes,
see the peak, with the change. So how do you correlate? I mean, how do you correlate between
Sir,
the peaks that you're observing?
sir, actually, we have tried many times for this ferrite sample, but due to problem in I don't know intensity or at lower frequency, some peaks are not visible here, but we can just relate by this these 2 or 3 peaks which should be present in a ferrites. We just have confirmed by these 3 peaks only. It should be present. So mainly we
which
have
peak
just
this?
did XRD.
No, I understand, but also Raman should
Yeah.
reveal some information about your sample. So you see, I could see in the red spectra there are some peaks, near 600, right? In the red Raman
Yes, sir,
spectra.
yes.
Can you bring your cursor there?
Yes, sir.
Yes. You can. Yes, yes,
Sir,
yeah.
this
So
the
yes,
shoulder.
can you comment on it? What is the what is the reason for having those peaks?
No, sir.
No?
I don't know about this.
Okay, I think some analysis will be required. Okay,
Okay,
because
sir.
because
Okay. Sure, sir.
even though it is very small peak, but when you amplify, when you use a source kind of an analysis, probably it will
Okay.
be amplified further.
Okay, sir. Sure, sir.
Please perform those analysis a bit
Okay,
rigorously.
sure, sir. Thank you, sir.
All right. Thank you so much, Apurva.
Okay, thank you, sir.
Yeah. Can you go to the next speaker? Thank you.
Okay. Thank you, Purva. So the next speaker is Dhaneswar Kalita from Burma College, Assam. So Dhaneswar Kalita, are you there? Yes. Can you please share your screen and can proceed to the presentation?
Okay, I am.
Is Dhaneswar is the last speaker of this session?
Yes, actually, he is the last speaker of this session.
Okay, fine. Okay.
Yeah.
Yes, Dhaneswar, please start your presentation.
Have a good day to all. Myself, Dr. Dhaneshwar Kolita. I'm from Bhawanipur College. My topic is the photoresponse properties of cadmium selenide thin films at different ambient conditions. So then, so my topic, this is my topic. Then I'll proceed. My okay.
Go to the present.
This is introduction. The cadmium selenide is a 2,6 binary compound semiconductor belonging to the cadmium selenide family, cadmium sulfide, cadmium selenide, and cadmium telluride. Cadmium selenide thin film has high absorption coefficient and nearly optimum band gap energy. This is 1.73 eV. Cadmium selenide thin film is preferred for fabricating different optoelectronics devices such as thin film transistor, photovoltaic solar cell, photodetector, LED, etc. Cadmium selenide thin film are highly photosensitive, and usually the prepared cadmium selenide thin film associate different types of native as well as foreign imperfection, which have a great influence on optoelectronics properties of the film. The motivation fabrication of high quality devices using 2,6 compound semiconductor. Characterization of cadmium selenide thin films deposit at different ambient conditions, establishments of correlation between surface morphology and electrical properties, influence of deposition parameter on electrical and structural properties of thin film, finding of electrical prospect, technical prospect of cadmium selenide thin films in modern technology, establishment of correlation between experimentally found physical properties, parameters, and theoretically found result. This is motivation. After that, aim of this work: study the increased photosensitivity of cadmium selenide thin film due to external illuminating intensities. Study the effect of external thermal energy on photosensitivity of cadmium selenide thin film. Structural study was done with the help of XRD. Study was done at different temperatures, 303 Kelvin, 333 Kelvin, and 403 Kelvin. Study the carrier stepping depth with illuminating intensity at different ambient temperature of the cadmium selenide thin film. Experimental. A HIN-HIVAC vacuum coating unit was used for prepared cadmium selenide thin film. The thin film was deposited on clean glass substrate. Gunpowder was used as board material. Film thickness was measured using interferometric method. Film were illuminated with the help of a white light illuminating intensities. For white light illuminating intensities, tungsten halogen projector lamp up to 50 watt operating at the maximum voltage to 24 volt was used, and Apple lux meter was used to measure the illuminating intensity, and ECIL electrometer amplifier was of input impedance 10 to the power 14 ohm was used to measure the photo current. Then result and discussion. This is the XRD study. The XRD of the cadmium selenide thin film reveals that the film was grown at 33 Kelvin and are polycrystalline and have a hexagonal Jordan type structure. The crystallites are preferentially oriented with the 002 plan parallel to the substrate as shown in figure 1. However, small percentage of orientation of 110 and 112 plans are also observed in case of the thermally deposited film. Then the photosensitivity was measured with the help of this formula. The photosensitivity S is equal to photocurrent I by ID. ID means the dark current, and photocurrent is the under illumination minus the current under illumination minus current at dark by ID, the current at dark. This is called the photosensitivity, and it was measured that photosensitivity versus temperature. It was fine. It is seen that various with ambient temperature for cadmium selenide thin film of thickness 294 stump deposited at 330 Kelvin are depicted in 2. The photosensitivity at room temperature is maximum for different white light intensities of the cadmium selenide thin film. The photosensitivity is decreased rapidly with the increase of ambient temperature, so showing thereby that there is an exponential like decrease of photosensitivity with ambient temperature. Variation of photosensitivity on applied bias and illuminating intensity of cadmium thin films. There are two plots are there. One is that here here photosensitivity and applied bias are shown this. That the photosensitivity observed in the two different conduction level. This is two different. This is one type and another type. Here also this is one. This is another. At lower bias, photosensitivity is increased linearly. Up to this, the photosensitivity is increasing linearly. Lower bias. After certain voltage, PTH, after this increasing behavior of photosensitivity changes from linear to exponential. It is exponentially increased. It is because the grain boundary core of pure cadmium selenide thin film contain a large numbers of defects due to the dangling bond that gives rise to the large numbers of localized state. The native defect state, along with the concentration, act as carrier trapping center. At low field, the rate of carrier injected is small and linear. So photosensitivity is entirely governed by the intrinsic P charge carrier density. In this region, there is less probability of getting interaction between grain boundary barrier and limited injected carrier density. But when the bias is increased beyond PTS, the rate of injected carrier density becomes greater than the free carrier. At this situation, the injected carrier interact with the grain boundary potential by hopping between the localized sheet, with which reduce the height and increase the carrier mobility. Therefore, sensitivity increases. Then the last one, this is variation of photosensitivity with external illuminating radiation. So this radiation, this is photosensitivity. The presence of external radiation due to absorbance of illuminating radiation, the trapped electrons get excited by receiving photon energy. The depth of the trapping center are multi-valued. Depending the energy of incident radiation, electrons trapped at different trap depth, trapping center get released accordingly. As a result, photocurrent increases, that is photosensitivity increases. Figure 4, this one. And the variation of photosensitivity with external thermal energy. This is also this. Simultaneously, on application of thermal energy on the flame, its thermal velocity increases due to the achieving kinetic energy by the trapped electrons. The probability of thermal ionization of trapping center increases at high temperature. The kinetic energy of the trapped electrons when exceed the limited value of the trapped depth, the electron jumped out from the potential well to the conduction band and increase photocurrent. As a result, photosensitivity increases. Thank you. Thanks.
Thank you, Dr. Kolita, for your presentation.
Yes.
I think we have a couple of few minutes, 1 minute only, to take questions from the audience. Yes, any questions from the audience? Yeah, I have one quick questions for you. I mean, can you go to the slide number 13, please?
Okay.
Slide number 13, the previous one, I guess. Yeah.
Okay.
I think here what you have shown in the picture, bias voltage with at temperature, right? And the photosensitivity.
Okay.
Yeah.
Yes.
What you have claimed, it is with the increasing temperature, the sensitivity will increase or decrease. First of all.
Increase.
But you
Increase.
see see your color of the graph says that at 330, it shows a quite steep, right? So the photocurrent, I think it is a photosensitivity, right? And at 403, yes. it is near to the zero value. I mean, I believe that with the increasing of the steep of the photocurrent, the parameters, so it should be more, right? At high temperature. What you have stated in your presentations, but it seems that it is contradictory. Your graph seems to be contradictory what you have stated in your presentation.
No,
can you comment on
when the temperature, whenever temperature increases, the trapped electron get ionized and they get energy, and then they get released and increase the photocurrent.
I understand, but see the current is not increased. So you have what is along the y-axis? It is photosensitivity.
Sensitivity.
Okay, so along the x-axis, so with increasing temperature, okay, so this should be the blue curve should be more. I think the slope of the blue curve should be more compared to 303 Kelvin. If I have understood your presentation correctly, isn't it?
It is room temperature. The blue is at room temperature 303 Kelvin. Oh no. Okay.
Understood what I want to say.
Yes. Oh no. Perhaps these numbers have been written wrongly. Okay, thank you for your point. Okay, sir. Actually, this is 403.
I think you have leveled it. You have not leveled it properly. That's why.
Okay. Thank you, sir, for your kind information.
Okay. All right. Thank you so much, Dr. Kalda, for your presentations.
Thank you. Thank you.
Okay. So, is there any final comment from the conference side? Physics.
Okay. Yeah. This is the last talk for session 2 actually. So we'll be starting the session 3 scheduled around 2 o'clock. So let me thank Professor Nath for his valuable time basically, and the beautiful talk followed by the Q&A session. Yeah, thank you so much, sir. And we again plan to invite you. We'll be delighted if you would visit our college sometime when you come to in-laws, when you visit our college. It will be great.
Sure. I'll be happy. In fact, I'll be happy to deliver a talk there in person also.
Surely, sir. Please let us know whenever you will be available. We'll arrange for it very quickly. Yeah.
Okay.
Thank you so much, sir. Thank you so much for your time.
Thank you. So,
Okay.
so can I sign off?
Yeah, sure, sir. Sure.
Okay.
Okay.
All the best from my side.
Yeah. Thank you so much, sir. Thank you.
Mhm.
Okay, for the participants, for the presentations in session 3, so we'll be starting at sharply 2 o'clock, just 10 minutes from now. So it will be chaired by Dr. Darpan Bhattacharjee from Bhawanipur Anchalik College. So the presenters, the chronology will be in such: Ubali Dihinia, then Sultana Rizwana Haq, then Arista Gogoi, then Shagar Bhattarai, then Nivedita Dihinia, then Pukhrum Sonika Devi, and Bidubhushan Brahma. Okay, so I request all the presenters to be present on time and check and for the smooth conduction of the event. Okay, so see you in like 10 minutes. Okay. Okay, I can see your screen, Bubali. Okay, so Dr. Bhattacharjee, it's over to you. Okay.
Thank you, Dr. Vivek Barwathapa. So it's Pubali Dihinya from Tezpur University, Assam. So she will be talking about strategic and challenges in two-dimensional material-based hydrogen gas sensors. Pubali, your voice is not audible.
Hello, am I audible now?
Yeah, it's fine.
Okay. Good afternoon, everyone. Myself, Pubali Dihinya. I am a PhD research scholar in Department of Applied Sciences, Tezpur University. So today I am going to present about the strategies and challenges in two-dimensional material-based hydrogen gas sensors. This is the outline of my talk. I will start. Okay. So I will start with a basic introduction. Okay. I'm not able to change the slides.
Okay, I think there's a lag on your end.
Okay, now it's fine. So as we all know, hydrogen is the lightest element in nature, and it's abundant in its various compounds. Due to its high energy density, it has potential for future energy resources with zero carbon emission. Currently, hydrogen are produced by burning biomasses and natural gas, but people are trying to develop some new technique to produce green hydrogen gas, which can be applicable for transportation, healthcare, and industries. But hydrogen is highly inflammable with low ignition energy, and since it is colorless and odorless, it is difficult to detect if there is any leakage. So we are in need of a high sensitive hydrogen sensor to avoid any accident in future. In 2007, US Department of Energy has gave some target for a ideal gas sensor. But in this era of Internet of Things, people are mainly using the smart devices. They are focusing on the smart devices. So apart from these parameters, we are in need of a hydrogen sensor, which is also flexible, lightweight, simple to operate, and needs low maintenance and also wearable. As per the data of Web of Science, the research on hydrogen sensors is growing tremendously in last 10 to 15 years. The hydrogen sensors works on different mechanisms, but here I will mainly focus on the chemi-resistive hydrogen sensors. In chemi-resistive sensors, the metal oxides shows excellent hydrogen sensing property. In fact, metal oxide-based hydrogen sensors are also available in the market. But these sensors mainly works at higher temperature and high temperatures like more than 150 degrees centigrade, but which is not recommended for hydrogen gases. So we are people are looking for a hydrogen sensor which can operate at room temperature. The metal-based sensor like platinum and palladium, they show very high sensitivity for hydrogen, but their responsivity is very slow. So people are looking for another materials like carbon allotropes and other 2D materials, and it is seen that these materials with this metal catalyst shows excellent hydrogen sensing property. Here is the image of a 2D material-based hydrogen sensor. This flat yellow and blue color is a 2D material. This is the substrate, and these are the electrodes. And these brown colors are the catalysts. In presence of hydrogen environment, this catalyst absorbs the hydrogen and form this compound of palladium HX. This compound changes the work function of the material. And I'm not going to in depth of the mechanism, but due to the change in the work function, the resistance of the material, whole system changes. And the resistance also depends upon the concentration of the gas also. By measuring the change in the resistance, we can measure the sensitivity of the material. And this same mechanism is also applicable for the flexible gas sensors. Before moving forward, let me introduce about a little bit about 2D materials. These are nothing but the atomically thin materials. In bulk form, they are stacked together with a weak van der Waals force. Some example of 2D materials are graphene, transition metal, dichalcogenides, MXN, etc. And this material has very high, strong light matter interaction and also high surface to volume ratio, due to which they have promising application in optoelectronics devices, sensors, and catalytic activity, and many more. This is an image of 2D double layer MOS2 with thickness of 1.3 nanometer. So let's look at the performance of some 2D material-based sensors. As you can see here, this platinum decorated RGO, reduced graphene oxide, can and this platinum decorated graphene can show sensitivity at very low temperature and at least around room temperature. And their performance can be enhanced by illuminating them in light. Also make a compound with some polymers. In fact, this transition metal dichalcogenides based sensors also shows good response in the under the illumination of light. Similarly, MXN based sensors, they also can show sensitivity in room temperature. In fact, MXN and transition metal dichalcogenides based heterostructure based sensors are also developed for ethanol sensing, but till now nobody has reported any heterostructure for hydrogen gas sensing. In summary, this 2D material can work at room temperature, but at this moment these materials have the other sensitivity and concentration. These quantities are very high, so more research required for make a commercial and 2D material-based gas sensor. So let's move to the opportunities. Since 2D materials are low cost and solution processable, there is a possibility of making inexpensive sensors in large scale. Also, 2D memory has huge number of potential candidates for gas sensing. In fact, their heterostructure and composites shows enhanced and new exciting properties. And due to their atomic thickness and flexibility, it is a perfect candidate for flexible and wearable sensors. But though the semiconductor performances are good in laboratory environment, due to selectivity issue and performance decreases in other in the environment of other gases. Also, some materials react with oxygen, which will raise the stability issue. So, for commercial use, control, fabrication, and reproducibility will be also an issue for these materials. Let's look for the future sensitive parameters at room temperature for commercial sensors. And this can be achieved by better understanding mechanism of 2D materials involved, and hence the selection of suitable material for sensing in terms of their electrical conductivity and also their chemical properties. Also, we can develop 2D material-based, highly sensitive, lightweight, flexible, wearable sensors. Also, using hybrid 2D material as well as their composite to design novel hydrogen sensors, which will leverage their new properties. And this may give a revolutionary gas sensor, which can replace the traditional catalysts like palladium and platinum. So, in summary, we are looking for a highly sensitive, flexible, wearable, room temperature sensor. And 2D material and their hybrids has potential to make revolutionary hydrogen sensors. So, at last, I would like to acknowledge DSC SCRV CRG grant and Tezpur University Research Grant for funding this project. And also, I would like to especially thank my supervisor, Dr. Pranjal Kumar Gogoi, and my lab mate, Sitakanta Panda, for supporting me during this period. Thank you.
Thank you, Ubali, for your nice presentation. So it is open for discussion. If anybody wants to ask any questions, yes. Okay. So Ubali, I have a question for you. So what substrate that you have used in the gas sensor?
Substrate can depends upon the application. For flexible electronics, we can use PDVF and PET substrates, and for other gas sensors, we can use silicon dioxide substrate also, and also people have used glass substrate also for gas sensors as a substrate.
Okay, fine. And what is the advantage of this hydrogen gas sensor over other gases? I mean, other gases can also be used for gas sensors.
Exactly, but other gas, they are very low, small. Low research in hydrogen gas sensors because they are non-polar in nature and very difficult to detect. So that's why I am focusing on mainly on hydrogen gas sensors. But it's not like advantage. All gases are toxic, but these are very high volatile. Inflammable. So for preventing further accidents, we need to detect hydrogen actually.
Okay,
and also,
fine.
people are focusing on hydrogen gas-based EVs actually. So we need really required hydrogen sensors.
And it is easily available.
Yeah.
Yes. So fine. Thanks for your presentation.
Okay, thank you.
Okay, thank you, Ubali. Our next speaker is Sultana Rizwana Hope from Condensed University. Are you connected with us, Dana?
Yes, sir.
Okay, you can share your presentation.
Hello.
Yes, you can start. Yeah.
Good afternoon, everyone. My name is Sultana Rizwana Hope. I am from Department of Applied Sciences, Guwahati University. Today, I am going to present a small part of my work entitled A Study on Optical and Structural Properties of PBS Adeno Core Shell Nanocomposite Embedded in Panimetrics. So first of all, what are core shell nanocomposites? In core shell nanocomposites, there is a material used as a core and another material is deposited onto it to make the core, the properties of the core very enhanced. The shell material protects the core from outside corrosion, degradation, and agglomeration. It can be any type of shell like silicon oxide, carbon, metal, or any polymers. The main work of the core, shell is to protect the core from agglomeration, oxidation, and degradation. The core shell materials can be classified into different types like single core shell, multi-core single shell, single core multi-shells, and multi-core multi-shells nanocomposites. And they have some application in the field of drug delivery, bioimaging, sensor, photocatalytic activity, solar cells, etc. The selected semiconductors materials, I have used lead sulfide and zinc oxide as core and the shell material, which belongs to group 4,6 and 2,6 of the periodic table. The selected capping agents, I have used PANI, that is polyaniline, as the capping agent for the experiment, and it has been done by polymerization of aniline. These are the objectives of my work. Now I'm going to discuss about the synthesis and the characterization part, then conclusion and future aspects. I have used chemical precipitation method for the synthesis of the work. The chemicals used are sulfuric acid, ammonium peroxysulfate, aniline for the formation or polymerization of PANI, and lead nitrate, sodium sulfide, and zinc nitrate and sodium hydroxide for the formation of PANI PBS and PANI PBS ZNO core shell nanocomposites. Now I'm going to discuss about the synthesis. I have synthesized 5 samples, 1 core PANI PBS core and 4 PANI PBS ZNO core shell nanocomposites by increasing the concentration of the cell matrix from 0.4 molar to 1.6 molar and putting the other precursors constant like the PANI, lead nitrate, and sodium sulfide. Now the characterization techniques. I have used UV visible spectroscopy, PL, XRD, SAM, and EDS. Now I'm going to discuss about the UV spectroscopy. From the images of UV visible spectra, you can see that the absorption edges are red shifting from the core, which means the larger size nanomaterials are forming. From band gap also you can see the band gaps are decreasing as compared to the core. That means this larger size particles are forming due to the deposition of shell over the core. From PL, you can see that the emission peaks are also red shifting as the shell materials are, the concentration of cell materials are increasing. It is also observed that by increasing the shell material, the intensity is decreasing. The field intensity is decreasing. From XRD, you can see the presence of the plane of pure PANI and cubic lead sulfide is observed in the core material C1, while in case of C1Z1, that is core shell, the extra peak of ZNO is also present, which proves the presence of zinc oxide over the core. The average crystal size of the C1 core is calculated to be 7.34, and for the core shell material it is 10.81 using the Dibya formula. Now I'm going to discuss about the SAM and EDS analysis. From SAM analysis, you can see the formation of spherical nanoparticles having dark inner core and bright outer shell. And from EDS also, you can see that the presence of lead sulfur, besides lead and sulfur, there is a presence of zinc also, which proves the formation of cell over the core. I have also used shown a histogram which shows that the maximum number of particles are observed in the range 80 to 100 nanometer. In the results, in this study, we have synthesized lead PANI PBS, and PANI PBS ZNO core shell nanocomposites. Different characterization techniques have been adopted. From UV analysis, it is proved that the core shell materials are red shifted as compared to the core. From PL, the red shifting can be seen, and intensity is decreasing as zinc oxide cell deposition is increasing, except C1Z2 sample. From XRD also, the average crystallized size is found to be 7.34 nanometer for the core material, while for the coercion material, it is 10.81 nanometer. The same images shows the formation of spherical nanomaterials having dark inner core and bright outer shell. These are some of the references. And future direction of the present work, we are working on the application part, the gas sensing of the Pani PBS and Pani PBS jet composites.
Hello, Sultana Rizwana Haq. You are not audible actually. Hello, Sultana. Okay, anyway, there may be some connectivity issues with Sultana. So let us thank her for her presentation. So the next participant is Arista Gogoi from Guwahati University. So are you there, Arista?
Arista, are you connected with us?
Arista, I can see you here, but you may share your slides now.
Arista, please share your presentation.
Hello? Hello,
Yeah,
am I audible? Sir, internet connection got cut.
Okay,
Okay,
no
okay.
problem. So thank you, Sultana Rizwana, for your nice presentation.
Thank you, sir.
And yeah, thank you. So we are moving forward to have another presentation by Arista Gogoi.
Hello, sir. Hello.
Yes, yes, yes.
Sir, actually, the internet got cut. The Arista Gogoi is also with me. Her also got cut. Can she
Okay.
give tomorrow or later? In the next.
Okay, she may present later on.
Okay, sir. Okay. Thank you, sir.
Oh, okay, fine.
So our next speaker is Nivedita Dibya. Dr. Nivedita, are you connected with us?
Yes, am I audible?
Yeah.
Yeah.
Please share your presentation.
Is it visible?
Yeah, you are visible.
Okay, yeah.
Presentation is visible. Yeah.
Thank you. So, good afternoon to everybody. I'm Nivedita Dibya from R&D College, Dibrugarh. So today I will be presenting presenting a small part of my research, which is concentration dependence photoluminescence of a praseodymium ion in silica matrix in presence of silver nanoparticle. Here I will be basically talking about the concentration dependent. If we change the silver concentration, how will be the effect of
Nivedita Dhingia, excuse me.
Yes.
Can you just make it full screen?
Full screen.
Yeah. If it is a PDF file, then you can just click Control L. You can just click Control L.
Control L.
You can also use the plus button, na? For PDF.
Yes.
Yeah, full screen mode.
Full screen, yeah.
Is it okay now?
Okay, no problem. We can go with your presentation.
Is it okay now?
Yeah. It's
Yeah.
fine now.
Today I will be presenting on the today I'll be speaking of concentration dependent behavior of photoluminescence behavior of praseodymium ion in silica matrix in presence of silver nanoparticle. So this is the abstract of my presentation. So the outline of my presentation is, first I will give the introduction on rare earth ion, then experimental results and discussion and references. So coming to the introduction, possible, it's possible, but it is very it's a very low absorption, and this can be lead to poor PL if we remove by adding suitable sensitizer or network modifiers. Here there are different types of network modifiers such as metal nanoparticle, semiconductor nanoparticle, ligand, etc. Here in this here I'm interested in metal nanoparticle as it's so LSPR effect and energy transfer. LSPR effect is a phenomenon, so it's a phenomenon of collective oscillation of electrons around the metal nanoparticles, which give rise to local electric field. This local electric field enhances the excitation rate of rare earth ions, and it can lead to enhanced PL efficiency. So in my work, I have selected silica as in the visible region and high degree of homogeneity, thermal stability, etc. So the rare earth I have selected is praseodymium ion, and the for metal nanoparticle I have selected silver. The fabrication method, for the preparation of the sample, I have used sol gel method because it is a room temperature method. We can prepare some samples at room temperature. It is cost effective, and it has high doping homogeneity, and we can control the starting precursor very precisely. The theory, the sample is Zudefeld theory. Here we, from Zudefeld theory, I am interested in these three parameters, omega 2, omega 4, and omega 6. Omega 2 gives the asymmetricity and covalency of lanthanide sites, and omega 4 and omega 6 gives the bulk property of the host. Spectroscopic quality factor known as spectroscopic quality factor, which signifies the rigidity and stability of the host. Now coming to the experimental part, this is the precursors I have used for the preparation of my sample. Methanol as a solvent, distilled water for hydrolysis, nitric acid as catalyst, TEOS, that is tetraethyl orthosilicate as organometallic precursors, DMF, dimethyl formamide as reducing agent for the reduction of silver nitrate, and DCCA is drying control chemical additive to reduce the cracking of the sample. For the source of rare earth, I have used praseodymium chloride hydrate, and for the source of metal nanoparticle, I have used silver nitrate. So to prepare the silver and PR doped silica matrices, I have followed these steps. First, I have mixed the rare earth with methanol, and then I added distilled water and H1O3 to this solution, and I have mixed it for half an hour. Then in Sol 2, I have mixed TEOS dropwise, and I stir it for 1.5 hours very rigorously. Then to this solution, I have added a solution previously prepared, which is prepared by mixing silver nitrate with dimethyl formamide, and both the solution is mixed and then stir for another half an hour. Then after half an hour, I have poured the solution in containers, and finally I keep the solution for 21 days for aging. And before the analysis were done, I have annealed the sample at 100 degrees Celsius to remove the hydroxyl group, which leads to the quenching of the photoluminescence emission. So these are the samples I have prepared for my study. I have prepared 6 samples where I have fixed the concentration of praseodymium at 4.48 weight percentage, and I have varied the silver concentration from 0.003 to 3 weight percentage. 2 samples, P1 and P6, are prepared, which is singly doped PR in silica matrix, and P6 is only silver doped silica matrix. And these are the instruments I have used to analyze my samples. Now coming to the result part, this is the XRD pattern for all the samples from P1 to P5. Here we can observe that there is a hero pattern from 15 degree to 40 degree of 2 theta, which arises due to the amorphous nature of the silica matrix. Then for P3 samples, we have obtained a XRD peak at 39 due to 213 plane of silver nanoparticle, and if we see P4 and P5 with a little higher concentration, we obtain 2 peaks at 32 and 46 due to these corresponding planes of silver. And we have also calculated the crystallite size using the Shearing formula. This is for P3. We have obtained the crystallite size is 16. Now coming, this is the TEM images of our sample. Here from figure A, we can see the dispersed silver nanoparticle and silica matrix. Then from the TEM image, we have also calculate the average particle size of silver nanoparticle, which is found to be 16 nanometer, and it consistent with the XRD results which we have calculated from the Shear formula. Now this is the absorption spectra for my sample from P1 to P5. Here we observe for this P1 sample, we have observed 4 absorption peak at 444, 469, 483, 593, which arises due to the transition from 3H4 to this level, and in the inset there I have shown the absorption spectra for P6, which is without the rare earth. Without the rare earth, there we can see there we observe 2 LSPR peak, which is at 386 and 472. We can also observe that as we increase the silver concentration from P1 to P5, the absorption intensity increases, which is due to the overlapping of LSPR peak of silver nanoparticle with the absorption peak of praseodymium ion. So this is the oscillator strength and Zudefeld parameter, which we have calculated from Zudefeld theory. Here I am interested on omega 2 parameter, which gives the asymmetricity around the rare earth ion site. As we can see, if we increase the silver concentration, the value of omega 2 increases till from 2 to 18. That means from sample P1 to P5. This can be clearly seen from this figure that for omega 2, I have plot another graph for to show the variation in omega parameters and AZ concentration. If we see the omega 2 graph, there is a sharp increase in omega 2 value up to 0.03 weight percentage, and then after that the curve becomes a little steady. So this indicates the asymmetricity around the rare earth ion, that is praseodymium ion, which can increase the excitation rate of excitation as well as absorption rate of PR ion, and that can lead to enhanced PL efficiency. So this is the excitation spectra recorded at 433 nanometer of emission spectra. Here the excitation is maximum for P3 sample. The excitation wavelength is found to be at 377 nanometer, which is due to the transition from 4F to 5T transition. And we have selected this excitation wavelength to record the PL spectra. So this is the PL spectra under 377 nanometer excitation. Here we have observed 4 PL peak of praseodymium ion, so which is centered at 433, 456, 476, 492 nanometer due to this transition. And we can see as we increase the silver concentration up to P3 sample, the PL intensity increases, which is due to the LSPR effect. And the rare earth in the vicinity of silver nanoparticle experience highly intense electric field, which increase the excitation rate of praseodymium ion. Then so it leads to an enhanced PL enhanced PL intensity. So beyond this sample, we can see there is a decrement in the PL intensity from sample for sample P4 and P5, which is due to the back energy transfer from praseodymium ion to silver nanoparticle.
Pabitra, your time is over, so you can proceed to the conclusion.
Yes. This is the energy level diagram. This is the energy level diagram for praseodymium ion. Here we have excited the 3H4 level ions with an excitation wavelength of 377 nanometer through ground state absorption. This is excited to the upper energy level of 5D. Then from 5D higher energy level, the electrons is non-radiatively decay to the long-lived lower energy levels, and from there we can obtain the emission of PR 3+ ions. And silver nanoparticle act as secondary channel to excite this enhance the excitation rate of PR ions. So this is the time correlated PL decay diagram. This is the decay curve of my samples from P1 to P5. So here we observe a exponential stressing, which indicates the homogeneous energy transfer in the matrix. And from this graph, we have calculated experimental lifetime, which is obtained to 2 for the sample P3 compared to the singly doped praseodymium ion. So this can lead an enhancement in PL intensity of praseodymium ion. So conclusion, so here we have obtained enhanced absorption. We have obtained with AZ concentration, there is an enhancement in omega-2 parameter, and we have obtained PL intensity enhanced by 1.5 times, and from the study we have obtained the optimum concentration for silver nanoparticle is 0.03 weight percentage, and all is due to the the enhancement in PL intensity is due to the LSPR effect. So these are the some of the references, and thank you.
So thank you, Nivedita, for your nice presentation.
Yes.
So it is open for discussion. If anybody want to ask any questions from the audience. Any queries from the audience? So if there are no questions from the audience, then let's thank Nivedita for her presentation. Thank you.
Thank you. Yes.
So the next participant is Ukram Sonika Devi.
So actually, there is a last minute notice from her end. So we can start with like Arishta Gogoi. Is she here? Arishta, are you here?
Hello, sir. Yes, sir.
Okay. So please share your screen. Then,
Okay, sir.
then followed by the next speaker will be Sagar Bhattacharjee, Dr. Sagar Bhattacharjee from IIT Guwahati. And then the final one will be by Biju Bhushan Brahma from CIT Kokrajhar. Over to you.
Hello. Am I audible,
Yes.
sir?
Yes. You are audible.
Good afternoon, everyone. My name is Arishta Gogoi from Department of Applied Sciences, Guwahati University, and my topic is synthesis of PB, Zeleno, iron doped nanoparticle and their characterization by chemical precipitation technique. And this is introduction. What is nanomaterials? Nanomaterials are the class of material with at least one dimension in the range of 1 to 100 nanometer. Based on the structural dimensionality, it can be divided into 4 categories: 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanomaterials. Similarly, based on their composition, it can be classified as organic nanomaterials, inorganic, and hybrid nanomaterials. Some example of nanomaterials are nanotube, nanorod, quantum dot, etc. Now, what is semiconducting material? Now, the semiconducting material are composed of various compounds. It is referred to as 2, 6, 3, 5, or 4, 6 nanocrystal. Semiconducting material have various in application. Some examples are group 4 are silicon, germanium. Group 3, 5 materials are gallium nitride, gallium phosphide, etc. Group 2 to 6 materials is zinc oxide, zinc sulfide, etc. And also coarse-cell semiconducting nanomaterials. Now, coarse-cell semiconducting material which have properties intermediate between those small and individual and those of bulk crystalline semiconductor. They are unique because of their easily modular properties. They have various applications in catalyst, biology, chemistry, sensor, etc. For example is ZNO, ZNS, CDSC, ZNS, PBS, ZNO, etc. Now, methodology. Here, all the samples were synthesized by chemical precipitation technique. One pot synthesis technique is used for the synthesis of core materials. Here, my objective is to synthesize PBS, ZNS, ZNO iron and ZNO iron doped nanomaterial. To study the morphology and optical properties, and are characterized by UV visible spectroscopy, PL spectroscopy, XRD, SEM, and EDX. Here, the list of two synthesis samples and their compositions with a constant concentration of PVA and zinc chloride. Yeah, this is the key analysis. Here, this is a position of absorption edges and the band gap of two samples. For first sample, Z1 sample, we observed that the absorption edge is at 250.07 nanometer and corresponding band gap is 5.60 electron volt. Similarly, for second sample, the absorption edge is at 260.11 nanometer and the corresponding band gap is at 5.07 electron volt. From the figure, we conclude that the absorption edges of Z1 sample is slightly redshifted in comparison to ZNS, who is due to increase in cell thickness corresponding to the band gap value, and the corresponding band gap values are decreases. Here, this is PL analysis. Here, this is PL spectra of the sample. From the figure, it is seen that the position of the emission peak is at 291.50 nanometer for the first sample, and for the second sample, it is 291.40 nanometer, which are blue shifted in comparison to ZNS. And here, no other emission peak was observed. Here, this is an XRD pattern. XRD pattern of Z. XRD pattern shows the formation of well-defined diffraction peak. Shows the good crystal structure, and the average crystallized size of the first sample is 24.01 nanometer, which is smaller than the second sample. Here, this is the same analysis. Here, this is the same analysis for second sample. For the same images, shows that the samples are more or less spherical in shape. The EDX images show the presence of zinc, sulfur, iron, and oxygen. Histogram images shows the larger histogram images shows that the particles in between 40 to 45 nanometer, with the average size is 38.41 nanometer. And this is the result and discussion. From the UV visible spectra show that the absorption edges of zinc is blue shifted in comparison to bulk ZNS. The absorption edges are the absorption of the ZNS ZNO iron doped are slightly redshifted in comparison to ZNS sample, which due to the increase in particle size due to the increase in cell thickness. Correspondingly, the band gap value decreases. The PS spectra shows the excitonic emission is at 291.50 nanometer for first sample, and for the second sample it is 291.40 nanometer, which are blue shifted in comparison to ZNS sample. And here from the EDX from the XRD spectra shows the formation of well-defined diffraction peak, which shows the formation of good crystal structure. The XRD result also shows the estimated crystallized size of ZNS ZNO iron doped sample is larger in comparison to ZNS sample, which is obvious due to the deposition of ZNO iron dope over the ZNS. Same image also shows the ZNS samples are more or less spherical in shape. The EDX image of the is shown in which confirm the presence of zinc, sulfur, iron, and oxygen. Here are some references. Further work to be done in the remaining part of the work. It is aimed to do the following. We can use other capping agent like PVA, PANI, etc. We can also use different synthesis method, and we can also study the various application part like gas sensing, photocatalytic activity, etc. I would like to thank Dr. Suparna Bhattacharjee ma'am, Department of Applied Sciences, Guwahati University. Professor Ishanku Saikia sir, Department of Applied Sciences, Guwahati University. I am highly grateful to the Department of Instrumentation, UC, Guwahati University, and Department of Chemistry, Guwahati University for XRD and semi-analysis respectively, and all my lab mates, seniors, and my dear friends. Thank you.
So thank you, Arista, for your nice talk. So it's open for discussion. If anybody have any questions.
Hello, Arista.
Hello.
Thank you for your presentation. I have a question. During the XRD experiment, what type of plan did you observe? Means FCC, VCC in your sample?
Yes, sir.
What did you observe? Means a plan in your sample during the XRD experiment? Was it the FCC or VCC?
Sir, actually, sir. No, sir, actually.
I think it was FCC, no?
Hello, sir.
Yes, I think it was FCC plan.
Yes. Hello, sir.
Are you getting my question?
Yeah, the question is about the plane, the structure of the plane. Is it BCC structure or FCC structure?
Means what was your crystal structure?
Sir, hello, sir. Hello.
Yeah.
Sir, am I audible, sir? Sir, FCC.
FCC, no?
Sir, hello, sir.
Fine.
Yes, sir. Hello.
Yes, it's fine. It's fine. It's okay. So if there is no questions, no further questions, then let us thank the speaker once again. Thank you, Arista.
Thank you, sir.
So the next speaker is Sagar Bhattarai from IIT Guwahati. Sagar, are you there?
Yes. Am I audible to you?
Yes, you are audible. You may share your slide.
Just a minute. Okay. So I think my screen is visible to you all.
Yeah, it's now visible.
Okay. So how much time I have? 10 minutes or?
Yeah, it's 10, 8 plus 2. So 8 minutes of presentation.
Okay. So first of all, I would like to thank the organizer, Dr. Vivek Badua and Dr. Rajkamal Kakoti, both of you. I want to thank you first before starting the presentation. So the topic of the presentation is designing a highly efficient tin-based perovskite solar cell by a numerical simulation approach. So I did this in Technology Innovation Hub. I am working there. So the presentation is divided into 8 sections. First, what is solar? As we all know, what is the impact in renewable energy? The details of PV technology. If we talk about solar, we would have to go for photovoltaic technology. Then in photovoltaic, the recent trend, that is the perovskite, and its introduction, the comparison between the silicon-based solar and the methodology, the simulation and numerical methods also results in discussion and the conclusion. So why we are discussing about solar? There are a lot of information already available and everyone knows also, but I would like to just say that in renewable energy sources, solar contributes almost it's 80% of, if you compare with any other energy source. That means it is the maximum contributed in a renewable energy source which is available, and it is incomparable with any other energy sources. So as we all know why solar is important to us, it is mostly renewable, it is cheaper, and if we trap whole solar, then whole solar energy, then we can utilize it in multiple ways. So why PV is coming into the picture? So as we know, since our childhood or since almost 20-50 years, we are seeing the same type of silicon solar cell. Here, the single crystalline or monocrystalline or poly, these two are the available photovoltaic cells that we are seeing. In the rooftop also, we are seeing the same type of that monocrystalline and polycrystalline silicon. But our aim is to make it a little bit more cost effective. Also, there are a lot of issues in fabrication of silicon solar cell because of its indirect band gap and also its cost, because we need a very highly pure silicon to designing a first generation solar cell. And the most important thing is that we have not achieved up to 15% for the silicon and poly, but then we focus on the second generation because the efficiency is stuck. I will tell you in graphical presentation there that how it is stuck, the efficiency. But in second generation solar cell, what is happening? In amorphous silicon, cadmium telluride, cesium, copper, indium, gallium selenide, CIGS, which we call. So these solar cell are little bit cheaper. But the thing is that the efficiency, the main aim is to increase the efficiency, which we are not able to increase more than suppose 20% in all these solar cells which is available. Then researchers and scientists already moving towards the third generation solar cell, which is organic solar cell, which is almost one perovskite, which is the most dominant, one of the most dominant third generation solar cell. As we know, DSS, dye-synthesized solar cell, quantum dot solar cell, and other than these, there are other, that is polymer PV. So these comes under third generation solar cell. So we are discussing today about the third generation solar cells. Here, as we can see, the third generation solar cell, that means one of the member is perovskite. So perovskite is very much studied because the efficiency was 3% initially in 2009. It is very much recent. Almost we can say 15 years back. So before 15 years, the efficiency was 3%, and right now in 2019 it was 22%. Right now means in 2023, the efficiency is increased up to 26 point some percentage which is recently achieved in China. So which was also published in Nature. So we would like to go to that, but we would like to introduce about the perovskite. The perovskite means it is just a name of a Russian mineralogist. His name is Lev Perovsky. So under his name, the name is called perovskite because all that material which is having a structure of ABX3 type, they are called the perovskite materials. So first it was introduced in 2009, where the efficiency was 3.8. But right now the efficiency is, as you can see in the slide, the efficiency with these just a minute, these yellow what you can say, yellow dots. There you can see in 2000 from the curve is showing from 2013 to 2021. This was last year, which was presented by NREL. So here you can see there is an increment in efficiency from 3 to 25 in 10 years. That means we can say that 20% increase we can found in last 20 years or 15 years. But for the silicon solar cell, the efficiency was initially 5 in 1950. 5% is 1950. Right now it is achieving 16 or 17%. That means the efficiency is stuck. We are not able to increase the efficiency for the silicon. So we must move to the perovskite because perovskite has certain advantages. The advantages I'll show you here, that perovskite material, you can see the high optical absorption, the high carrier mobility property, And band gap tunability, it is cheap and easier to fabricate. By simple spin coating, you can fabricate the perovskite solar, which we are doing in IIT Guwahati. So here, the same thing, the working of the solar device is simply same, but the main thing is that the absorption coefficient, because high absorption coefficient, the solar main task is to absorb the high energy photons, or not high energy, just photons of visible wavelength, which they can trap, and they can make electron and hole pairs. So here you can see the curve. Already I have shown you the chart, and the simulation methodology we use is here. G, as you can see here, G means the generation profile, which is directly related to alpha. That means for every material, perovskite, we have the liberty to choose the absorption coefficient. If you need a high absorption coefficient, you go for the methyl ammonium lead iodide or something like that. If you need lower, then you go for the germanium iodide, or that type of material is also available. But most important thing, we should not break the energy conservation equation. There's A plus R plus T equal to 1, where A means, the absorption, R means reflectance, and T means transmittance. Similarly, JSC also says that higher absorption is our main aim, but it doesn't mean that more absorption means the more shortcut circuit current, because more absorption may lead to other mechanical issues such as recombination. That will also come into play in our study. But if you have more absorption, there's a possibility to increase the current density, that is JSC. So here, the current density is the main equation I'll come to, that is PCE, power conversion efficiency, which is directly related to current density and open circuit voltage and fill factor. As you can see, it is directly proportional. So if you try to increase the KC or VOC or fill factor, then you can increase the power conversion efficiency very effectively. That means if you have the IV curve in solar, if your curve is steep, that means the curve is very much steeper. So you can see that it will have a higher fill factor. So these are all the parameters which we need to optimize in our theoretical optimization. And I prefer theoretical optimization because of 2-3 things. Because we don't need sophisticated equipments. We don't need all type of errors. Suppose if you want to fabricate a solar or anything in fabrication, you must have always find there are a lot of errors, and if you want to fabricate some OLED also in solar as well, if you obtain 25%, you need to find, you always find 2 or 3% is only. But I will come to this. And also there are other advantages that we cannot vary in experimental. If you make a layer of 1 micrometer, you cannot vary that what will happen if the thickness is 2 micrometer, what will happen in 3 micrometer. But in theoretical optimization, you can predict, and it comes out to be almost nearly equal, as we have already obtained in same simulation. We go for the fabrication, we obtain almost same type of results. So here the methodology we used that is, I have also expertise with 7 or 8 softwares, so which does the theoretical calculations. But also apart from that, we are also doing the experimental. So there are a lot. I will not go into detail because we have limited time. So here we'll go to the resultant discussion. In this presentation, I would like to focus on the double stacking of observer. In 2020, I was the first person to predict that the dual stacking of observer, which will increase the efficiency. Because before this, the introduction was the tandem devices. Suppose one observer, one ETL, one ETL. This is the fundamental PIN structure of solar. But we introduced the double observer. Suppose I'll tell you that if there is one observer of methyl ammonium tin iodide or methyl ammonium lead iodide, anything, so it will absorb up to a particular level. Suppose if the band gap is 1.6, it can absorb up to almost 800. Okay, but it will not absorb the 900, the 1000 wavelength photons. So that will be absorbed by the another one. The working principle of this dual absorber stacking of the layers is same with tandem devices. But tandem device says that First, you make one device, then you go for the lower bandgap device. Then if you make combine both of them, then it will give a third device, which is more efficient than the first two, and that is the tandem devices. But here we have used dual absorber, which is one is having higher bandgap, the other one is having lower bandgap. So the working principle is same. So as you know, the diffusion mechanism, it is already shown here. So apart from that, we have also obtained that, as I told you, that high efficiency is our prime goal. So in this work, I have obtained more than 30%. So all the related studies we have done. Suppose I told you that how much thickness to keep to make the efficiency maximum. Suppose we varied the thicknesses from 0.1 to 1.6 or 1.5. So you know that how much thickness will give the maximum result. As you can see, if you directly go without the theoretical approach, then there is one problem. If you see eta, that is efficiency, if you see here that in 18% is obtained in 1 micrometer of thicknesses of the absorber layer, first absorber layer. So if you go for 18% absorber with 0.1 micrometer, so we need to go further. We cannot increase the thicknesses. Now, if you increase the thickness and make it up to almost this, that means almost 1 or 1.25, here you can see a very little decrease here, a slight drop. If you keep increasing it, the curve will come, but I didn't do because it's just about the data. Data says that it will decrease in increasing the thickness. Why? Because of the more recombination with higher thickness of the electron and holes. So here we have obtained of 31.5%. So, and now there is a question that why don't we go for only thickness optimization of first layer? What about the second layer? When we did the thickness and defect variation, we can have a very good contour curve, which is giving, here you can see 34% efficiency we have obtained, which is almost near to the Shockley-Queisser limit, which is not more than 35%. That means we have minimum every type of issues, and we did it. And we obtained it the maximum efficiency which can be obtained by this dual absorber layer. But tandem devices is obtaining more than 40. But we are going for, because tandem making is very complex, making tandem is very much costly. We have to go for this, and the efficiency is also high. Similarly, how much temperature to keep, because there are a lot of temperature regions. Suppose in our India, the temperature is lies between 20 degree to 50 degrees somewhere. So why won't you go for almost 20 degree to 80 degrees Celsius? What will happen in Sahara? That's about the solar device we can predict here. So here you can see that VOC will decrease. So VOC, but JAC is increasing here, you can see, but the data is very it's up to third decimal points. So that means it is almost equal. That means there's no change. But for the VOC, you can see the efficiency is 0.98 to 0.94. That means it decreases for the temperature increment. That means it says that the maximum efficiency of the perovskite devices is obtained at the temperature of 300. That means 27 degrees Celsius. Here I have written all the outcomes. Similarly, I go for interface defects. So here you can see also that if we keep the interface as 1 into 10 to the 10 centimeter cubed, so there the efficiency is almost more than 30% that we'll focus, our main prime focus. So if I go to the conclusion, then we have done this particular calculation in SCAPS 1D. More than 30% we have obtained. We have used ETL, HTL, C60 and CUSTN. And there is one important thing. If you talk about the C60, that means this is cheaper. CUSCN, that it is cheaper than the spirometer. If you go for the spirometer design, the 10 gram will cost around 50,000 rupees for spirometer. But that's why it becomes very much costly. So we replace the spirometer with QPress SCN, so which is having more efficiency. As you can see, higher interface defect will lower the not temperature, the efficiency to 23% for designing a solar device. So I kept my presentation very short. So based on this, we have already doing this project. We are doing the project on the large scale production of energy from organic, that is perovskite solar cell for underwater this project I have recently got, and another I have got from DST as well. So till now, I have done 84 publications with various softwares, SCAPS 1D, SAT4, GPPDM, and other MATLAB software, DFT. These all type of thing I have done. Also, apart from it, we have done the experimental fabrication also, where we have obtained 21%, which is very huge. So because the fabrication is a little bit tough for the perovskite, but we want to minimize the cost as well as we minimize already all type of defect in experimentally as well. So apart from this, we have done books and chapters. Any question, you are most welcome. So I think that's all to my presentation. Any question?
So thank you very much for the nice and informative presentation. And you have 84 publications. That is really incredible. So,
thank you very much.
Yeah. So any questions from the audience? So may I ask you one question, one simple question?
Please. Yeah.
What are the other applications of the perovskite material apart from its uses in solar cells?
Yeah, perovskite material is used for absorption mainly. So I have seen in OLED application also. I have done the organic LED designs, organic. We have done, I think, 2 or 3 publications regarding this as well. So mostly those have those applications which are related to the absorption of photon. There we can use the perovskite. So we are not only working on the perovskite, we are working on the different ZNO. Suppose biosynthesized ZNO I used in this perovskite solar device design, which is more cheaper than the conventional way, that is chemically synthesized. So that kind of thing also done. But for perovskite, I want to tell you that those applications where the absorption is prime focus. Suppose OLED designing also, there we can use this material as well.
Yes.
Yeah, and it is organic. Always that organic, inorganic, based on your thing. Since organic is little bit non-toxic. Suppose I told you, some people used to tell that methyl ammonium lead iodide is toxic because there is lead in it. So we say, okay, no problem. We'll replace the lead with tin or germanium. Then it will become non-toxic as well. So that is the thing.
And the efficiency remain the same.
No, efficiency will increase more. Because in tin, I have with lead iodide I obtained almost 18%. With tin I went up to 22%. Because all type of optimization is needed in before going for the fabrication. So we are already working with the Department of Chemistry as well for designing or DFT based calculations. So for effectively increment, because directly going for a fabrication is not always the solution, because just going for someone else's literature survey and you prepare accordingly, it is not the efficient way. So we design theoretically, go for the fabrication after that. Thank you for your question. Thank you.
Yeah. So any other questions? If there are no further questions, then let's thank our speaker. Thank you so much for your presentation.
Yeah. Thank you for your kind words and allow me to present. Thank you very much.
Thank you.
Bye.
So our next participant is Bhattacharjee Brahma. Bhattacharjee Brahma, are you there?
Yes, sir. I'm here.
Yeah, you can share your slides.
It is visible, sir?
Yeah, it's visible.
Okay.
Can you make it full screen? Yeah, it's fine.
Thank you, sir. So, good afternoon to everyone. My name is Bhattacharjee Brahma, a PhD scholar at the Central Institute of Technology, CIT Kokrajhar, pursuing PhD under the Manasi Puzar Madam, HOD and Assistant Professor of Physics Department. So I'll be presenting on the R&D silk fiber composite with single wall carbon nanotubes for applications in conductive fiber. So these are my outlines. So I'll start with the smart fabrics. So smart fabrics and conductive fibers are emerging as revolutionary technologies in material engineering supporting and in diverse applications like in sensors, batteries, smart display systems. The conductive fibers are often fabricated using different materials, reduced graphene oxide and carbon nanotubes because of their excellent conductive properties. But one of the main challenges which the researchers are facing is achieving the high mechanical and electrical properties within a single fiber system, along with the necessary thermal stability and also durability for the textile use. For instance, the spider silk fiber has been combined with the multi-wall carbon nanotubes, and it has showed good electrical conductivity, but it lacks the thermal stability and durability needed for textile applications. So there are one of the best material for designing of the smart fabrics is silk. Now there are various sources of silk are there, but the silkworm silk is the abundant one. And also it has got unique properties of being biocompatible, biodegradable, and robust mechanical strength. So there have been many applications in biomaterials, optics, biosensors, and wearable electronics also. So to achieve its full potential, we need to have understanding and knowledge of the silk. So there are various types of silk are found. Usually it is categorized into two mainly categories, mulberry and non-mulberry. Mulberry silk is Bombix mori silk, where we locally call it as a path silk. And the non-mulberry silk, eri silk, muga silk, and tosor silk. So what is the composition of silk then? So the composition of silk, the main silk is composed of two types of protein. It is fibrin and the sericin. The fibrin gives the mechanical strength to the fiber, and sericin is the glue-like coating over the fiber. The repetition of this polypeptide chains gives structure to the fibrin and ultimately the fiber. Here in the table, I have shown the percentage of the fibrin and the sericin present in the different types of silk. Here you can see the percentage of fibrin is very high in case of eri and muga. So of course it tells us that the mechanical strength of the eri and muga will be very high. So what causes this high mechanical strength? It is because of the amino acid sequence which is present in the eri silk or the silk. So the fibrin consists of repeated sequence of the amino acid which forms beta sheet, alpha helix, and random coil structure. So this now here in this figure, I have shown the one amino acid sequence, but in the case of non-mulberry silk, the amino acid sequence is quite different. It is polyalanine. Rather, in case of mulberry silk, it is polyglualanine. So the polyalanine sequence gives a very high amount of binding energy to the beta sheet, which causes a very high, better mechanical strength than the non-mulberry silk. Now, since we have our base material, non-mulberry silk, eri silk, that's why as our base material for the smart fabrics, we need to incorporate it with some very high electrical conductivity material. So in this case, we have chosen single wall carbon nanotubes. So here you can see single wall carbon nanotubes are cylindrical nanostructures composed of single layer of carbon atoms arranged in a hexagonal lattice, renowned for their unique and physical and chemical properties. So it is very excellent for different types of fields like nanoelectronics and transistors and conductive films and various sectors. So the tensile strength is also up to 100 times greater than the steel. And it can be chemically modified to enhance the properties and to improve compatibility with different matrices, which we will be doing here. We will be incorporating the eri silk fiber with the single wall carbon nanotubes to get a good result, to get a good fabrics result. So this is a synthesis method, a very easy synthesis method. Here at beginning, we take the acetic acid as a medium, and we take the single wall carbon nanotubes where we disperse the on the acetic acid. So we stir it for the 30 minutes, and then after it, we put the eri silk fiber into the solution where we stir it for 2 hours at around 70 degrees Celsius. Then after this 2 hours, we collect the sample and oven dry it, and later on we keep it for the sample characterization. So we have done various types of characterization to ensure that these two have incorporated themselves along with each other. So at the beginning, I've done X-ray diffraction, which tells us that the two single wall carbon nanotubes and the eri silk fiber has incorporated among themselves very easily. So if you see for the ESF, eddy silk fiber, it shows a peak at around 16.99 and 20.71, which represents alpha helix, and at 24.11 and 30.61, it also shows peak, which represents the beta sheet structure. The single wall carbon nanotube shows a peak at around 26 degrees Celsius with the values of 0.3506 nanometer. Additionally, it also shows a peak at 43 and 44 with a corresponding Miller indices of 100 and 101 planes. So if you see in the composite material, it contains both the peaks for eddy silk fiber also and single wall carbon nanotubes also, which shows that these two have incorporated among themselves. Then also we have tested with the TGA. We have tested the thermally. We have tested it with the TGA. So here, if you can see, the ESF eddy silk fiber, it degrades to about 40% between 200 to 369 degrees Celsius. But after the incorporation of single wall carbon nanotubes, it degrades to about 34% only between that same very temperature. So which tells us that after the incorporation of the single wall carbon nanotubes into the eddy silk fiber, it has become more thermally stable than it was before. Then we have also tried to see what is there on the surface of the eddy silk fiber. So with the help of scanning electron microscope. So if you see here in the eddy silk fiber, it was clean earlier, but after the incorporation of the single wall carbon nanotubes, they are on the surface. The single wall carbon tubes are on the surface of the eddy silk fiber. Then we have also tested the tensile strength for the mechanical strength of our sample. So with the help of our figures provided, we can see there is a steeper, the composite material shows a steeper initial slope compared to the eddy silk fiber, which indicates that it has a high which indicates that the composite material has high elastic modulus, making it stiffer and more resistant to the deformation under initial loading. It also suggests that it can withstand a greater maximum performance stress before necking and failure, and it also suggests that it is more ductile, allowing it to undergo more deformation before breaking. So after all this characterization, we can say that they have successfully incorporated among themselves. So what are the various applications we can do? So we can go towards the various types of applications, like we can choose for the wearable electronics, then flexible sensors, smart textiles with conductivity and structural integrity. Also, the conductive eddy silk fiber can be utilized for medical textiles, smart clothing, electronic interconnects, flexible and conductive fibers. So this is my conclusion. So the combination of this eddy silk fiber with single wall carbon nanotubes yields a unique conductive material with exceptional properties, presenting opportunities for diverse applications in textile, electronics, and biomedicines. Then the future development, the continued research and development in this field hold promise for further enhancing the conductive properties, scalability, functional and versatility of the eddy silk fiber composite. Innovation amongst manufacturing process and application will derive the future prospects of this composite. What are the potential impact on our lives? The advancement of this conductive eddy silk fiber composite may contribute to the evolution of sustainable high performance materials, offering solutions to the next generation wearable electronics, advanced medical textiles, and eco-friendly electronic components. So I'd like to acknowledge my supervisor, actually Dr. Manasebuzar Mure Madam, for providing with consistent direction. And also I'd like to thank the HOD of the Department of Chemistry for CITK for providing space and facilities. Also, I'd like to express my gratitude to the IQAC and Department of Physics, Bhawanipur Anchalik College, Barpeta, Assam, for providing me with the forum in which to discuss my research. These are my references, and thank you.
Thank you, Dr. Brahma, for your presentation. So if there are any questions from the audience, then you may ask. Any questions? So can you just go to the slide where you have shown the synthesis method of the eddy silk fiber? Some diagram was there. Yeah, this one. So, can you just tell me it is start for 30 minutes for 2 hours at 70 degrees centigrade? So, the time is predetermined or is calculated or what?
No,
Suppose it
sir.
is kept for 3 hours or 5 hours or for
So
1 day,
actually
then
the
yeah.
medium is acetic acid medium. So if we keep it
Okay.
more, then the AD silk fiber, its own properties may degrade also. We cannot keep it for very longer period of time, sir.
Okay, and why it is 70 degrees centigrade, not less, not more?
So actually the 70 degrees Celsius, actually, sir, I have actually followed one of the research papers.
Okay, fine. So, thank you for your presentation.
Okay. Thank you, Dr. Bhattacharjee, for chairing the session. So this brings us to the end of day 1. It was a great day actually, with around 20 plus presentations, and the Q&A sessions were very good. I would like to congratulate everyone here for sticking up to the last talk today. Actually, it's quite hectic. I can understand, starting from 9 o'clock staying up till 3. So thank you very much. So for tomorrow's session, actually, tomorrow will be again starting at around 9:15 a.m. in the morning. So for tomorrow, the track will be completely in astronomy, astrophysics, and cosmology. The plenary speaker will be Dr. Rupjyoti Gogoi from Tezpur University. So she will be delivering her talk at 9:15 a.m. And followed by that, we have three presentation sessions, which will be chaired by Zaikumba Singha from South Africa, University of Cape Town, then Dr. Vishal Parmar from INFN, Italy, and by Rupjyoti Gogoi from Tezpur University. Okay, so then we'll meet you tomorrow. Thank you so much. Thank you so much for joining.